Hello, hello, mic test. Hello, hello.
No, no. So you need a okay, you
I have an adapter.
use this.
So if this works, I can use this directly.
Yeah.
No, but you need an HDMI cable, right? Yeah. Where's your HDMI?
Yeah, yeah. Here's HDMI.
So that's your HDMI. That should go in over
Ah.
from here. Here. Yeah.
This is USB-C. Ah, is yours right?
No, no.
Oh, it's showing the screen.
Yeah, yeah. Hold on. So in fact, I think if okay, maybe it might be better to move this guy one before me and have me speak um, just before lunch. And the reason is that this takes time. Then if he's talking with his own, like on this computer, then it's easier to just keep the flow going.
Okay. Let me ask. So,
Okay, can you just
Yeah,
can
yeah,
I just
hold on.
try?
Yeah, yeah.
Yeah.
Okay. This looks. Let me just check. This thing over there.
Can I put to the other?
Wait, hold on. That's right. Should be okay. Let me just check one thing. Okay, should be.
Is it okay then?
I Abhishek, give me एक pen और paper. हाँ.
लंच का तो हो गया ना अभी
फ्री लंच का सेंड करें कपड़ा है क्या
वो ठीक है वो नीचे कोई नहीं देखेगा
ये देखने का बात नहीं है
टिश्यू नहीं
ये है क्या टिश्यू है
टिश्यू नहीं ऑर्डिनरी पेपर
ना 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 मैं देखता हूँ अभी लंच से पहले का भी बनाया था ठीक से पहले की स्लाइड एंड लोगों को बुला के
तो तुम सुनो ना अभी करने का क्या
क्या अभी कुछ नहीं है
अभी कुछ getting cut, right? Sorry.
What did we do last time?
Yeah,
190 or something.
You
right?
can
Just put here 190.
move it down a bit.
Good.
Ah, okay.
Now it will be.
Nothing's getting cut, right?
Okay. And I can use this, right?
You'll have
Ah,
to turn it on.
okay. No. Okay.
Okay, guys.
Yeah.
Let's stop watching this.
Oh yeah. No video.
The laser pointer is on, yeah.
No. Pointer is working.
This is not connected.
It's not
put here.
connected. Ah,
Correct.
yeah. Okay. No.
Put in a different slot.
No, didn't.
Try this. We can try the one at the bottom as well. Sorry.
Should I?
No, just
Okay. No, it doesn't. Maybe you have to
Yeah.
click. No.
yeah, can you try now?
No. This. Yeah. Okay.
Okay, so good morning all. So we are going to start day 2. So we'll have, it's a Carolean morning. So we'll have 2 talks. And then we will be ending with something exciting on rethinking about, this complex multiplication. So we are going to start with Daniel, who is going to talk about some universal sectors of Carolean CFT2. So Daniel, please.
Okay, yeah. So let me also start by thanking the organizers and also apologize for only including IoT here as an affiliation. So for the record, we're at the NISER campus and in one of the nicest lectures I've been. I want to talk first about a review on Carol physics and flat space holography, and in the second part about universal sectors of Carolean CFTs. So this is based on work with a number of people, but this specific work was done together with my postdoc Ankit Agarwal, who's currently applying for postdoc positions, with Arjun Bakshi, with Stéphane Detonnet, and Jean Simon. So this is the collaboration between Night Cafe and me on Alice Meet Red Queen. If you're puzzled by this, you will get the explanation 3 slides from now, why this is relevant and what Carol means in the first place. Okay, so for those of you, okay, there's some echo. Okay, is it better if I stand here? Oh, there's some feedback. Here? Okay. Okay, so I'll start with a review on Carol symmetries. So this is going to be introductory and an overview. Then I'm going to give you the main statement on the flat space Carol CFT correspondence. And then I show you some specific example of the flat 3 CCFT2 correspondence, some checks based on symmetries. And then in the more technical part, I discuss these universal sectors, in particular the Schwarzen sector of Carolean conformal field theories in 2 dimensions with focus on the Carol partition function. Okay, so let's start very basically with Carol symmetries. What are they and why do we care? So Carol symmetries are spacetime symmetries and they complement the well-known Aristotelian, Galilean, and Lorentzian symmetries. And the distinguishing feature is that space is absolute, but time is relative. So it's sort of the opposite limit of the Galilean limit, and you can understand it as a speed of light going to 0 limit. So if you start with the Lorentzian light cone, then in the Galilean case, it would open up, and in the Carolean case, it would close. So there's a limiting definition of a Carroll spacetime. It's the C to 0 limit of a Lorentzian spacetime. And this feature, that the speed of light goes to 0, is what inspired Lévy-Leblanc to call the spacetimes Carolian, after the nom de plume of the author of Through the Looking Glass and Alice in Wonderland, because there's this scene where Alice meets the Red Queen, and the Queen says that, now here you see it takes all the running you can do to keep in the same place. Just because when you move within the light cone and the speed of light goes to 0, you're not actually moving. There's also an intrinsic definition of Carolian spacetimes, namely as spacetimes with metric signature 0 plus 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 and a vector field in the kernel, so you don't have to think about Carolian spacetimes as a limit from Lorentzian spacetimes. The simplest example is a flat Carroll spacetime, the C to 0 limit of Minkowski. If you do this, you just end up with a metric that has a 0 here and the Kronecker delta in the spatial part, and the vector field in the kernel is just dt. And the Carroll boosts indeed just act on time, so time is changed, b is the boost parameters, and xi is unchanged under these boosts. And indeed, the vector field lies in the kernel of this metric here. All right, so why do we care about Carroll symmetries? The C to 0 limit seems a bit bizarre. I mean, we are well adapted to the Galilean limit because this is our everyday experience, but the Carolian limit is very far removed from everyday experience. So let's consider, to answer this question, Carroll conformal killing equations. So we act with some vector field on the metric. We get some conformal factor lambda with a relative factor 2 times the metric, and we act with the same vector field xi on this vector field in the kernel, v mu, and we get minus lambda times v mu. And when you solve this and you take into account that this metric is degenerate, you find this infinite set of Carroll conformal killing vectors. And the key observation is that this function t is unrestricted. So it's an arbitrary function of the spatial coordinates. So that means, as opposed to the Lorentzian case where you only have finitely many conformal killing vectors, here you have infinitely many. The best known special cases are when t is constant, then this just generates time translations. When it's linear, it generates Carroll boosts. And when it's quadratic, it generates temporal special conformal transformations. But you really have an infinite tower of so-called super translations. So these are just space-dependent time translations. The remaining part you're familiar with from standard conformal field theories. So the yi, they generate the spatial translations, rotations, dilatations, and spatial special conformal transformations. So there's no change as compared to Lorentzian CFDs. So to sum up, the Carroll conformal algebra in these spacetime dimensions is generated by this infinite tower of super translations and these additional transformations that you know from standard Lorentzian conformal field theories. And the key observation is now that the Carroll conformal algebra in d dimensions is isomorphic to the BMS algebra in one dimension higher. And this algebra, the BMS dimension, is in turn the asymptotic symmetry algebra of asymptotically flat spacetimes. So, for instance, the metric on Scribe Plus is intrinsically Carolian because as r goes to infinity, this factor here goes to 0. So this is like the boundary speed of light, if you want, and you get this 0 times du squared. So you have a Carolian structure induced at Scribe. So therefore, the answer to this question, why we care about Carroll symmetries, and in particular Carroll conformal symmetries, is because they are relevant for flat space holography, and it's suggestive, given this isomorphism, to conjecture that the dual quantum field theory, if it exists, is a Carolian conformal field theory in one lower dimension in the context of asymptotically flat gravity. So if that works, then instead of ADS d plus 1 CFTD, we would have a flat d plus 1 Carolian CFD D correspondence. And that provides one of the key motivations why there's this increased interest in Carolian field theories and Carroll symmetries. Apart from this holographic motivation, there are additional motivations which I'll not elaborate on, but if you want to get a summary of them, I recommend you read this review by Arjun Aritra and collaborators, the Carolean kaleidoscope review from this year. I just highlight one application. So Carolean symmetries are intimately related to null hypersurfaces. So whenever you have a null hypersurface, you automatically get Carolean symmetries. And there are many applications in gravity where, or more generally in physics, where null hypersurfaces appear. Asymptotically flat space is just one of them, but also if you have black hole horizons, then you automatically deal with null hypersurfaces and therefore get Carolean symmetries. Okay, now let me elaborate a bit further on this Caro-conformal algebra. There are different types of Caro-conformal symmetries that you can consider. So let me guide you through this slide here. This is the algebra of Caro-conformal killing vectors in these spatial dimensions, and the part in black is the part that you should be familiar with from standard Lorentzian conformal field theories. And the part in red is different, so this involves commutators with the supertranslations. Now, here are some generalizations of this Caro-conformal algebra. One natural generalization is to consider anisotropic dilatation operators, where you have a Lifshitz exponent Z. Of course, you can do this also in the Lorentzian case, but there it's a bit less natural because in the Lorentzian case, there's no asymmetry a priori between space and time. But in the Carolean case, you have from the very beginning an anisotropy between space and time because the time part is the part that has a zero in the signature. So there it's somewhat more natural to allow for anisotropic dilatations with a Lifshitz exponent that is not equal to 1. You can also generalize the yi, so the spatial part of the Caro-conformal killing vectors, by imposing fewer or no restrictions on them. So then you generalize the usual conformal killing vectors to superrotations or to diff S whatever, diff S2 for instance. And the biggest generalization you can envisage that doesn't cover all diffeomorphisms is the so-called Carroll diff algebra, where you allow arbitrary time and space dependence in these generalized supertranslations and only spatial dependence in the spatial part of these vector fields. If you just restrict yourself to the finite Carroll algebra, so to the Carolean analog of the Poincare algebra, and you gauge it, then you get Carroll gravity in much the same way that by gauging the Poincare algebra, you get relativistic gravity. You can add supersymmetry or higher spins to the mix, so there are various extensions of this Carroll conformal algebra. But the one message that I want to convey on this slide, the one commutator that you should remember after this talk, is the first one here. So the key feature of the Carroll algebra is that the Hamiltonian commutes with boosts. And that makes the Carroll algebra very different, not just from the Lorentz algebra or the Poincare algebra, but also from the Galilean algebra. So physically, when you boost the state, you would expect it changes its energy. That's the most sort of natural part of our physical intuition. We know that when we boost any state, we change its energy, regardless of whether this is Lorentzian or Galilean physics. But it's no longer true in the Carolean limit. And this feature is behind many of the physical properties of systems that have Carolean symmetries, like flat bands, soft hair, tensionless strings, etc. The second commutator is also noteworthy, although it's a bit less remarkable because you have this feature already in the Galilean limit. So the boosts commute with each other. That means you don't. Okay, and finally, the Carroll algebra preserves the Carroll structure, not just in terms of conformal killing relations, but as actual killing relations. So these vector fields associated with these operators are all Carroll killing vectors and annihilate both the Carroll metric and the Carroll vector field. All right. Now, since in a large part of my talk I'll be focusing on 1+1 dimensions on the field theory side, let me ask you the question, is there anything special in 1+1 dimensions? We know in the Lorentzian case this is so. So here's the Lorentzian CFD2. There we have infinite symmetries with the the Virasoro-centric charges C plus, C minus, and in the holographic context, they're just given by the Brown-Eno result, 3L over 2G. And when you linearly combine the Virasoro generators, curly L plus and L minus in this way here, and rescale their sum by 1 over L, and then do an Univinger contraction where you send the ADS radius L to infinity, then you end up with the Carroll conformal algebra in 2 dimensions, including its central extension. So there are 2 central extensions. One is just the usual Virasoro central extension, CL, and the other is this BMS central extension in this mixed commutator between super rotation and super translations, and the super translations, of course, mutually commute. Now, if you start with a plain vanilla CFD, like a minimal model CFD, and you do this contraction, then both CL and CM will vanish. CL will vanish because, well, for plain vanilla CFDs, you don't have a gradation anomaly, so C plus is equal to C minus, therefore the difference vanishes. And if C plus and C minus are finite, then the limiting result for CM is always going to be 0. So the only way you get something non-zero if you take a limit from some CFD or some family of CFDs is if in this family the central charge scales to infinity as you take the limit L to infinity. And this is exactly what happens for holographic CFDs. So this factor L in the Brown-Eno central charge gets cancelled by this 1 over L, and you end up with a finite result for the central charge CM. And if you're worried that this result is dimensionful here, it's 3 over G Newton, well, it's a valid worry. I mean, it is dimensionful, but that doesn't mean there's no meaning to this central charge. So it turns out that in physical observables that we care about, this central charge Cm always appears as a ratio with another quantity of the same dimension, like with the Hm weight of some state. And in that case, there's a meaning to this ratio. So there's still a meaning to the central charge being small or large as compared to other quantities of the same dimension. All right. Now, before I move on to the main statement about flat space holography, let me give you one slide on aspects of Carolean field theories. So the premise of this slide is, of course, that it's worthwhile to explore Carolean quantum field theories and CFDs in the first place. Let's start with what Schwinger labeled as the most fundamental equation of relativistic quantum field theory, namely the Poisson brackets or commutation relation between energy densities at different spatial points. So they're given by derivative of the delta function times momentum density. So that was already found by Dirac in the early 60s. And the Carolean analog of this commutation relation is much simpler. It says that the result is 0 on the right-hand side. And that must hold for Carolean quantum field theories. So if you do some Carolean quantum field theory model building, that's always a commutation relation you can check. Another aspect is this magnetic versus electric limit. Now I should say that you can also consider Carolean quantum field theories intrinsically, so you don't have to consider them as a limit. And probably not all Carolean quantum field theories emerge as a limit from a relativistic one. But if you want to make a limit, you always have two possible choices, and they're labeled electric and magnetic because of their role in electromagnetism, but I show it here for the free scalar field example. So if you start with the Hamiltonian Klein-Gordon action in the Hamiltonian formulation and you set the speed of light to 0, then you directly get the magnetic limit, where pi no longer is then the momentum, but the Lagrange multiplier for the constraint that says that phi has to be time independent. So you get very simple, somewhat boring equations of motion in this case. And the electric limit you can obtain in a similar way by first rescaling the momentum and inversely rescaling the scalar field by a factor of the speed of light. So that pushes this factor c squared to the last term, and when you set c to 0, you end up with an action that is still quadratic in the momentum, so you can still integrate it out and get this simple electric action dt phi tilde squared, and again with very simple, almost boring equation of motion. Now, in neither of these cases you have wave propagation, and there's no finite propagation speed. And to go around this, you have to consider interactions. So in this work with Marquinot, we considered this case of derivative interactions where you can find Carolean invariant interacting fields that lead to excitations with a finite propagation speed. We called them Swiftons. That's the English word for tachyon. And we didn't want to call them tachyons because they are not unbounded from below when you look at the energies. Okay, so what is the technical key issue in this construction? When you have this inverse metric under quotation mark, because, well, there's no real inverse because the metric is degenerate, you can still construct a quantity with upper indices, but this quantity is not Carroll boost invariant. So when you write down actions that involve this metric with upper indices, you are not getting in general a Carroll boost invariant action, so this is not going to be a Carroll quantum field theory in general. So you cannot just raise spatial indices at will unless you impose some suitable constraint. And we just saw an example in the magnetic Carroll scalar field case. There is such a constraint, limit dt phi equal to 0, that saves Carroll boost invariance. And there's a more general way to make this work. So if you have a covector theta mu that is transversed to the Carroll vector, so the contraction of the Carroll vector vanishes, then this quantity theta nu contracted with g mu nu is actually Carroll boost invariant. So even though g mu nu by itself is not Carroll boost invariant, this contraction is. So that means if you take a derivative interaction term of this form with two scalar fields, d mu phi, d nu chi, antisymmetrized and contracted with this vector field, then this quantity is orthogonal to the vector field. So it obeys this relation, and you can use theta squared as an interaction term. So the simplest Swifton action is this one, where you have an electric kinetic term for both scalar fields, and this higher derivative interaction term that is still quadratic in time derivatives, that is sort of electromagnetic with some coupling constant g. And you can show that, first of all, the energy density is compatible with the Carroll condition, so this commutator is 0. The energy is bounded from below. And you can find a solitonic background where chi is t and phi is 0. And when you consider linearized fluctuations around this background, you find that they propagate with a finite speed if this coupling constant is negative. Okay, so let me finish the slide by saying that there are various no-goes, or at least apparent no-goes for Carroll field theories. The oldest one is that there's no propagation in Carroll quantum field theories. That's what gave them their name. But we just saw a counterexample, so Swifton circumvent this. So if you work a bit harder, then you can avoid this no-go result. Similarly, there were some no-go results regarding the absence of Carroll thermodynamics. There's no obvious thermodynamics in the Carrollian limit. Nevertheless, it turns out if you are careful about how you take the limit, there is some version of Carroll thermodynamics, which I'll show you in the last part of the slide, of the talk. And okay, then there are additional more recent statements, like there's no obvious interacting Carroll quantum field theory. And very recent from last Friday, there's no holographic local Carroll conformal field theory. And these are serious concerns, and well, they should be addressed in the future. Let me show you one simple example what can go wrong with taking a C to 0 limit in thermodynamics. Let's just consider the Schwarzschild black hole and naively take the C to 0 limit, keeping fixed the energy. In that limit, obviously, none of these quantities make sense. The temperature goes to 0, the entropy to infinity, and the horizon radius also to infinity. So to make this work, you just have to do a multi-scaling limit where you not only send C to 0, but you keep fixed this magnetic coupling combination C to the 4 over G Newton, and also H bar times C. So in this compactified Bronstein cube, what this limit uses, if you want to keep finite the temperature, the entropy, and the horizon radius, is that you are pushed into this corner that we call tantum gravity, where the speed of light goes to 0, H bar goes to infinity, and Newton's constant goes to 0 as well. Okay, so that concludes the review part of my talk, and now I want to come to the main statement about the flat space Carroll CFT correspondence. So the main statement is based on this fact: the Carroll-conformal algebra in d dimension is isomorphic to the BMS algebra in one higher dimension. And the conjecture based on this fact is that Carolean CFT in d dimensions could be the field theory due to asymptotically flat gravity in d+1 dimensions. Okay, and of course, people have thought about flat space holography from the early days of ADS-CFT. I think the first instance that I'm aware of, at least, was Wittenstock and Strings 98. But the realization that the dual field theory, if it exists, could be a Carolean conformal field theory is younger than that. So this is basically from the last decade. And, well, we can test this conjecture by calculating physical observables on both sides of the correspondence, like correlation functions, thermal entropy, and thermal entropy. And in the remainder of my talk, I'm going to focus on 3 bulk dimensions, and Arjun is going to address 4 dimensions in his talk after mine. Okay, so let me now move on to the flat 3 CCFT2 correspondence, and I'll show you a selected check that is based on symmetries. Namely, I want to focus on stress tensor correlation functions, starting with the field theory side. So if you look at the Fourier modes of the Carolean conformal field theory stress tensor on the cylinder, they're given by these expressions m and n. M is associated with the super translations, Cm is this BMS central charge, Ln are the super rotations, and Cl is the Virasoro central charge. And the Carroll conservation equations are given here. So m is u independent. You can think of u as the Carroll time or as the retarded time in a holographic context, the null time on the light cone. And dun is d phi m. So this is the Carolean analog of this CFT conservation equations that lead to holomorphic and anti-holomorphic conservation equations of the flux components of the stress tensor. Now, if you check the 2-point functions for a Carolean CFT on the cylinder, this is what you find. The 2-point function between these super translation operators vanishes. The one between one super translation and one super rotation gives something that on the right-hand side looks like a CFT result. So you get the central charge divided by 2 times s to the 4. So on the plane, this would just be c to the 4. And on the cylinder, this Sij is given by 2 sine of phi I minus phi j over 2. And the most complicated one is the one between these super rotation generators. So N1 and 2 has 2 terms, one that depends on the Virasoro central charge and another one that depends on the BMS central charge and this quantity tau that is linear in the retarded time difference. And these 2-point functions, like in a relativistic CFT, are entirely fixed by symmetries and by the values of the central charges. Similarly, all 3-point functions here are determined uniquely by the CCFT2 symmetries. So here we're in the magnetic sector. The 4 and higher endpoint functions are not universal. So for instance, the 4-point function with 1 super translation and 3 super rotation insertions is given by this expression where this function G4 depends on these conformal cross ratios and takes this specific form. But of course, this non-universal function is determined if I give you the operators that I'm inserting here, so we can just calculate what this is for these stress tensor correlators. And in fact, you don't have to calculate the higher endpoint functions. You can derive them recursively through Belavin-Polyakov Samologikov type of recursion relations. So the endpoint function involving 2 super translation insertions or more always vanishes. The endpoint function with 1 super translation and n-1 super rotations can be recursively determined from a corresponding one with 1 fewer insertion. And the endpoint function with just super rotation insertions for Cm not equal to 0 is given by the first line here. So if you can calculate these ones, and we know them for the 2-point function, we can construct all the higher endpoint functions recursively. And in the case Cm equal to 0, you're back to a Carroll half of a CFT, so there's nothing new in that case. Okay, how do we do the same calculation on the gravity side? Most conveniently, we use the Chern-Simons formulation. So you formulate 3D gravity in flat space as Chern-Simons with an ISO 2,1 connection A, and you impose this holographic kind of gauge. So people working in 3D gravity for sure have seen this. So you split this connection into a group element B that depends on the radial coordinate, but is state independent, and into a boundary connection small a that depends only on the boundary coordinates, the null time u and the angular coordinate phi. And that can be expanded in this highest weight gauge such that the highest weight components m plus L plus are state independent, and the lowest weight components contain state dependent functions m and n. And you can check that the Einstein equations impose these on-shell constraints that you recognize as the Caro-conformal word identities dum equal to 0 and dun is d phi m. Now, to calculate the two-point functions holographically, we have to add sources. So we include chemical potentials as sources. So that means we shift the u component by these chemical potential terms in the highest weight component, and these other components are then automatically determined on shell. And then we localize the sources at insertion points of the endpoint function. So to show you how this works in the CFT2 case, we get the two-point correlators from one-point functions in a deformed CFT with a source. So this is the deformed CFT, this is the original CFT, and this is the source term that we add. T is the holomorphic flux component of the stress tensor, and mu the source. And we localize the source at some insertion point and have a bookkeeping parameter epsilon, and we linearize in epsilon. So the one-point function in this deformed CFT is then expands as the one-point function in the original CFT plus epsilon times the two-point function. So taking the linear order in epsilon gives you the two-point function. And you can do the same in the flat space case. So for a single localized source, in this way, we precisely recover the Carolean CFT2 two-point functions. I'm just displaying the results here, but I'm not going through them. The end result is that the gravity calculation agrees with the field theory calculation. Moreover, by complete induction, you can show that localizing n times instead of n minus 1 times yields precisely the BPZ type of recursion relations. So this proves that all the endpoint functions on the gravity side correspond with all the endpoint functions on the field theory side. So this is a basic consistency check that 3D flat space holography has a chance to work. It doesn't tell you what the dual field theory is, of course, but it tells you that if it exists, then at least the stress tensor correlation functions automatically come out right. Okay, so let me conclude this part by mentioning some earlier checks. So here are some additional entries in the flat space holographic dictionary. The first check was, of course, that the symmetries in the linearized spectrum match. That's not just true for Einstein gravity, but also for more general theories like topological massive gravity, where you have a gravitational anomaly. So in that case, you have non-vanishing CL and CM, and CL is then determined by the gravitational Chern-Simons coupling. The thermal states, they show a characteristic Carolean flatband structure. So if you take the state space of 3D ADS gravity, so the state of BTZ black holes, I'm focusing here on zero-mode solutions, so no Vero solar excitations. So this is the state space of BTZ black holes. Here on the red line, you have extremal black holes. And if you take the Carolean limit, then this light cone in state space opens up, and you get this flat band structure with this characteristic Penrose diagram of these flat space cosmologies. I'm going to mention them again in more detail in the final part of my talk. There's also some cardiology you can do. So that's based on the Caro-conformal algebra and Carolean modular transformations, which I'll also show you in a few minutes in the last part of my talk. And the result of this is if you insert the values for the L0 eigenvalue and the M0 eigenvalue associated with these flat space cosmologies, you recover this result in terms of angular momentum and mass. And this is exactly the Bekenstein-Hawking entropy associated with these flat space cosmologies. So the microscopic calculation of the entropy on the field theory side matches precisely the macroscopic one. You can also do Caro thermodynamics and find there's a Hawking page-like phase transition between flat space cosmologies and hot flat space. You can calculate Carolean entanglement entropy and its holographic version and find that they match. And the question that I want to address in the remainder of my talk is there a Schwarzian sector in every holographic Carolean conformal field theory in two dimension? And this question is motivated by the CFT2 counterpart that was answered, well, first posed and then answered by Ghosh, Maxfield, and Toriachi 6 years ago. And we address it in this recent work with Ankit, Arjun, Stefan, and Joan. Okay, so before I start this last part, maybe I should pause here because I conveyed already a lot of information. So if there are any questions on the review part or on the holographic part, feel free to ask. Yeah.
So, hello. I have some questions from the review part.
Yes.
Carroll symmetry. So, my first question is this when you gauge it, when you look for Carroll gravity, is it an off-shell or a non-shell algebra, the Carroll algebra?
So the Carroll algebra, so I mean, it's essentially the same situation as in the Poincare case. So you have the analog of local Lorentz boosts would be the Carroll boosts. And the analog of the Poincare translations are local translations. So this is the part associated with diffeomorphisms. And as usual, when you do the transition from the sort of Cartan formulation to a second order formulation, the gauge symmetries associated with your Cartan formulation involve some equation of motion term to map diffeomorphisms to your gauge symmetries. I'm not sure if that's what you were asking about.
Yeah, because in Poincare gravity also you have, suppose you have conformal gravity, you gauge fix the conformal symmetry. So that's an off-shell representation of the gravity, and you gauge fix it and you get Poincare gravity. So I was thinking similar things is happening here also or not, because you can add auxiliary fields to the algebra and you can make it an off-shell algebra. So it closes without the equations of motion. So while constructing gravity theories, can such things can be used here, or is it already used? That was my.
So I would say the situation is completely analogous to the Poincare case. But I mean, you mentioned conformal gravity. So here I'm not talking about conformal Carroll gravity. It's just plain vanilla Carroll gravity.
Okay.
So you just have diffeomorphisms and local Carroll boosts. The main difference, I would say, between the Carroll and the Poincare versions of gravity is that in the Poincare case, there's sort of a preferred way of fixing the connection, namely the Levi-Civita connection, which you can achieve by imposing the usual non-metricity and
constraints on
torsion constraint. And that's not possible in the Carolean case. There's always an irreducible part of torsion called intrinsic torsion that is independent of the connection that you cannot remove. And there's always an free part as part of the connection that you cannot fix by imposing some torsion constraints. So that, I would say, is the main difference. But other than that, the situation is completely analogous between Poincare and the Carroll case.
Okay. Thank you.
Sure.
Hello.
Yes.
Yeah, maybe. Should I go to? Okay. Yeah. So normally in 3 dimensions, if you have a massive particle in gravity, it changes the asymptotic structure of space-time, right? Whereas long-range gravitational field. Is that a problem for this case?
So if you have a massive particle in 3D gravity, that just generates a conical defect.
Yeah.
Yes. Yes.
So.
But I mean that's already true in ADS, of course. So the situation is not different between flat space and ADS. So you have in the state space you have the same kind of gap here between global flat space and the first excited state that has no conical defects. And in this region in between, you have your particle state. So you have conical defects. That's the same situation as here. You have global ADS, then you have a gap. And here you have the state space with states that don't have conical defects, and the conical defects or particles would be in between here. So, but the particles would not give you a long-range Newtonian kind of force. So there's no log R potential that you get in 3D gravity.
Yeah, that's if they have no charge, that's true. But if they have charge, then it can have logarithmic growth.
Okay, you mean electric charge?
Yeah, electric charge. Yeah.
Okay, sure, that's true. Yes.
And I mean, is that a problem for Carolean gravity, or meaning of this holographic dual description?
You mean to include electromagnetic fields?
Yeah.
Oh.
And charged particles.
That's a fair question. I don't know the answer because we haven't considered what happens when you add electromagnetism to the mix. It would definitely be interesting to do so because that's the only way that's the simplest way how you can get radiation at Scry. So far the checks in 2+1 dimensions were focused on understanding these aspects of these flat space cosmologies and the entropy, and not so much on scattering of massless states. So it's in that sense complementary to the program, to the celestial program in 4D, where the focus is mostly on scattering states. But in principle, you should be able to do this by adding electromagnetism. And I'm not sure what's going to happen to the dual Carolean conformal field theory. My expectation is that you need both electric and magnetic sectors to cover this case, because at least in 4 dimensions, we know that the scattering amplitudes are not captured by magnetic correlation functions, but by electric correlation functions. So there you need electric aspects or electric Carolean field theories. But to cover these flat space cosmologies, we need magnetic Carol field theories. So presumably, if you want to have a full holographic description of a system that has both scattering of massless states and these states with horizons, you would need a Carolean field theory that has both magnetic and electric sectors. But this hasn't been studied in detail yet.
Thank
you. I have a question about monotonicity theorems. Is there a notion of some sort of monotonicity theorems for the Carolean central charges? Here.
Here. You mean something like a C theorem?
Exactly.
Yeah, possibly. I mean, I looked at this with one of my former students, with Max Riegler, and we found this flat space analog of domain walls. And based on this domain walls, there's at least a holographic C function where you can prove monotonicity, provided the the null energy condition in the bulk holds. Yeah, on the field theory side, we don't have an analog of the summologic of C function. And also the Cassini-Huerta C function, that did not quite work out. So this is still an open issue if there's a sort of non-holographic C function in these Carolean CFDs that is not based on this domain wall construction.
But is there a notion of the average null energy condition for the Carolean stress tensor? Can you use that to derive the C theorem, just like
so? I mean, yeah, there is a Carolean version of this quantum null energy condition. So there's a QNEC. There's a limit of QNEC, or 2 limits of QNEC that you can do. One in the case when the Virasoro center charge vanishes, which is the case of relevance for the gravity application, and one when the EMS center charge vanishes. And in both cases, you find there's a convexity condition. So there's an analog of this QNEC. Yes.
Thanks.
Okay, so maybe we can wait for the talk to be finished and then, because we are already in the. Okay, please.
Okay. Yeah. Okay, so then let me come to the final part, the universal sectors of Carolean CFD2 and Carolean partition function. So since I'm from Vienna, I have to show you this grave of Ludwig Boltzmann. You can visit it if you're in Vienna. I've been there twice in the past 6 weeks. So I'm not sure if you can read it, but this is the entropy is K Boltzmann times log of W on his tombstone. So, okay, let's consider torus partition functions, thermodynamics and universal sectors first in CFD2. So we look at this grand canonical partition function depending on the inverse temperature beta and this angular potential or angular velocity theta. you get the grand canonical entropy in the usual way, and by double Legendre transforming, you get the microcanonical entropy in terms of this degeneracy of states, depending on energy and angular momentum. And it's very convenient to rewrite this in terms of modular parameters. So tau is just up to some factor 2 pi, theta plus I beta, and if theta and beta are both real, then tau bar is the complex conjugate. And you can write the partition function in terms of these modular parameters, and these zero modes L0 and L0 bar, whose linear combinations give you back the energy and angular momentum. And in some cases, you can write the partition function in terms of a single character, in particular the vacuum character. More generally, you can write it in terms of Virasoro characters, but the vacuum character is going to play a special role, so that's why I displayed here. And the quantity eta is the Dedekind eta function. So if you've never seen it, this function is well defined on the complex upper half plane. And modular transformations act as follows on the modular parameters. So tau goes to a tau plus b over c tau plus d, where a, b, c, d are integers subject to this determinant condition. And we are particularly interested in this S transformation, where tau goes over to minus 1 over tau. Now, modular invariance of the partition function implies that set of tau and tau bar is set of minus 1 over tau, 1 over tau bar. And the reason why it is useful is because it allows you to map the low temperature to the high temperature partition function and vice versa. So this is how you can get the universal Cardis sector of a CFT2. You're interested in the limit beta to 0, which means large temperature. But then you map it by this S transformation to this partition function depending on 4 pi squared over beta. So that means you basically project the partition function to the vacuum partition function, and that in turn is expressible in terms of the vacuum character, and you can evaluate it, and you just get the simple result here for the partition function and the free energy. So this is essentially Cardis result. Now, by contrast, the universal Schwarzian sector, uncovered in this paper by Ghosh, Maxwell, and Toriachi, takes a different limit. So you take this combination beta minus I theta to infinity, so meaning it's no longer possible that both beta and theta are real. And also beta plus I theta goes to 0. Now, the gravity interpretation of this limit is that you go towards extremality. So you have very large, but the extreme will be the Z black hole. So one of the temperatures, say the left moving goes to 0 and the right moving goes to infinity in this limit. And they found that in this limit, again, you have vacuum dominance. So the partition function is dominated by the vacuum character in the dual channel. And our goal is now to investigate universal sectors where the partition function after some S transformation is dominated by the vacuum character, and to investigate this for Carolean conformal field theories in 2 dimensions to see if there's again a Schwarzian sector. So the task list for the last 50 minutes is, well, first I have to tell you how does a Carroll partition function look like, what are Carroll modular transformations, what are Carroll characters, what are the conditions for Carolean vacuum dominance in the dual channel, and then finally identify the universal sectors in this Carolean CFT2. Also discuss the field theory properties, and last but not least, provide the gravity interpretation using flat space holography of these Schwarzian sectors. Well, okay, and in the rest of my talk, I will go through all these steps. So this is getting a bit more technical. I apologize for people who are not that much into Carroll physics, but let me move on. So the Carroll conformal algebra is displayed again here. In these vector field representations, the gravity interpretation is that these generate super rotations and these generate super translations. So this is just essentially diffs1. And the zero mode vector fields are then angular momentum and Hamiltonian. And the Carroll CFT2 grand canonical partition function is again depending on 2 chemical potentials, beta C and theta C. And I relabel them as sigma and rho here. And beta C is the inverse Carroll temperature, and this is the angular potential theta C. And up to some factors 2 pi and the factor I, rho and sigma are essentially the same quantities here. So rho is essentially the inverse temperature. Okay, now you can obtain Carroll partition functions by invariant contracting CFT partition functions, by sending the time to epsilon times time and then setting epsilon to 0. You've seen already the contraction in terms of the generators before. And if you apply this to the partition function, in this limit, you end up with this Carolean partition function with Carroll modular parameters, one of which is rescaled in a singular way. So this parameter rho is tau minus tau bar over 2 epsilon in the limit epsilon to 0, and sigma is tau plus tau bar divided by 2. As a consequence of this factor epsilon, there's something subtle going on with the temperature, namely, if you keep finite the original temperature in the CFT, you inevitably end up with a singular temperature in the Carroll limit, so it goes to infinity. So that's not what you should do if you want to have a Carolean system at finite temperature. So if you want to obtain a Carolean system with finite beta c as a limit from a relativistic one, then this beta has to be singular. So beta basically has to go to 0 in the original CFT, meaning that the temperature has to go to infinity in the original CFT. And nothing spectacular happens for the other chemical potential. That just goes along for the ride. Okay, so you can do this in an invariant contraction also on the modular parameter. And if you do this, then you get this Carroll modular transformation. Sigma behaves in an expected way, so just like a plain vanilla modular parameter, but rho doesn't. Rho instead transforms like a modular vector, so it transforms into rho over c sigma plus d squared, and a, b, c, d are subject to the same conditions as before. So the geometric interpretation is that, as I said, sigma transforms like a standard modular parameter, and rho transforms like an element in tangent space of the upper complex half plane. So it's like you're zooming towards the real line from above in the upper complex half plane. As a consequence, the S transformation looks slightly different. So sigma still goes to -1 over sigma, but rho goes to rho over sigma squared. So this is the main change in this Carroll modular transformation. The T transformation is the same, and these braiding identities also hold, but the S transformation has this crucial difference here. Okay, now you can label states by the eigenvalues of L0 and M0. We call them delta and psi. And we are mostly going to use the highest weight representation, where Ln and Mn annihilate states for positive n. But there are also induced representations that are useful in a gravity context, where Mn annihilates states for any n that is not equal to 0. And there's no constraint on the Ln's. Now, for the highest weight representations, Arjun and friends calculated these Carroll characters, and this is the result. So it's again expressed in terms of the Dedekind eta function. And the vacuum character, which we're going to exploit, okay, has this additional factor here, 1 minus e to the 2 pi I sigma squared, but otherwise it's the same structure, and again features the Dedekind eta function. And the Carroll characters for induced representations are identical up to a modulus. Okay, so now you can write the CCFT2 partition function in terms of these Carroll characters. D denotes the density of primaries with corresponding weights, delta and psi. And assuming there's a unique vacuum, D of 0, 0 is 1, we can expand the partition function in terms of the vacuum character and the rest. And the expectation values are just given by the usual derivatives with respect to chemical potentials of the log of the partition function. Now, let's store for later, not much later, only 8 more minutes, that when sigma is real, the Dedekind eta function is actually ill-defined. That's important for one of the sectors. Okay, and now finally, if we apply this Carroll S modular transformation to the Carroll partition function, this is what we get. So we get z of rho over sigma squared minus 1 over sigma, and that expands in this way. And vacuum dominance technically means that the first line in this sum here dominates over the rest. So you can neglect all the terms in the second line. So a necessary condition that has to be obeyed by all highest weight primaries is that this quantity here goes to 0. And you can check under which condition this vacuum dominance in the dual channel is obeyed. And for induced primaries, there's a similar condition just with absolute values. Now, some consequences of the vacuum dominance. First of all and foremost, the partition function projects to the ground state, so you can just evaluate it very easily. And in the same approximation, it turns out that the expectation value of the energy is given by a combination of chemical potentials that is independent of this quantity rho. So that means that the rho of the absolute value of the expectation value of xi vanishes. That's going to be important for the last statement I want to make. By contrast, the angular momentum expectation value is some complicated function that depends on both chemical potentials. And on the next slides, I'm going to analyze the conditions for vacuum dominance. But I think given the time, I just focus on one of the three sectors. So here's again the condition for vacuum dominance. And here is the zoo of possibilities. So essentially, there are three universal sectors plus three special limits thereof. A Cardy sector, where the temperature goes to -infinity. A Schwarzian sector, where the temperature goes to 0 from below. And the Boltzmann sector, that's the only sector where the temperature is positive. And then the additional convexity condition you have to impose. For instance, the energy always has to be bounded from below. Okay, so I'm going to skip the Cardy and the Boltzmann sector. Let me just focus on the Schwarzian sector. So in the Schwarzian sector, beta goes to -infinity, omega goes to 0 from below, in such a way that beta times omega goes to infinity, but beta omega squared goes to 0 from below. And then we have also to obey these convexity conditions. If these conditions are met, then the leading plus next to leading order grand canonical partition function is given by this expression. And if you have seen the Schwarzian partition function, you will recognize it as such. So there's this log correction term with a factor with an exponent 3. And then there's this Schwarzian term here, and there's also a leading order contribution. Now, if you calculate the associated entropy, this is the result you get up to order 1 contributions. And this is a gravity-like form if additionally this quantity, which is essentially the angular momentum, is finite. So then you can write the Schwarzian entropy as the leading order entropy minus 3 times the log of the leading order entropy plus order 1. And this minus 3 has an interpretation as, well, minus 6 over 2. And the 6 refers to the number of generators that are sort of blind to the central charge. So this is the global conformal Carroll algebra. It's the analog of the SL2 plus SL2 subalgebra in the conformal algebra in the relativistic case. Okay, and the energy expectation value tends to 0 in this sector here. Okay, so the last statements I want to make is what is the gravity interpretation of the Schwarzian sector, and then I also want to tell you about specific heat. So let me skip the Boltzmann sector. So the gravity interpretation of the Schwarzian sector is as follows. So if you look at flat space cosmologies from PTZ, this is infinity. So this part here describes formally the outer horizon of PTZ. But you keep fixed the inner horizon. So the horizon in this flat space cosmology corresponds to the inner horizon in BTZ. And that explains why you get negative temperature because of the inner horizon first law. If we're interested in the Schwarzian limit, we have to take a different flat space limit where both the horizon radii of PTZ scale to infinity with the same weight, square root of L. And as a consequence, the charges scale as follows. The mass scales to 0, but the angular momentum remains finite. So that's a very curious limit. And we realized after a while that this was actually already considered more than 2 decades ago in this work by Conalba and Costa. And they realized that this particular orbifold of flat space is the so-called O-plane orbifold. So here's the line element with phi being 2 pi periodic. And this is the Penrose diagram. So this is locally flat and also locally asymptotically flat, but it has naked closed time-like curves. So there's no horizon in these geometries. But this is allowed by the boundary conditions. It's part of the Barnich-Compare phase space. And the horizon entropy, even though there is no horizon, is formally infinite because you can view this as coming from a limit where you have a horizon, but then you push it to scry. So in the limit where the mass goes to 0, this entropy goes to infinity. There's some redundancy. You can do a finite rescaling of R plus and inverse rescaling of R minus. And you can do this in such a way that always R plus set is R minus set. And if you do that, then you can view this O-plane orbifold as a scaling limit of extremal BT set. So the upshot is that the Schwarzian CCFT sector is a Carroll limit of a Schwarzian CFT sector. And on the gravity side, the O-plane orbifold is a flat space limit of extremal BT set. Okay, so how am I doing with time actually? 5 minutes, okay, good. So let me now make the last statement before summarizing, namely this one, Carolian vacuum dominance implies negative specific heat. So if you calculate the specific heat at constant angular momentum, this is generally the result that you get. So it's determined in terms of variances and expectation values. But recall that vacuum dominance implies that d rho of expectation value of psi vanishes. And that in turn is exactly this combination of psi squared minus expectation value of psi squared, so the variance of psi. So that means in the case where we have vacuum dominance, this first term vanishes. And that means specific heat is just given by this expression. And the key observation here is that there's a minus sign and all the other terms are manifestly positive, at least as long as delta and psi are real. Because with beta squared, beta is always real. It may be negative, but it's real. And if these quantities are real, well, the numerator is just the square, and this is a variance which is also positive. So therefore, in the Carding-Schwarzen sector, where delta and psi are real, you can prove on using this inequality that the specific heat has to be negative. And it turns out that also in the Boltzmann sector, where it's not true that both delta and psi are real, it still happens to be that the specific heat is negative. You can show this by explicit calculation. So the conclusion of this is that Carolian vacuum dominance implies negative specific heat. And if a statement like this is true in high dimensions, this would provide a field theoretic explanation of the negative specific heat that we observe in asymptotically flat spacetimes with horizons. So it's well known that Schwarzschild or Kerr black holes have negative specific heat, and also the flat space cosmologies do. And this inequality provides the field theoretic explanation for the flat space cosmologies of why this happens. Okay, so let me sum up and contrast the Schwarzian sectors in ADS3 CFT2 and in flat 3 CCFT2. So the chemical potentials both take singular limits. In the ADS CFT case, beta minus I theta goes to infinity and beta plus I theta to 0. In the flat space case, beta goes to minus infinity and I theta to minus infinity as well. In the ADS CFT case, the mass goes to infinity, but m minus j goes to 0 from above. In the flat space case, m goes to 0 from above and j is arbitrary. The Schwarzian partition function in ADS3 CFT2 takes this form here, so it is the Schwarzian partition function. And in the flat space case, up to some additional square, so instead of 3/2, we have 3. It's essentially the same expression here. And holographically, what happens is that you zoom into this region here of the state space. So the Schwarzian limit is you move up here towards extremality and towards large masses. And you can already picture what happens if you take the flat space limit and the light cone opens up. So this black arrow goes down here, and that is indeed what happens here. So, and in that limit where m goes to 0 from above and angular momentum remains finite, you get this O-plane orbifold. Okay, so let me conclude with some takeaway lessons. The first one, I guess, is that Carroll symmetries are more ubiquitous than anticipated in the 1960s. Here's some INSPIRE evidence for this. I just want to highlight this fact here that, I searched for publication with Carroll in the title, but not with Chakiev, because there are many Carroll field Chakiev papers otherwise. And you see that I searched from 95 on, so the past 3 decades. Before the millennium, there was no such publication, and in the first decade of the millennium, almost nothing. And now there was, in the past 5 years, some exponential increase. The reason for this is that Carroll field theories are less trivial than thought originally. Here again, the main features. Boosts do not change the energy. The signature of Carolian spacetimes has a singular 0 here. And the Dirac-Schwinger relation in the Carolian case is that energy densities commute at different points. And the main rationale for the Carroll approach to flat space holography is that you have an infinite set of symmetries that match precisely. The Carolian conformal field theories in D dimensions have precisely the BMS D+1 symmetries that constitute the asymptotic symmetries of asymptotically flat spacetimes. Is there really a flat space D+1 CCFT-D correspondence? We don't know. We think there is, we hope there is, but clearly there needs to be done more work. So also, I think it's fair to ask, is a flat space holographic correspondence more useful than an S-matrix approach to physics in flat space? When it just comes to scattering of massless states, I'm not sure the answer is yes. But when it comes to states with horizons like black holes or flat space cosmologies, I think the answer is yes, because otherwise it's hard to understand things like the entropy and give a microscopic description of the entropy. In 2 dimensions, the checks so far are based mostly on symmetries. Can we do more? And for 3 dimensions, I refer to Arjun's talk. In 3D, this correspondence has passed numerous checks, but again, these checks are essentially based on symmetry, so it would be nice to do more than this. Okay, so to conclude, let me stop with a question. Are we on the right track with Carolian flat space holography? The honest answer is I don't know, but if we are, then it's, I think, in no small part due to the Indian strings community and specifically to Arjun's work. So I'll stop here and thank you.
Questions?
I have a generic question. Is there any construction of Carolian field theory from lattice field theory or non-statistical model whose critical point corresponds to Carolian CFT?
Yes, so besides the free theories that are kind of trivial, so there is the Carroll analog of the Ising model that you can construct.
Oh.
But yeah, so that was constructed independently by 2 groups. And that's an explicit model, but it's of course not going to be useful for holography because it's very far from the kind of models we would need for holography. There is no microscopic model for Carolian CFT that also has holographic features. There is an intermediate level formulation of such a theory, namely a Carolian analog of Liouville theory. So Glenn Barnich, together with Andy Gomarov and Hernan Gonzalez, they constructed more than a decade ago a boundary action associated with flat space gravity. And that boundary action you can interpret as a field theory living on this 1 + 1 dimensional boundary. And it is a Liouville type of action, and it has the right central charges. So it has in particular, a vanishing Virasoro central charge and a non-vanishing BMS central charge, which is in contrast to the Ising model, to the Carroll Ising model that I mentioned. That has a non-vanishing Virasoro central charge, namely 1, but a vanishing BMS central charge. So yeah, the short answer is we don't have a microscopic model for a holographic Carolian CFT that could be dual to flat space Einstein gravity.
Oh, okay, thanks, sir.
Yeah.
Hi. I didn't understand the last part very clearly, but did you, in the end, have a prediction for a finite entropy for the density of states in a 3-dimensional flat space?
So it depends on the context. I mean, the Schwarzian limit, we didn't because the entropy formally tended to infinity if we took this Schwarzian limit. I mean, but the same is true in the ADS CFT case, right? It's just because you scale your state parameters, mass and momentum, in such a way that the entropy diverges in that limit, just because the black hole is very large in the case of EDSCFT, and in the flat space case, because the entropy scales inversely to the square root of the mass, and if you send the mass to 0 from above, then this goes to infinity. So
sorry, so do you get a prediction? Do you get a prediction for gravitational thermodynamics in flat space in the end?
yes.
So could you say what is the prediction? I mean, in any limit, what entropy as a function of energy and angular momentum, is there a formula?
Well, yes, this is the formula. Maybe if I show you the Cardi sector, it's a bit, well, here I've shown you the formula as well. So this is the leading order entropy, this is the log correction, and the leading order entropy is determined in terms of this BMS central charge and this chemical potentials.
So is that a finite expression in the end?
This expression here is infinite, because beta omega squared goes to 0. So it's a very large entropy. It's, yeah.
Is there a finite amount per unit volume? So I'm looking for something well-defined.
In that limit, it's infinite. Yeah.
So is there a prediction for anything finite at some point? Or could you give me one finite, one prediction that's not infinity? Or if it's infinity?
Yeah. So, well, but I wouldn't claim it's not infinite, because psi tilde also goes to infinity. So this, I mean, okay, depends. If CL is switched on, then this would also be infinite.
So is there something finite per unit volume? I mean, I'm trying to understand the nature of the prediction. If you're getting infinity, I'm not understanding what to make of it.
I mean, but I would say, okay, to me this is not so different from getting the infinite entropy in the Schwarzian sector in ADS-CFT, right? The reason it's infinite is because the mass is sent to infinity in this case. Yeah, so in this case, if CL is equal to 0, this expression here would be finite, that's true. The first term would be infinite because beta omega goes to 0.
Yeah. So just can you decode that finite answer for me? Entropy as a function of energy.
4 pi squared Cm over beta omega squared.
So
this is the Cardi entropy, 4 pi squared Cm over beta omega squared. Beta omega squared here is arbitrary, so it can be finite.
So this is the final prediction for some flat space theory as a function of beta and omega?
Yes.
In some limit?
Yes, yes, in the Cardi limit. So that's the limit when there's a horizon and the inverse temperature goes to 0 from below, so temperature goes to minus infinity.
Is there a volume of space-time in this answer? I'm asking because I would have expected that just a gas in space would have extensive entropy and have a volume of space-time.
Yes. Sorry, I don't hear very well. Can you use the microphone?
What is the physical interpretation of this finite answer? You have some space-time with a horizon?
Yes. So
is it supposed to correspond to the area of the horizon?
Yes, it is the area of the horizon. That's precisely what it is. So in this,
can you explain the space-time once more?
So this is the space-time whose area this formula is computing. So this is the flat space cosmology. It's an orbifold of flat space, and you can also obtain it as a limit of PTZ when you send the outer horizon to infinity and keep fixed the inner horizon. So the area that appears in the Bekenstein-Hawking formula for the entropy is just the area of this inner horizon, which is given by this quantity r minus, the horizon radius, and this is kept finite in this scaling limit. And they're called flat space cosmologies because they are, well, cosmological spacetimes, you don't have a time-like killing vector, rather you have homogeneity. And the spacetime is regular in this whole region 1 and 2, including the horizon, so it's a valid orbifold of flat space that you should consider as part of your state space. These wiggly lines here correspond to the onset of closed time-like curves. So here you have, closed time-like curves. Yeah, so the area of the dotted line is given by the Bekenstein-Hawking entropy, which in turn is given by the Cardy formula that you can obtain from this Carolean vacuum dominance. That's correct.
Please.
Yeah, here, over here. Yeah. In 2D CFT, if we introduce a continuous internal symmetry, like some Lie algebra symmetry, then if we commute it with Virasoro, we get the Kac-Moody algebra. And if you do the same thing here and commute global symmetry with your Carolean generators, what do you get?
So, I mean, the BMS algebra or the Caro-conformal algebra has a Virasoro subalgebra. That part would be the same, so that U1 current algebra that you would add would have the same commutation relation with the Ls, with the Virasoro generators. And with the M's, presumably you can assume that it just commutes with the super.
No, I think the interesting question would be, for example, let's say we have an SUN symmetry, global SUN. Now we commute it with these generators and we'll get something, right? We get some new infinitely many generators extending the SUN symmetry. So now the question is, what is the algebra between them? That's the analog of Kac-Moody.
Yeah, so, I mean, I don't know, but I would guess it's not different from the CFT case because you can still do a Sugawara construction of I mean, as a contribution to the stress tensor. So, I mean, you get at least one Caro half of what you get in a CFT. You don't get the second Caro half, but given that there's always this Virasoro subalgebra, I think you can do the same type of Sugawara construction, and yeah, Arjun has some comment on that.
Yeah, I'm always trying to butt in. So yes, this is something that we have done, and the guy sitting next to you here, I mean, was also on the project. So there is a structure, like Daniel is saying, and it's a little, I mean, richer than that. You can get more stuff out of it.
Nice. Okay, thanks.
So we have one more question, so please.
Yeah. So we have some known string compactification on 3 dimensions, right? Take the simplest one, type 2 on 7-dimensional torus. So is it possible to systematically construct the CFT dual for that theory? Because you know many things about it, right?
Yeah, so you can compactify on T7 times some orbifold of 3-dimensional flat space. That's what you mean?
No, just the 3-dimensional flat space, or just orbifold times 3-dimensional flat space, and you are trying to see what the Carolean CFT dual of this is.
Yes.
Because we know spectrum, we know S-matrix, we know everything, right, about this, at least perturbatively.
Okay, and you just compactify all the internal dimensions on a T7.
Exactly, yeah.
Yeah, I mean, okay, this was the construction that actually led to the conclusion that there is a O-plane orbifold, or that this geometry has an interpretation as an O-plane orbifold. That came from considering string compactification on T7 times this orbifold. But you're asking about the field theory side.
Yeah, I'm thinking of T7 times flat space, flat 3-dimensional space time.
Yeah, so there's a subtlety, I think, because okay, yeah, I haven't mentioned this. So I think the issue that I see is the following: when you do your CFT construction in the string context, you probably will always impose highest weight conditions, and that's not something you can do in this Schwarzian or Cardy sector. So I haven't mentioned this in my talk, but well, I addressed it a little bit. So you can either choose highest weight or induced representations, and if you obtain the Carolean CFT as a limit from a Lorentzian CFT, it turns out to get the highest weight representations in the Caro CFT, you have to start with flipped representations in the parent Lorentzian CFT. By flipped, I mean that you impose highest weight condition in, say, the left moving sector, but lowest weight conditions in the right moving sector. If you start instead with highest weight conditions in both sectors, as you would usually do in, I think, any string construction I know, you end up not with the highest weight vacuum in the Carolean CFT, but with the induced vacuum. And the issue is that the induced vacuum or the induced representations were not compatible with the Schwarzian or the Cardi sector. They are only compatible with the Boltzmann sector. So specifically this Schwarzian sector, I don't think you can obtain it from a standard string construction. You would somehow have to flip 1 Caro half so that you use lowest weight representations there. And I'm not sure if this was ever done or if anyone considered this, because why would you in a stringy context, right?
But isn't that the claim that every three-dimensional theory of gravity will have a Carolean CFT dual? Is that isn't that expected?
This is expected, yes.
Yeah.
It's
And I'm just saying that this is one particular three-dimensional quantum gravity, right?
Yes.
String theory on T7.
This is the expectation, yes. That's right. That's right.
So it should have some Carolean CFT dual.
Yes, I agree. Well, I hope it's true.
Okay.
Okay.
Yes.
So
Yeah, I think this question will go to Arjun also. I mean, replace T7 by T6 and answer this.
Yeah, but again, I see this technical issue that with lowest and highest weight representation, that's not what you usually start with in your string construction. So, and I'm not sure what it means if you flip the signs in 1 Caro sector. If you can just do this without any issues.
okay, so let us thank Daniel again for the very nice talk and very nice interaction session. So, yeah. Okay. Next speaker is Siddharth. I think there is some change in the schedule, so I was just told.
It's not Arjun?
So Arjun will speak after. So it was very picosecond below, before this update was there. So Arjun, I've just asked him to.
This should be fine.
Okay, so our next speaker is Siddharth. He is going to talk about conformal representation of flat space correlators. So let's listen to him.
Hello, everybody. Thanks to the organizers for putting up this wonderful conference, especially to Shamik for offering me this slot and to Arjun for agreeing for the swap at short notice. So today I'd be talking about flat space correlators. So I'd just be doing QFT in flat space. I would like to tell you that there is something interesting if you look at QFT in flat space by looking at its conformal representation. And in particular, there is a way in which you can get all flat space correlators in QFTs by just having cubic interactions. And that's what I refer to as the cubic expansion. So usually, of course, when we do QFTs in flat space, we do it in momentum space. Particularly, let's say when we want to compute the S matrix as a probability, which encodes probability of transitions between asymptotic free states. But let's say for let's say for today we want to understand gravitational physics in some isolated region of our universe. Okay, so I'm thinking of some region which is large enough that it contains lots of interesting objects inside, but it's still small and much smaller than the size of the universe, so the curvature of the universe doesn't matter. In that case, we are in this setting of asymptotically flat spacetimes. And so you want to understand, if you want to understand these spacetimes, you might think that there's a useful boundary description for them. And in the 70s, Abhay Ashtekar had this program where he showed us that, in particular, if you look at massless fields, which I'll be doing for this talk, in the far past and the far future, the phase space, if you look at of these fields, you see that there is a Fock space of free fields. Okay, so in some sense, if you look at scattering and asymptotically flat space times, you're looking at transitions between free states in the past to free states in the future. There are some subtleties due to infrared divergences, which I won't get into today. So there are approaches to look at these boundary descriptions of flat space-times. One of them is the Carolean approach, which we heard about yesterday from Mrityunjay and today from Daniel, and we'll be hearing about it again from Arjun. There's also the celestial approach, which we'll hear about from Nishant tomorrow. But today I'll just be thinking about trying to get a boundary description just in position space, in our old regular position space. So you want to do something like we do in ADS, where we have correlators in the bulk of the space-time, and then we take our insertion points out to infinity and see if these kinds of correlators can encode bulk physics for us. I'll start out by doing by just looking at QFT in position space and see what we find for QFTs in position space. So we are taking we're going to start with that today. So in some recent work, we asked whether position space correlators can encode the S matrix, and indeed we found that this to be true in work with Diksha, Shuman, Shiraz, Omkar, and Pushkar. We found that there was a formula for the S matrix in terms of the path integral, which only takes which is only a function of the boundary values of fields, and we are able to show that these boundary correlators somehow encode the S matrix. And one can find constraints on this boundary path integral that come from unitarity in the bulk and so on. So I'll just give you one a small aspect of this work, which is if you look at massless correlators and then you ask how is the S matrix of massless fields encoded in these massless correlators. Your first question might be, if I start off with some fields on the boundary of flat space-time, how do I know that, and I let these guys go into the bulk, how do I know if these guys will scatter at all in the bulk? And for that, we found a very nice answer. If we said if the fields are at these positions x1, x2 to xn, you just have to form this matrix of distances. And if this matrix has determinant 0 and its and the corresponding eigenvector is such that it has all positive entries, then it's true that if you put fields at these points, they will scatter. So for example, if you took the 4-point contact correlator for 5 to the 4th in 4 dimensions, you can see that, so since there are 4 points here, you compute this determinant n, and you see that this determinant n comes out to be proportional to the z minus z bar squared, where the z and z bars are formed from the cross ratios of these 4 points. And so it becomes 0 when z equals z bar. And indeed, if you look at the correlator around this point, z equal to z bar, you see that there is a singularity here. And the residue of that singularity is the S matrix. Okay, so this is some general statement which we think is true for massless correlators in flat space-times. And in particular, for this particular case, we could actually compute the correlator exactly and then first compute it in some Euclidean slice and then take them to the take the insertion points to a configuration where they will scatter, so in the Lorentzian configuration, and then find this result that the correlator around this singularity looks like this. Okay, so yeah. Yeah, so it's just that these are massless fields, so they travel along light-like lines, and they have to meet at some point in the bulk and conserve momentum there. That's all. That's the. Yes, so this is the condition for determinant n being 0. Yeah, that's just the condition that these lines will meet in the bulk and they'll be able to conserve momentum there. But now restated in position space.
But I'm sorry, momentum conservation just follows from transversal invariance, right? So there's one more condition. Is that something?
No. So the point is, let's say you take any 4 points on the boundary. Okay, they might not even meet in the bulk, right? So if they meet, they might meet in a way that momentum might not be conserved. Let's say if you took, for example, a trivial example is all the points were on the far past. then the light-like lines might meet in the bulk, but the momentum will not be conserved there. So you want to see what the configuration, what are the set of configurations which from where if you draw light-like lines, they will meet in the bulk and they will also conserve momentum there. So I'm saying, so in position space, that's the condition that you will get if you ask this question. So so to answer, yeah. Yeah, for now I just looked at contact interactions, exactly. So Shruti is asking if this was just a contact statement, and precisely to answer that question of to take this to higher orders in Feynman diagrams, we want to understand how to compute flat space correlators in position space. Okay, so the rest of my talk will be about just computing flat space correlators in position space, which will let us make these statements for all the kinds of Feynman diagrams that we'll encounter. So that was some motivation for why do we want to do QFT in flat space, and I will in the first part of the talk I'll tell you that there is a conformal representation of these flat space correlators that will allow us to do these calculations, and if you know, boundary descriptions of asymptotically flat spacetimes is not your cup of chai, there is still some usefulness in doing this, and that is because there are some implications for these for this representation for these in the usual Feynman diagrams in momentum space. So there we'll see that you can organize and maybe even compute these Feynman diagrams better if you use this conformal representation. And finally, I'll talk a little bit about there being a basis for these flat space correlators, which you can find by just looking at cubic interactions. So if given any interaction in the theory, you can reduce it to sets of Feynman diagrams which come from cubic interactions. Okay, so this part of the story is in this paper, this Feynman diagrams in momentum space is in that paper, and the cubic expansion is some ongoing work. Okay, so to start off, let's look at contact correlators of massless fields, and they look like this, where you have insertions at points 1 to n, and the idea is that this sort of a correlator that you want to compute, which now you want to do in position space, and indeed there are some kinds of correlators we do compute in position space, which are conformal correlators, and the idea there is because you have all of these extra symmetries, you are able to do it explicitly in position space. So what we are going to try to do is to take this general correlator here and see if we can make it conformal in some way, and then compute it, and then recover our original non-conformal answer as the limit of the conformal answer. Okay, so that's what we're going to try to do. So to do that, let me do a quick comparison of these conformal and non-conformal correlators. So the conformal correlators, as you know, have a structure like this, where there is an overall simple function of these distances, Sij's, which are xi minus xj squares, and there is a non-trivial function sitting here, which are these d functions, which I'll call dCFTs here, which is a function of cross ratios of these points. Whereas our non-conformal correlators will have a similar structure with some simple function of distances sitting outside and this non-trivial d-flat function, which is a function of simple ratios. Okay. So on the left-hand side, these deltas for me will satisfy this additional conformality constraint, and you can show that if you write down a general position space correlator and put this constraint at each vertex, okay, where all the deltas meeting at each vertex will satisfy the sum of the scaling dimensions equals the space-time dimension, which I'll call the conformality constraint, then you can see that the position correlators will transform well under conformal transformations. You can then so this is the comparison between the conformal and non-conformal correlators, and what you can observe is that the number of cross ratios, if you compute for n points on one side and if you compute the number of simple ratios for n points on the other side, you see that the number of n plus 1 point cross ratios equals the number of n point simple ratios. Okay, so you can see from there that n plus 1 point contact conformal correlators have as much information in them as n point flat space correlators. So in fact, something more, even at the level of the full correlator, one can recover the non-conformal correlator from the conformal guy by taking the conformal correlator here on the right side and sending 1 point out to infinity. Okay, then you have to rescale this conformal correlator by this factor here, which is this insertion point of the n plus 1 point, and then you recover the flat space endpoint contact correlator. So this works, for example, if you take the 4-point conformal correlator, you have these two cross ratios. Sorry. Yeah.
I just wanted to ask you, how did you get the constraint on delta?
That's the constraint I put in. So this is the left side I want to calculate.
Yeah.
So on the right side, I'm putting in an extra delta n plus 1. I'm putting in this constraint.
No, the slide before, where you had the table. Yeah, here. Yeah. Why do you, so this conformally constraint that sum over all deltas should be equal to D.
Yeah.
Where do you get that from?
Yeah, exactly. So see, this is the left-hand side that I want to compute.
Yes.
These deltas don't have any relation between them, okay? I introduce an extra delta n plus 1 such that this constraint is satisfied.
Okay.
Okay. So that's the conformal correlator which I will be able to compute.
Right.
Okay. And then I'll recover the left-hand side as the limit of this guy by sending out 1 point out to infinity.
Okay. And is there any way I can fix, let's say, a particular delta, or does that depend on the asymptotics of the field under?
No. So these deltas are given to me. This is the theory I want to compute.
Okay. Okay.
And this is the extra one that is fixed by this constraint.
I see. I see.
Okay.
Okay.
Great. So so if you just take 4 points, you have 2 cross ratios, and if you take 1 point out to infinity, you get 2 simple ratios, and the formula looks like this. You can do this at 5 points, and you can do this at any n points. In fact, for any, not just for the contact correlator, but for any correlator, you can add an extra field at each vertex and take all the fields out to infinity, and the result is that you recover your flat space correlator. So I'm not going to be able to prove that statement today, but I'll just state it. And so what happens then is that you're reduced from computing all these QFT correlators, you are reduced to computing conformal correlators. Okay, and just to set up some notation, these conformal correlators have, as I said, this overall simple function of this distances times this d flat times this d function, and this d function I'll be writing in this Mellin representation. So the Mellin representation looks like this, and the function that is a function just of the Mellin variables I'll call d tilde for, and I'll be able to express flat space correlators as functions of these d tildes. So for example, at 4-point contact, this d tilde looks like a product of 4 gamma functions. The 5-point d tilde looks like a product of 5 gamma functions, and so on. So ultimately, ultimately we'll be expressing our flat space correlators in terms of these d tilde functions. Yes.
Taking one leg at a time to infinity and several legs, and taking to infinity is the same as like a this soft limit factorization, or?
Yeah. So it looks like it should be similar to the to the soft limit in the sense that you're taking positions out to infinity, but I'm not sure exactly. I'm not sure it's exactly the same because it doesn't look like this guy has the soft expansion that momentum space correlators have. So we can discuss this maybe more later, but even I felt that it should be something similar like the soft limit when I first started on this, but it doesn't seem like it quite works. Okay, right. Right. So good. So the point is that these are massless correlators. So to begin with, there is no energy scale, right? So though they don't have the scale invariance of conformal theories, if you look at massless correlators naively and scale all of the x's to lambda x's, the whole correlator will go like lambda to some power. It's not the same power as conformal correlators, but it goes as lambda to some power. Of course, this kind of naive scale invariance is broken when you go to higher correlators. But the idea will be that then what happens is the flat space correlator that you're trying to compute is divergent, but so is the conformal guy that we're trying to compute. So the way of regulating both sides is the same. So in the sense that you can regulate the conformal guy, which I will give you some examples of that in a bit. And from there you can, for example, get the regulated version of the flat space correlators in, let's say, dimensional regularization by doing this sort of procedure.
So is it a feature of just the massless sector, or?
It's a feature of the massless sector, that's right. But the massive correlators also have a conformal representation. I won't talk about that today, but they do have some representation like this, which also might be useful.
Thank you.
Actually, I think we are already competing with Indigo, so please wait for, when we clap, then you ask question, maybe for this one. Thanks for your patience.
Okay, I just gave you a brief view about the conformal representation. So now I'm going to talk a little bit about what this means in momentum space. And so let's look at one loop Feynman diagrams in momentum space. They look like this. Where the incoming momentas are these differences, P1 minus cyclic differences of P1, Pi minus Pi plus 1. And the internal loop momenta is L. And so the internal momentas go like L minus P1, L minus P2, and so on. So you'll see that this one loop diagram, basically if I took my contact diagram with insertions at x1 to xn, just replace the x's with the p's, I'll get this expression here, right? So this is like the dual diagram of the contact diagram. Okay, so all the results I have about position-spaced Feynman diagrams, I can now translate into this language. And what that gives me is that you get what I call conformal families like this. So what this means is that, let's take this guy for example. At one loop, if I wanted to compute a triangle diagram with some number of external fields, so each of these vertices have some number of external fields, it doesn't matter how many, but at least one. And then what you do is, if you want to compute this diagram, this triangle diagram, then you start off with this box diagram where if you look at this expression here, there are these delta i's sitting. And the sum of these delta i's is d in these blue diagrams. So in these blue diagrams, the sum of the delta i's is d. And you can compute this because it goes like these conformal correlators. And then you can recover the triangle diagram from the box diagram by taking one of these Pn plus 1 squares to infinity. So basically, we have to do what we did in position space, and at the end of the day, we replace the x's with the p's, and then we're able to get the momentum space Feynman diagrams out of them. So then you can go on to two loops. At two loops, what happens is you can take either of these blue boxes. You can start off with two blue boxes and take one of them becomes a triangle, and then both of them become triangles. So you get like three diagrams here. You start off by computing this one on the right, and taking limits of this gives you both of those diagrams. Okay, so what is happening is all of these different Feynman diagrams are organizing into families, where I just need to compute one of them, which is the one with all blue lines. And from that, I can recover the others as limits of these kinds of diagrams. Okay, so at 3 loops you get some families like this. At 4 loops you get some other families like that. But let me give you some exact results for some Feynman diagrams which come out of this procedure. Okay, so for example, there are these ladder diagrams in 4 dimensions. So a while ago, these people, David Ichev and Yusukina, they showed that if you looked at massless phi-cube theory in 4 dimensions, then they computed L-loop contributions to the 4-point function, which come from diagrams like this, and to 3-point function, which comes from diagrams like this. And they noticed that there is a relation between these two kinds of diagrams. Okay, so they computed the right side, they computed the left side, and they showed that there is a relation between these two. And for us, this relation comes very naturally from what we just discussed. What is happening is, if I'm just taking one of these blue boxes and making it into a triangle. So if you start off with the exact answer for this L-loop 4-point function in 4 dimensions, this is the answer that they give. And this is written in the same notation that we had earlier. So now there are these cross ratios u and v, out of which we form these z bar variables. So you get an expression looking like that. And we can very simply recover the 3-point function. All we have to do is change these cross ratios to simple ratios and get this 3-point function. And indeed, this is the 3-point function that they also find. But now we have some explanation for it coming from these conformal transformations. In fact, we can also take, we can take one of these boxes here on the left side to a triangle. Then you'd get a 2-point function, which is L-loop contribution to a 2-point function. And if you did that, you very simply recover this result, okay, which is a finite result. And it turns out that people have been computing this result to various loop orders. So there's 1 loop result by these authors in 1980, and there's a 3 loop and 4 loop result in 2010. And this matches with all of these results. But at once we recover the L-loop answer just by doing a very simple transformation on an existing 4-point function that we found. Okay. To give you one other example which works in any dimension, you can recover the box integral in any dimension from this pentagon integral, which is conformal pentagon integral. And you can do it in dimreg, because now this is, let's say you wanted to compute this in 4 dimensions, this is divergent, but you can do it in dimreg, thank you, because you have the exact answer here in any dimension, so then you can put d equal to 4 minus 2 epsilon and recover the dimreg answer. And in particular, you can look at the on-shell 4-point box. And that's also something we can very simply do, because our simple ratios are given by this. And if you want to put all the external particles on shell, that's just taking the cyclic differences of momenta squareds to be 0. So the only non-trivial ratio that remains is this P13 by P24. So we can go back to our expression for the box, and we are left with 1 million integral to do, which corresponds to that 1 ratio. And if you do that 1 million integral, we get this exact answer. And indeed, if you go back and look in the literature, there is a paper in 2017 by Tarasso where he computes this massless on-shell box integral with arbitrary powers of propagators using the differential equations method. And we recover his answer very simply by doing just 1 million integral. Okay. In particular, you can find the dimreg answer for this by putting d equal to 4 minus 2 epsilon and so on, and then it matches with the dimreg result in this paper by Byrne, Dixon, and Kosover from 93. Okay. So it seems that there are, even in momentum space, this sort of gives you some nice way to compute some Feynman diagrams and get exact answers for them. There's one more example I wanted to say, but I'll just skip this for lack of time. And I'll just go to the last part of my talk, which is to say that there are further conformal transformations which relate the diagrams that we just saw in different families. And these relate diagrams with different number of loops in them in momentum space, or the equivalent version in position space is with different number of vertices in them. And so to be able to get at some basis set of correlators, which we need to compute once for and all, and then using these relations, we'll be able to compute any other correlators as combinations of this basis set. So to find that basis set, my claim today would be that all you need to do is to compute Feynman diagrams with cubic interactions, and once you do that, you'll be able to get Feynman diagrams with other higher point interactions as combinations of these Feynman diagrams with cubic interactions. Okay, so in the last 10 minutes or so, let me tell you how this works. So if you looked at 3-point conformal correlators, we of course know this result that 3-point conformal correlator is just given by the product of 3 propagators, right? And if you use the relation sum of deltas equal to d in this case, you get that the product of 3 propagators has these powers, delta 1, where delta 1 bar is, sorry, it's d by 2 minus delta, there's a typo here. So this is d by 2 minus delta 1, d by 2 minus delta 2, and d by 2 minus delta 3. So that's the integral relation. And this, in the Feynman diagram literature, this was called the star triangle relation, where they noticed that if you happen to compute a diagram here which satisfies these deltas, sum of deltas equal to d, then you get a triangle instead of a star. But we now take this relation and we can go to higher point interactions with this sort of a relation. So how does that work? For example, you start with a quartic interaction here. Okay, so you start with a quartic interaction which has delta 1, delta 2, delta 3, delta 4. You see that you can express this interaction by looking at 2 cubic interactions and an exchange between them. And this works because this a star on the right you can replace by a triangle, so you'll get a triangle here. And what I've done is I've added an extra propagator here between these two external fields, which will cancel the third side of this triangle to give you back the quartic interaction. Okay. So the idea is that if you wanted to compute correlator here with this quartic interaction, which is this thing on the left hand side, you would what you would compute is an exchange diagram with 2 cubic interactions, which is this thing on the right side, and you would have to multiply this by this factor here, which is this which accounts for this external propagator. Okay, and you can go ahead and do the same at. You can go ahead and do the same at. So here you could do it in 2 ways. You could take either an external propagator here or there, or between any 2 external fields. So you're able to expand this in various channels. This is one channel, this is another channel, and so on.
So can you explain, these are different fields in the second diagram, like phi 4 prime and phi 3 prime. Can you explain that again a bit?
Yes. So you're replacing one quartic interaction here by 2 cubic interactions, and in general by you're introducing other fields, not the fields that you started off with. But the point is that Feynman diagram by Feynman diagram, you'll be able to recover your original answers by looking at these kinds of interactions now.
So what is that extra, how that extra propagator is compensating for that? Can you explain?
Yeah, so the point is, so what you have to do is you just imagine doing this integral here on the left.
Okay.
Okay. If you do this integral on the left, there is the conformal condition here, which tells you that the sum of the dimensions here add up to d. And so what you will get instead is a propagator going from phi 1 to this point, from that point to phi 2, and a third propagator that's between phi 1 and phi 2. So that the third one cancels this one that's already here, which is shown in this dotted line. And so the 2 things that you end up with are one propagator from here to here and there to there, which is what the
equivalent to that diagram.
Yeah.
Okay. Yeah. Thank you.
So you can do this at higher points. We start off with a pentic interaction. You will have 2 of these external propagators that you have to introduce. And you imagine doing both of these integrals on the left and the right, and then you recover the thing on the left-hand side. You can go up to any higher order you want. If you do a sextic interaction, for example, you have 3 of these, and so on and so forth. So what you are able to do is you're able to replace your higher order interactions by combinations of cubic interactions. Okay? And the usefulness of this is that the cubic interactions will give you some set of Feynman diagrams, and you can use that as the basis set to be able to compare, correlators in different theories which are secretly related to each other by these conformal transformations. You can discover all those relations by working instead with this cubic set. Okay. So you're blowing up these multiple point vertices into cubic ones, and you're generalizing the star triangle relation to arbitrary numbers of fields. There are momentum space implications of this cubic expansion, which is summarized in this slide. So basically here, if in the first line, this quartic interaction being represented as an exchange between 2 cubic interactions, in momentum space, it looks like replacing a box with 2 triangles. The pentic interaction with 3 cubic interactions looks like replacing a pentagon with 3 triangles, and so on. So at the end of the day, what you're doing is you're taking all momentum space Feynman diagrams, and you're seeing that you can replace all of these polygons just by triangles. So what you only need to compute is Feynman diagrams with triangles in them, and then you can recover all the other kinds of Feynman diagrams by taking combinations of these triangle Feynman diagrams. Okay. Let's try to then see in this cubic expansion what are the kinds of diagrams we get. Okay. So I just told you that this one here is just the quartic interaction. This one here is the pentic interaction. This one here is an exchange interaction between 2 quartic vertices, because if you do the integral on the left and the integral on the right, you will see that that's an exchange between 2 quartic vertices. But there is one more simpler class of diagrams you can get. So here we are increasing the number of external fields as you go from the left to the right. But let's say at 4 points, at 3 points it's too trivial because you just get the conformal 3-point correlator. But let's say if you have 4 points, what are the simplest diagrams that you can get? And those you can get by taking coincident limits of these higher point diagrams. Okay, and it works nicely. So for example, take the diagram here in the middle and take the coincident limit where you take 1 point here and another point here, and take the limit where those 2 coincide. You get this. Okay, so this is what I'm calling maximally coincident chain diagrams. You can do this with the diagram here, and you'll get this one. So what these maximally coincident chain diagrams are actually secretly, if you go into momentum space, they're just the ladder diagrams that we had earlier. Okay. So these are the kind of relations that you see once you use these sort of conformal transformations. And these ladder diagrams now, the ones that we wrote down earlier were ladder diagrams in 4 dimensions, but these are now ladder diagrams in arbitrary dimensions. And using secretly the fact that we have this representation for them, we can find an integral representation for these ladder diagrams in momentum space, and that looks like this. Okay. So where, you know, the ladder diagrams now I've expressed in terms of these d tilde functions that we saw earlier, which are these products of gamma functions. Okay. So one can get these sorts of representations for these diagrams from this as well. And another class of diagrams that I wanted to quickly tell you about is if you go back here and instead of going to the to these 4-point and high point diagrams, I'll take one step further back and I'll go back to a 2-point, what looks like a 2-point diagram with delta 1 here and delta 1 and delta 2 there. So if this diagram has to be conformal, then the sum has to also add up to D. So the only kind of conformal diagram you get here is one with a delta and one with a delta tilde, which is D minus delta, which otherwise we know as the shadow operator of this guy, right? And the other building block that you have is this 3-point function here. So earlier we saw contact interaction, but now I'm imagining here to be some anything else. But whatever else is there here, a 3-point function will always give you a product of 3 propagators, right? So we can put both of these building blocks together, right? We can sort of take products of 3-point functions, and that gives us another sort of simple looking class of diagrams. So this class looks like this. You take integrated product of these 3-point functions, 2 of them, 3 of them, or some n of them. And this class of diagrams you might have also seen before. They are nothing but these conformal blocks in the Coombe channel, okay? Or more properly, they're called conformal partial waves because they also include the contribution of the shadow operators. If you're wondering why Coombe channel, because you can rewrite them like this, which resembles a Coombe. And these guys were actually computed at 4 and 5 points by Rosenhaus in 2018, and remarkably enough at n points by Sarthak in 2019. So we can get some integral representation for them and all the Mellin integrals to get a series representation, but all that work has already been done for us by Sarthak in this paper, where he actually uses some ADS geodesic Witten diagrams to compute this. However, so now that we have this answer, we can go back and see in our Feynman diagrams what do these answers give us. Okay, so this is the answer for the endpoint conformal partial waves in this Coombe channel. In the Feynman diagrams, this corresponds to, in position space, a chain like this. And in momentum space, it actually again gives you back the ladder diagrams, but now with extra rungs. Okay? So our earlier ladder diagrams had just these 2 rungs in the beginning and these 2 rungs in the end, but these have all these alternating extra rungs. So his answer for the endpoint blocks in the endpoint conformal blocks in the Coombe channel directly gives you these sort of diagrams in momentum space. So you can also take these 3-point functions and then smooth them up not in this linear way, but in you know, in different ways, and you get conformal blocks in all kinds of channels. You can derive some integral representations for them and so on using the methods that I've been talking about. And each of that will give you some representation for multi-loop Feynman diagrams in momentum space or multi-vertex Feynman diagrams in position space. In the last 1 minute, I'll just tell you that if you can go ahead and consider loop diagrams in position space, which in momentum space give you nested loop diagrams, because contact diagrams in position give you loops in momentum, loops in position give you loops of loops in momentum, which are these nested loop diagrams. And our conformal guys have these simple relations even for these sort of nested loop diagrams at 3 points and 4 points and so on. So since I've run out of time, I end here. I'll just give you a summary. that we said that all flat space correlators have this conformal representation, and we would like to use this to study massless correlators at null infinity. We also would like to see if we can use this for massive correlators, maybe at spatial infinity. In momentum space, we found that Feynman diagrams live in these conformal families, and we used it to find some finite as well as dimensionally regularized answers for these Feynman diagrams. We would like to see if this can help with the computation and of some relevant phenomenologically relevant Feynman diagrams in the future. Out of all this conformal representation, you get actually a new integral representation for this Feynman integrals, which is different from the usual Szymanczyk polynomial representation for them. And that's something we would like to also explore in the future. And we'd like to see how much of these structures of conformal field theories we can put to use. Okay, thank you.
Okay, thank you. Okay, maybe time for very two short question, please. So, okay, one was there.
So, in the first part of your talk, where you were taking some limits to take 4-point function, then retain in terms of 3-point function, I was just wondering, is it possible to just start with a 3-point function of the non-conformal theories to construct the 4-point functions of the CFT?
Yeah, it is in the contact case. It is, because in the contact case, all you have to do is replace the simple ratios by the cross ratios. But that's not true for the higher point cases, because if you go beyond contact, then the conformal and the non-conformal are not literally the same. The non-conformal ones are a limit of the conformal ones, but you can't go the other way around. Conformal ones have actually more information left.
But
you could see that in the ladder diagrams that I gave you, for example. The 2-point ones just have that simple finite answer, but from there you won't be able to recover the 3-point ones, which have a complicated expression in terms of polylogs and so on.
Is it possible that any subleading correction to 1 over this infinity limit, also including those also in general?
No, because these are exact answers for the full diagrams. They are not in some expansion.
Okay. So one more, but yeah, we will be back by 11:57. Try to be precise, because somehow we have to manage. We are already running 30 minutes late. Okay, so let us thanks Sarthak again, and then we get back. Okay. Some announcement?
Just one small announcement that we'll be having excursion to Konark on Friday, 12th. So those of you who want to go, please sign up on this sheets kept at the station desk. Thanks.
Okay, thanks. So let's get back to 11:57. So yeah.
No, नहीं. Not ESC. Oh, wait, they're not open.
Open is settlement. Where is it?
Who's next?
Arjun Babji, I think. Place myself. We are here, right? So Nico. Is he okay? It's okay. Just don't.
There's no open in new tab. Oh, this is open.
Okay. This is there, and then I think this Arjun Babji.
Somebody says using their own laptop.
Abhiram Kindambi. Kindambi, I think. Kindambi.
Kindambi will use your laptop.
Just let them know that.
speakers, you know?
Yeah, we have arranged that.
Oh, you know the numbers, right?
Should I put it to 40 or what? Sorry.
अरे यार इसने वापस पूरा ऊपर कर दिया यार इसी से भी दिन रहता है I think I'm not the best person but that 5 plus minus 5 is 195.
Yeah, I think they changed.
Because that is, yes, exactly. So maybe like in 25.
Fine, I guess this is the.
This is the same problem as in the morning. What did they do?
I think this is okay.
I think maybe they can adjust this. What? Yes, the second one.
Please, Anand, please get the microphones ready.
Yeah.
for this. Okay, so welcome back. So in this session, we will have 3 talks with 30 minutes. So I would request, the speaker as well as the audience to not, get into very long loop. So we'll have discussion during the during the lunch also. Excuse me. Yes, so we have Nico who would be talking about string-inspired holography for hot and dense QCD. So let's listen to him. Okay, Nico, please.
Okay, I take that you hear me. So I'll start by thanking the organizers to invite me here, and in particular, rescue me from the dark north. Okay, so we heard some interesting talks in the morning, and so now you're going to experience something different. So this is something that we have learned during many years. So I'm going to present, works with these people that I've directly worked with. So so there are many people involved, and if I don't do justice to this work, you should really shoot a messenger. So I already apologize for citing not all the works that they are in the literature, especially if you are in the audience and you feel that I omitted you. That's the well, you wouldn't notice that anyways. You're sitting so far, you don't get to see the screen that clearly. So very good. So what's the outline of the talk? So I will start with some motivation, and then I will present some features of this data-driven holographic approach. I will make some contact with astrophysics. I will end up with the phase diagram of holographic QCD, and then I will summarize and give some sort of an outlook. Okay, so the motivation is to try to understand nature at the fundamental level, and for the time being, that means standard model of particle physics, and I'm interested in particular the strongly coupled sector of that, which is QCD. And the matter at extremes is very interesting. For example, if you heat up the QCD matter to extreme temperatures, you get quark-gluon plasma. Or if you take this all of us in the world and you compress that to immerse, you keep on compressing all humanity into a size of a sugar cube, you reach densities of which you would encounter inside neutron stars. So that's pretty exciting. So to describe this is still low energy from a particle physics perspective, and in that case the QCD is strongly coupled. It's complicated. So this means that the perturbation has limited applicability. Lattice approach is either too expensive or not trustworthy, and there are no all encompassing models that you could describe all the things that you are interested in on the same footing, such as this quark-gluon plasma and neutron stars. So maybe this is a fruitful application area for holography. There are of course some serious limitations in the number of colors not being 3, but it can actually give an all-encompassing models and gain insights. So can we solve QCD using a neutron star? So what I present here is the sketch of a phase diagram of a QCD. So the y-axis is the temperature, and this is the chemical potential. So what we know lattice QCD gives some results at small chemical potentials, and you cannot extend that to finite densities. Effective field theory works close to down here, and perturbative QCD only at asymptotically far from the origin. And so there are some open questions at the intermediate densities, and in particular right here, so that's where the neutron star densities are. On the left I have a sketch of a neutron star. So this is an object which is of the size of 20 kilometers. So you could basically fit that in between us and the downtown Bhubaneswar. And this is very dense. So the masses are 1 to 2 solar masses. So very dense objects. So if you would, throw some material to the densest or the most massive neutron stars, that would ultimately collapse into a black hole. Okay, and we don't actually know what's inside here. So there are all kinds of models suggesting that maybe there are hyperon matter, or maybe there are quarks, deconfirmed matter, and so on and so forth. And but there is some data coming in from gravitational waves, for example, and we could sort of try to infer what's inside, and in particular we could then infer what is the phase diagram of QCD in this axis. So maybe that's the way to approach this using ADS-CFT, is that maybe if I replace this part of the neutron star by some ideas coming from ADS-CFT, I could actually try to do this inverse problem. So I could try to infer what is the QCD phase diagram, and by that I actually mean the relationship between the pressure and the energy density. So in order to solve for a neutron star, this is a self-gravitating spherical object in general relativity, but in order to close the equations, you need to give a relationship between the energy density and pressure. So that's the equation of state. So here's an equation of state, pressure is a function of energy density. So in principle, you should be able to compute that from first principles, but it's a no-go currently. And from holography, you could actually try to draw a line here in between so that it matches the effective field theory at low densities, nuclear theory, if you so wish, and then it goes through a band which is generated by renormalization scale changes in perturbed QCD. So no matter what your theory is, it should basically meet these two endpoints. And this is our approach. And there are two reviews in the there that you can read more about this and more references. So why do we actually use holography to describe this dense matter? So that's one interesting question. Because there are lots of models already in the literature. So maybe holography is just another uncontrolled approximation. Okay, but there's actually strong motivation to use holography because it might actually work better than many other approaches, because this is strongly coupled physics, and holography may work better than these other approaches, which are basically wired to work at decoupling or in perturbative regimes. Different phases, quark, nuclear, maybe color superconducting, quarkion and whatnot, those can be actually taken in the same footing in this holographic model, even maybe in a single model in the future. And this is not typically achieved in the literature. In the literature, what happens is that we will use some other model for quarks and another model for nuclear matter phase, and there's no consistent way of putting them together, because they're in a different model. And in particle, this means that you cannot describe phase transitions, because you don't know where it happens. But if you can achieve that in one model, you can predict where the phase transition happens, for example. And so as it turns out, these predictions from holography, they do make sense. Okay, this is highly non-trivial because there's no a priori reason that there would even be a holographic dual of a QCD. And what is interesting is that many details just work out of the box like that. And why you in the audience should care about this is that for once we are going to have an experiment which might care about our holographic equations. And for example, this Indian Initiative for Gravitational Wave Observations commences in 2030 maybe. So you should be ready because there are going to be lots of data coming into your desks. Okay, so top-down approach. We know that there are gluons in QCD, so this means that you take some background geometry generated by deep brain fluxes. But this is also not conformal field theory because there's a dynamical scale. You need to have some, let's say, scalar fields, pre-conformal field theory, conformal symmetries. There are quarks, so this means in a holographic sense you need to add flavor D branes. Baryons, you have wrap branes on some internal cycles if you wish. And back reaction of this mess is practically impossible, okay? And you are limited to, let's say, quench batter case or maybe do some smeared approximation, who knows what. But nevertheless, many computations has been done, especially in the probe level by D3, D7, so that's something that we started several years ago. Also papers on Sakai Sugimoto model and so on and so forth. Both of these cases have been applied in the neutron star context already, which means that you basically go to zero temperature but finite baryon chemical potential. So you get beautiful equations and elegant intuition coming out of that, but unfortunately neutron stars don't care. So what's this bottom-up approach? So we are just going to limit to equation and state discussions. So we are basically want to have some sort of state-of-the-art equation state, which already, well, there is, of course, by definition, one of those. And so that it can be used to describe quiescent neutron stars just sitting out there, in simulations of neutron star mergers, core collapse supernovae. So that hasn't been done yet, but I'm sure that people are doing that, being contacted. Also analyzing heavy ion collisions. So all-encompassing model. And we are going to use a specific holographic model. This is a very sophisticated framework. It has been developed over many, many years and so on and so forth. It basically consists of Einstein gravity with dilaton, and then there's brain action, we mean dBi, and there are Sumino terms that take into account CPO sectors and who knows what. Some parts could also be described some simpler approaches, which has been very popular also in the literature. For example, Einstein-Maxwell dilaton approaches, but that is only applicable to quark matter. So you cannot really go to neutron stars that easily. So the main ingredients is that I'll have a holographic model for quark matter. So this basically corresponds to a background geometry. There's a black hole, deconfined matter. There's a holographic model for nuclear matter. There's no black hole in the bulk, but that's not great when it's adjusted a little bit because the thermodynamics in that phases are sort of trivial. You need to amend that a little bit, and also these are lots of nucleons, and when you go to very small densities, the holographic description of this is not great. So it's better to merge it with some traditional nuclear theory. Okay, so that's what we do. So we are going to combine all these building blocks to make this monster, this hybrid model. And one thing that to notice that you better make sure that your theory that you start with at, let's say, small chemical potential matches with known physics. Okay, so it has to match with what you would expect from QCD qualitatively, and in this case also quantitatively. And that's something that we have spent lots of time into, so we have made sure that our model precisely matches lattice data that there is at very small chemical potentials. So there are some fits that basically fixes your action to some way. Okay, and then put them all together. You get some sort of a description of this holographic model. But what happens that I already mentioned is that the description of nucleons in confining geometry is very trivial, so there's no temperature dependence. So there are some nucleons. So how do we come around this? Is that we actually borrow the temperature dependence of these baryons by adding van der Waals interactions. So that will give them, temperature dependence. And then we will also make sure that we will merge with some traditional nuclear model very smoothly in such a way that we don't generate some spurious first-order phase transitions. And now you notice that this basically covers all there is, also the new heavy ion collision regimes and neutron star regimes. So this is consistent with all theoretical and observational constraints. I will come back to that too. And what you can further do is that, so this was basically used by a certain choice of potentials, and something that we also did very recently is that we generalized this into a probabilistic approach. Okay, and this is a very technical slide, so this is the most complicated slide on my talk, I think. So what we do is that we will we're going to match with some traditional nuclear matter model at very, very, very low densities. So half the nuclear saturation density. The nuclear saturation density is basically the mean density of a nucleon. Okay, and if you are at those densities, then the nucleus begin to interact, and you would need to care about interactions and whatnot. At those densities, you basically are describing the crust of the neutron star. This is very well known. Well, to very good accuracy, I mean, when it comes down to questions about the equation state. So if you change little bit your crust, it doesn't make big differences in the equation state. So we just pick some crust, and then we merge that with some sort of interpolating solutions between in this region, which basically covers all viable equations of state. Those are so there are parameters in this game because we split it into, let's say, 4 segments, and there are some parameters that basically parameters our ignorance about the equation state. That transitions into holographic description. There's a continuous transition to holographic nuclear matter. Later on, there is going to be a transition in the holographic model to quark matter, which is strongly first order at 0 temperature. So this is marked by this horizontal line. So this is the pressure as a function of energy. Actually, this is a number density now. And then all these equations of motion equations, they actually meet the perturbatory QCD band. So our prior are these gray lines here. Okay, so then what we do is that we take all these priors and we compute what kinds of stars do you get out, and you get these stars which are in gray here. And then we will implement constraints probabilistically, because we know that there are, for example, stars which reach 2 solar masses, like so, and there's simultaneous data for the mass and radius from the NISER, the other NISER, the neutron star interior composition explorer sitting at the International Space Station. And there's also a constraint on the diagonal deformability of a neutron star. So what happens is that if a neutron star is in the vicinity of another neutron star, there's a big gravitational field, it deforms, and then you can calculate how much it should deform. And because they didn't see that, they actually get some sort of a bound on this diagonal deformability. So we can also implement that from this one event. Okay, so you go and compute this, you implement these constraints, these astrophysical constraints, and in addition we also implement probabilistically constraint on the chiral effective field theory, and then we see what comes out as a posterior distribution. Let me also mention that this is basically all these equations state actually go to the PQCD very nicely at these densities, so they don't actually, it's sort of automatic, if you wish. So what they comes out are these color bands. So this blue one, and the darker the color, the more probable that equation state is. There's also a red line, and that's the the most likely equation state. Has the highest probability, if you wish. So that's the optimal model. And then you can also compute what comes out as a function for the mass, as a function of radius, and you get some sort of a prediction also for this. So if you find a star which doesn't hit that somehow, then we can rule out our holographic model. That's nice news. Okay, so this is the equation state. Basically at 0 temperature, you can just compute all kinds of quantities that you care. For example, one thing which has been on the hot topic recently has been this trace anomaly. This basically measures that how much we are away from the conformal equation state, if you wish. So distance to 1/3 is the conformal value. You get some curves like so. You can also plot how strong is this first order phase transition from nuclear matter to quark matter as a function of number density. You get some probabilistic determination of this. Speed of sound is here. It goes above the conformal limit. There's a first order phase transition. It drops down, goes on to 1/3 eventually. And in particle, there's what is called the conformal distance. So this is supposed to be a better device to tell about the conformalization of our material or QCD matters. Because the QCD matter is supposed to become conformal when you go to asymptotic densities. And this is maybe a better device to measuring that by these guys. And what happens is that if you note this conformal distance actually goes below this 0.2, and it's larger than 0.2 in the quark matter phase. And this is sort of in contradiction to their way of telling apart nuclear matter from quark matter. So this was a way to try to separate and to see whether there could actually be quark matter cores in isolated neutron stars. But what we find is that this holographic nuclear matter doesn't conform with that notion. So this is a singular equation of state, or maybe this is probably shared by many families of holographic equations, that doesn't conform with traditional nuclear matter models. They went through all the nuclear matter models that are in the literature, and they came up with this criteria of 0.2, and now we don't meet that, and this is great news. Okay, so that was 0 temperature, and then you can extend this to finite temperature. And so here's the, again, what we get out as a posterior distribution for the phase diagram. So again, there's the temperature on the y-axis and the baryon chemical potential on the x-axis. So recall that there's a first order phase transition at 0 temperature, and you can just track it upward as a function of temperature, what happens. And what happens is that eventually the phase transition goes away and it ends at the critical point. There's going to be a prediction for a critical point coming from constraints from astrophysics. And this critical point is, in here. And if you now go and can compare what you would get from models that are built at 0 chemical potential, what do they get when they predict a critical point for a beta equilibrated strange neutral matter? They're in the same ballpark. So something may be correct here. So that's also pretty interesting. There are also all kinds of other things in this plot. So this is pretty busy. So these green and orange bands, those are estimates from two different lattice QCD groups for crossover temperature. There's also the Grease outline. So if you have a phase transition, the phase transition, and in particular the critical endpoint should better be above this line. Okay, so let me summarize. I'm running out of time anyways. So I hope that I convinced that case gravity duality or radius CFT provide some insights into QCD matter, and some of these details actually looks reasonable. And many details actually work very well. So precise fit to lattice data is possible. You can get an equation state for cold quark matter that looks also reasonable. This is a simultaneous model for nuclear quark matter, and you actually get a very stiff equation state for nuclear matter, and this actually sort of helps to overcome all those constraints coming from astrophysics. I only presented you predictions for the equation state at, for cold and finite temperature matter, and are argued in favor of a critical endpoint for beta equilibrated QCD matter. I did not discuss transport, so this is something that has been computed for the unpaired quark matter phase. There are 0 results in the literature in the holographic nuclear matter, so I welcome you to do that computation. This is very important. So standard computations are here, but what is much more interesting is that the the electroweak bulk viscosity is much more interesting. It's 20 orders of magnitude larger than the QCD contribution, but the QCD input goes into that computation. That's something that we managed to do in this paper, both in using holography and also in Perturbative QCD at next to leading order. There's a nice match. I didn't discuss properties of neutron stars or signatures in gravitational wave spectrum. Interesting. Let me just say a few words about outlook. So these are nice neutron stars. Maybe there's now a way to actually see some hints of holography in play. So that's a challenge to us. So we should try to put our finger on that. There are lots of extensions one could do. Favor-dependent masses, turning on isospin, look at neutrino emissivity. So there are also some words already in the literature. Magnetic fields hasn't been done. Nothing. Neutron stars have a magnetic field. You should care about that, especially when it comes to transport. Quark pairing, there are some ideas. And there are lots of caveats also. So what I presented was a Maxwell construction. I basically said that I have a phase transition from a nuclear matter phase to a quark matter phase. And I said it's an abrupt transition. The surface tension between these two phases are practically infinite. So there's no possibility for mixed phases. In practice, the surface tension is something finite, and you could in principle have sort of simultaneous quark and nuclear matter. And maybe you could also see quark matter in these neutron stars. And one big issue is that homogeneity seems lost. So there's a global flavor anomaly in QCD, and this is all the details are basically dictated by by one coefficient. And it happens is that if you do this computation in these holographic models, we looked into many families. All of them in the quark matter phase, they are unstable towards modulated phases. And what happens is very surprising is that this instability reaches to very high temperatures, maybe even cloaking the critical endpoint if it even exists. So maybe there's a possibility to actually see some sort of inhomogeneities in collider experiments and also in the lattice. So this is a regime accessible by lattice methods. But there are some caveats here because this is done at with zero masses for the quarks. We did some estimates when we turn on strange quark mass, and this phase boundary does move. So it's not clear where it moves, and that's going to be future work. Right. Thanks for your attention.
So thanks a lot for the nice talk. So we have the time for two short questions.
Can you repeat what was the statement about the conformal distance not going below 0.2 and why is it good news?
This one.
Yeah.
So this is sort of the criterion which basically measures how conformal the matter is. And with that, you can then try to give some sort of an estimate how much conformal matter there is inside a neutron star. Okay? You may wish to call this, for example, quark matter. Okay? And one criterion that you could imagine using is that if you have an equation of state for which this conformal distance is below 0.2, you call that quark matter. So this is one way of distinguishing nuclear matter from quark matter in this model agnostic analysis. And they did two analyses in that paper. So one is by the same kind of interpolation that I did with constant or linear speed of sound segments, but they also did Gaussian process inference. And both of those gave results that very, very likely most massive neutron stars do have quark matter cores based on this criteria.
Thank you for the nice talk. I have just two questions. Like when you talk about the VQCD, so that the V there, does it point out to the Veneziano limit of the QCD?
Yes, there's a Veneziano limit, that's right. So there's a full back reaction of the flavor sector to the...
Okay. And
yes.
Second question is that suppose for high energies, when the asymptotic free term comes into the picture, does the VQCD, that model, will account for that at high energies?
So what happens is that at zero chemical potential, so this VQCD is wired to match with lattice QCD. But when you go to, let's say, zero temperature and asymptotically high densities, what happens is that you can basically see it from the speed of sound. So the speed of sound actually goes to this conformal value, but it goes to it from above. Okay? But that's okay because I don't trust my holographic setup anyways at asymptotically high densities. I only want it to be reasonable in the regime where I apply it, which is here. Everything's under control there.
Thank you.
Okay, so let us postpone further question for the lunch time and thank the speaker again. So our next speaker is Arjun, who is going to take us through some Carolean adventures in the flatland. So, okay, so Arjun, please don't take us too far because, we have to go through revisiting some, this complex multiplication before we get too hungry. So, take us through that adventure.
I'm not the only one who's standing between us and
Thank you.
Okay.
Thank you.
With that heavy responsibility.
Do look at me.
No,
usually what happens after 15 minutes, speakers don't look at the chair.
I'm late, I won't look at you, right?
Okay. Thanks.
So, all right, thank you. Thank you so much. And I would like to start by thanking the organizers for giving me this, opportunity to speak. And most of my job is done, actually. So Mrityunjay introduced things, and with Daniel, we have had an hour of adventures. But again, this is supposed to be a slide where I say, it's a strange thing to take speeds of light to zero. But you already know that, and you hopefully are already in love with it. So I wanted to show you something. So this is called the kaleidoscope, as we try to call it, and it's a review that I wrote with these people here. For those of you young people in the audience looking for new projects, I invite you to go here and try to solve some of these enormous number of things that we seem to be trying to find at the moment. And these symmetries, these weird symmetries that you have, heard about now for two talks, emerges practically everywhere. So in all of these places, I'll of course not, since I'm, the chair is going to be strict with me, so I cannot speak for a day or a week. I can't go through everything. But it's just not words. We are actually doing things where we are looking to understand, Carol and condensed matter. Rudranil, whose slot this was supposed to be, was going to speak about, Carol and condensed matter. So we have been looking at field theories. We're looking at hydrodynamics with, Ashish, who's here in the audience, and others. And we've been also looking at strings. And but this talk is not going to be about any one of these things. And as advertised before, this is going to be about flat space holography. So why is this important? This is important because so we started off with these symmetries, and what happens is that these symmetries generically appear on any null hypersurface. And the two most important examples of this are the null boundaries of asymptotically flat spacetimes where you have scattering defined, and even horizons of generic black holes. So this is going to show up when we try to understand holography in flat spacetime. So that's where we are at. And these are the people that we have been doing work with for a long time now. And so I'd like to thank them going forward. It's been a great journey. Right. So I will give you a little bit, maybe 2 minutes of a review of what was done. What we say is holography in this way. So again, this trying to take the speed of light to zero. Mrityunjay has shown you this earlier, and Daniel has repeated it. And so what you can do is you can start off with the usual I mean, Poincaré algebra, and you can take the speed of light to 0, you're going to end up with a different, I mean, algebra where some parts of this are, I mean, abelianized. So one of the most important things is that, you know, these CIs, which are now the boosts, they actually give you 0, and this reflects the non-Lorentzian nature of the algebra. And this is, so you can also give it a conformal extension, and this algebra written in this way is what we call the finite dimensional, conformal Carolian algebra. Daniel also flashed, I mean, this was the central element of his talk. So what happens is that if you go in 3 dimensions to the null boundary of flat space, this is the Bondi-Mesner-Sachs algebra that you find. And so this is in 3 dimensions. My talk is going to be about 4 dimensions, and this is the not so simple looking algebra that you find. This is called the BMS4 algebra. Now you see, just to contrast it with what we had in the talk in the morning. Now you're instead of a circle, you're going to get a sphere here, and so what happens? You get 2 copies of your L's, your super rotations get lifted to these 2 Virasoros, and the super translations, these M's which commute amongst themselves, now have 2 legs. Okay, so that's the algebra that I would be interested in. And the reason why these 2 things are equivalent is because there is an isomorphism between the conformal Carroll algebra in D dimensions and the BMS algebra in D plus 1. And this forms the basis of this flat space, this program of flat space holography. And let me just, in a slide, give you the main thing here. So this is, what we try to, in this framework, what we try to say is that if you have a field theory that is dual to Minkowski spacetimes, it should inherit its asymptotic symmetries. So, a theory of, quantum gravity in D dimensions, asymptotically flat spacetimes, we hope that this is dual to a D minus 1 dimensional Carolian field theory. So and this CFT, this field theory, this CFT is going to live on the null boundary of flat spacetimes, and we would have 2 sort of ways of trying to understand this. One is sort of like the intrinsic way where we use these symmetries, and Daniel also mentioned in the morning that there is a limit. So we call this the ultra-relativistic limit, and so that's what we want to do. And what I'm going to be focusing on in these next few minutes is understanding 4D flat spacetimes and 3D CFTs of this kind. Yes?
So just a quick clarification. So when you take C goes to 0 limit, the resulting thing that you get, there is no time, right? Like
no, there is. It's a null time.
And the BMSD that you write down analogous to, that's like that will be like the Minkowskian one, or the meaning?
If you are thinking about the finite dimensional subalgebra, for example, this is exactly the Poincaré subalgebra. What happens is what you can do in D equal to 4, 3 and 4, is that this is going to also have an infinite dimensional version of it. But for my talk, for whatever little that I'm going to be saying in this talk, you can just think about what we are trying to do is we want to figure out field theories which has, let's say you are in 4-dimensional bulk. So your field theories are ISO 3.1. Are symmetric under the Poincaré group in 4 dimensions, which is ISO 3.1. I want to realize a field theory in 3 dimensions, a dual field theory in 3 dimensions, which has the same symmetries. So it's going to be ISO 3.1 realized on D equal to 3 instead of your usual D equal to 4. So that is the equivalent statement that the ADS isometries in D dimensions map onto CFT in relativistic regular CFT in D minus 1. So there the groups are SO D2 on both sides, right? So this is the equivalent statement. There is going to be bulk physics, which is going to be invariant under, if it's D dimensions, ISO D1. And there is also going to be, boundary physics, which is D-1 dimensions, but realizing the same algebra. Okay, so that's what I'm going to be doing, and hopefully it will be clear as I go along. Okay, so what do we want to do? So there has been a recent sort of resurgence of flat space physics, and these, IR triangles have appeared everywhere. So these relate soft theorems with asymptotic symmetries and memory effects. Just to flash this once more, this is the algebra that I'm going to be interested in. This is BMS4. To answer what you were asking, if you take n and m as plus minus 1, that's your 6. That's 6, and you take r and s equal to 0 and 1. That's 4 more. So that's the 10 generators that you're going to need. So the Lorentz part is hidden in the L's, and the translations are in the M's. Yes. You will. I'm not going to be addressing those subtleties here, but we can speak about this, and you will. Yes. So the main point essentially is the boundary, the metric on the boundary will have a 0. That's the main point. But anyway, let's go forward, because again, as usual, I think I'm not going to get anywhere in the talk. So this is the algebra that I'm interested in, and so. Flat space holography has seen two, so now it's sort of two ways of trying to do it. The more popular approach is a codimension 2 approach, which is called celestial holography, and we will hear more about it, I think. But this says that the dual theory is a two-dimensional relativistic CFT, and of four-dimensional flat space is a two-dimensional relativistic CFT. And there have been significant understanding in 4D scattering amplitudes and asymptotic symmetries based on this. What we are trying to say is that this is going to be more like a usual codimension 1 version, where the field theory that you're going to be dealing with is going to be this weird one. Okay, so that's the approach that we are going to adopt, and there have been some attempts to bridge these two. And again, I point you to our review for more details on this. But let's go through this a little bit. So again, this is going to be very quick. So I apologize for that. So the main observation in this codimension 2 approach is to say that, look, Lorentz group, acts as two-dimensional global conformal group on the boundary. And the basic observables here are S matrices. What you can do is you can recast the S matrix in terms of endpoint functions of a two-dimensional CFT, which lives on the sphere now. Okay. And here I have sort of parameterized this, and so there is a Mellon transformation going on between the endpoint function here and the S matrix here. These O operators are primary operators in this 2D celestial CFT, and I have parameterized the momentum of these sort of massless particles in this way, which you'll be seeing throughout. Okay. All right, and ZZ bar are the stereographic coordinates on the sphere. Just to give you a little bit more, you can rewrite these local fields in terms of creation and annihilation operators. If you see this epsilon sitting around here, this is plus minus 1, which just says that if this is a creation operator or an annihilation operator. Now, these local fields transform nicely under Lorentz transformations, and they give you the usual SL2 primary-like relations. This is the thing that forms the fundamentals of this link up between 4D flat space and two-dimensional relativistic field theories. Now, I have some issues with this, which I'm going to say. So one of the things is that these so we're just looking at the Lorentz subgroup. Of course, if you're looking at flat space in, say, 4 dimensions, you also have four translations that have to be included in the game. And we could ask what translations do here. And for me, at least, it does something a little unnatural. In a sense that if you translate it, the weight of these operators O shift. Okay, this is a very straightforward thing that you can look at. And this is just the Hamiltonian. The other P's will also have the same thing. I say we find this feature unattractive. Maybe I should say I find this feature unattractive. And also the Mellin transformation as it stands is singular. These yields diverging results, for example, for the 4-point graviton amplitude in 4D bulk. All right. So another thing that I find, not so nice is if you started off with ADS and took an infinite radius limit, you're going to get to flat space. I would expect that you should be able to get at least some features of this from the flat limit. So Q1 is that the field, the bulk theory, for example, if you took a limit from ADS 5 goes to flat space 5. That does not go down, down in sort of dimensions, right? So it's also very unlikely that the dual field theory will also do the same. Again, as I said, these are things that I don't like, maybe somebody else does. So I would prefer to have something which is a codimension 1, which is more in tune with usual sort of holography and not a codimension 2. Shomik doesn't like that. Yes, absolutely. Because the next slide is going to be your work. So if you're going to kill me, you're going to kill yourself. But please go ahead.
No. So what I'm saying is that okay, that thing is fine. So you can have a 3-dimensional in the acid. Well, first of all, it is when you take the flat space limit, it's mostly kinematics. So not exactly. True. But the thing is that what actually, in fact, if you look at Siddharth's talk, actually, so. Siraj and this they also, and the original idea of relating the S matrix to a 2-dimensional rather than a. So also actually it is very clear from Siddharth, I don't know if he mentioned this inverse LSZ. Okay, where you express the Green's function, bulk Green's function with all the external x taken to infinity as a Fourier transformation of the S matrix, and that actually localizes on the sphere. So the thing is that if you start from the scattering amplitude in the bulk, and if you believe that those are the only observables, which in a sense it is true. Even you can deal black holes as metastable states and all these things, but blah blah blah. But the thing is that it's a fact that this 2-dimension is a and the reflection.
I'll give you an example. I'll give you an example where
the reflection of that actually, where do you see the reflection? Is that you have not introduced it.
Yeah. So what I'm saying is that I could give you an example where it should not work. If you have a sort of time dependent thing in the bulk, suppose there are two states. So if there are 2 high energy states that go in, form a black hole, and you have something else that sort of scatters off the black hole, your two-dimensional theory will not be able to get that for sure.
So I am guilty as charged, but the thing is that the point is that the 3-dimensional theory, at least if you just talk about the S matrix, okay, the U direction, the null direction is sort of decouples in the sense that if you take the OPE, then you don't have a singularity in the null direction.
I agree with you on that, but I'm saying that if you put the U equal to 0,
you can introduce.
So it is up to the chair now. You and I could just go on having this debate, and I'm not. So just
Samik, please get into the organizer mode, I would say.
but just to sort of answer one thing, you'll have to give me five minutes for this. So the thing that the thing that I do not agree with in the OPE is if you set something equal to 0, you might miss poles which were there in the other sort of directions. This, for example, is something that we know happens in the D equal to 3 game that Daniel was saying.
Okay. So please.
So it's now up to the chair.
Yeah. So that's why I'm asking him to get into organizer mode. Actually, suddenly he got into the academics mode. So don't forget that you are the organizers.
Right. So internal feuds aside, what I'm going to be saying now is actually his work, right? So let's do this. So what I'm saying, so what I would propose is that if you sort of keep track of the U direction in stripe plus minus, you get to solve some issues that I just sort of flashed. And as I said, Soumik Banerjee is up here. So if you have anything, blame him. Okay. So what are we doing? So not what are we doing? What he did was he started off with these particular operators which were at U equal to 0, if you wish, the Z bar, and translated them to an arbitrary U. So in that case, there is, if you sort of look at how I re-express these in terms of these creation and annihilation operators, there is a crucial exponential IU term that appears here. What this does is nice. What I tried to say before is when you try to translate these operators, there are shifts in the weights. But now if you translate these operators, these transform in a nice way, okay? The weights don't shift anymore. So I hope, modulo the internal feuds that we are having here, this is clear, right? So this is one of the main messages that I wanted to give. So this transforms nicely under translations. What we had seen earlier, now let's go back to what the field theory is. So yes, sure. No, the shift is just this. So what we'll be able to see is from the field theory, we have a way of understanding what these things are. So that's my next slide. So let me maybe clear that up. So these are the transformations you get from these objects out here. So the celestial ones did the first line, but they had shifted weights in the next line. So if I can take you back. So you see translations shifted these weights. Okay. Now translations do not shift weights anymore. This HH bar stays HH bar. Okay. What we had done earlier in 16 is that we had looked at the algebra and we had looked at some vector field representations. We had labeled these operators under L0 and L0 bar, and we had imposed highest weights. Now the highest weights, this part is something that you have you know and love. But there is something extra that we imposed back in the day. Okay, so that was MRS acting on phi equal to 0. And if you look at the transformation rules of these primary fields, then you get these. It's again a straightforward read off. The fun part is whatever we got here in 16 is the same thing so the infinitesimal version of this is the same thing. So the stuff that we are looking at are these primaries, but now instead of two-dimensional CFT primaries, these are three-dimensional CCFT primaries. Okay. All right, very good. So now what you can do is you can reformulate this, and now what happens is if you started off with the S matrix and you did the modified Mellon transformation, what you get are endpoint functions of primary fields, but again, as I said, in the three-dimensional field theory, not in the two-dimensional one. So this now is a proposal for a codimension 1 bulk dual. And so again, Soumik and friends showed that the Mellon transformations are also finite from the view of the 4D bulk. So this is the basic premise of what we want to do. So the Poincaré group in 4D AFS acts as a three-dimensional Carolian conformal group at null infinity. So we now use the whole structure. It's not only a subgroup, but the whole structure. And then, so three-dimensional endpoint functions are going to be related to the bulk amplitudes by this Mellon transformation, and this modified Mellon transformation yields finite bulk amplitudes as well. Okay. So that was the basic premise. So what have we solved? Well, I mean, again, in my eyes, so we have a co-dimension 1 dual. It doesn't suddenly reduce in dimensions, as you said, the cosmological constant to 0. The null direction plays an important role in the, on the boundary. We have fields that transform nicely with respect to the whole of the group and not only a subgroup. As I try to mention again and again, translations now do not change the weights of the operators. Okay. Good. So how am I doing on time? 10 minutes. Now this is a crucial juncture. So since Mrityunjay already told you about ultra-local 2-point functions, let's see. So let's do a very quick check. We can start off with what the ward identities give you. And so as Mrityunjay already flashed, there is one piece which looks like a CFT piece. This is something we've got back in the day. But there is also another one. If you solve the ward identities, you will end up with something which is like a delta function. Okay. So this is something that you're going to get. And a priori this looks bad, and this is not something we want. But lo and behold, if you started off with the 2-point function in the bulk, scattering is of course trivial. Things just go through. So if we just do it in our earlier way of doing things, so then the modified Mellon transformation of the 2-point function, just follow your nose. What you're going to be ending up with is actually this ultra-local stuff that you had from the boundary theory. So the fun part is that it seems that the peculiarities of this weird branch are exactly what are required to link up to scattering amplitudes in the bulk of Minkowski spacetimes. This I think is your sentence, right? Yes. So that's his sentence. I should write Shomik there. Okay. Good. So there is an example of a massless scalar that you can do, and this is, for example, an explicit example where you can get these things to show that the features can be found in all. A lot of these theories, which are these electric theories. There's a question back there: should I take it or should I postpone it? Chair is being hard, so let's do it after the talk. Thank you. All right. So question is, so I said that AFS, asymptotically flat spacetimes in D plus 1 are these weird field theories, but it's a codimension 1 game. So I have spoken about the intrinsic approach so far. I didn't show the 3-point function, but I can. But the 3-point function, I'm being unfair, but the 3-point function is an analysis. No, that's not fair. So I'll get an extra 5. But the 3-point analysis is something that we can do. So I think I said something about it here. See, there are more interesting non-zero 3-point functions which also have been matched between the boundary and bulk. I didn't show it because I have a lot else to show, unfortunately. All right. So this is usually the place where I have to stop. But thanks to my previous speakers, I can do a little better. So what we have done is we have so far looked at the intrinsic approach to flat space holography. But what happens to the limit of ADS CFT? And now we actually have been able to do some interesting work out here, and that's more, So there are also other things which are going on, but let me give you very briefly what we did here, okay? So what we do is, I mean, excuse the slide. This is an unattractive slide, but we start off, but it's a simple one. We start off with embedding space, and we sort of parameterize these, I mean, x's like the way that I've shown you. So you can write down the areas, I mean, metric here. And what happens is in this way, the boundary of areas is approached when this rho goes to pi over 2. So you can figure out what the, I mean, boundary of the above is. And these, I mean, coordinates p plus, p minus, and yeah, I mean, pi are this way. And you can figure out what the metric on the CFT is. And you know, this is just flat. Okay? Now what we want to do is we want to take a flat space limit. Okay? So in the flat space limit is you just, I mean, redefine rho as r over big R, tau as, I mean, tau over R, and you take R goes to infinity, and it's a straightforward exercise to see that what you had here just goes over to flat space. Now the rest of this is going to be, you know, something that we were inspired by these authors here. And what we now want to do is, you know, as opposed to these authors, we also want to keep very careful track of what's happening to the null direction. So we will start off with, I mean, retarded, I mean, time t of u t subtracted from R. And now, as we reach the, I mean, boundary as rho goes to, I mean, pi over 2, what you see is that u just goes to something like this, which means that the point at the boundary tau p has this, I mean, pi over 2 factor, but you would also have a u over r piece. And it's crucial that you keep this u over r piece because there are going to be some u, I mean, r pieces which are also going to appear, multiplying which you're going to get answers which will have non-trivial u's in them, okay? So as a sort of sanity check, you can insert this into the boundary metric, and as you take r goes to infinity, you get this 0 in front of the u squared. So of course, this is straightforward. So what we do is, there are 2 points here. So what we are going to be doing is we are going to be inserting the boundary field theory operators at slices which are tau equal to, I mean, plus minus pi over 2, but crucially a band which is u over r as well, okay? And yeah, so we will also see that these guys are going to be identified. So this is going to lead to a, I mean, codimension 1, I mean, sort of boundary dual, and we will see that I mean, modified Mellon transformation naturally emerges from ADS within diagrams. So how many minutes? 2, 3, 2. Okay. So these are in a sense the two approaches, if you wish. So if you keep this band, you are going to, I mean, you know, see the whole of scry. But what these guys did earlier is that they neglected the u over r, and hence they didn't get a, I mean, codimension 1, but a codimension 2 stuff. Okay. So this is a slide because I knew that I was not going to be able to go into the details of it. So what happens is, if you look at, I mean, the Witten diagrams, they're different pieces, and you take this limit, then what you end up with is the, I mean, ADS bulk to boundary propagators actually give you the, I mean, Carroll primary wave functions. The bulk to bulk gives you the, I mean, Feynman propagator. The ADS vertices go into the flat space vertices. The ADS Witten diagrams naturally go into the scattering in this modified Mellon basis, and hence the dual CFT now would go into 3-dimensional, I mean, Carroll CFT endpoint functions. But again, what I'm trying to stress is that it's in the same number of dimensions. Okay. So I will now, since I am out of time, just go ahead and not do this. So we were trying to show all of this to you, but let me just completely go ahead. Okay. So let me wrap up now. So this is something that you can do in all its glory or its gory, if you wish, and you can look at several spinning diagrams and whatnot, 2 points, 3 points, 4 points. I mean, you know, take your pick. But so what have we learned? So we have seen that these I mean, Carolian physics emerges in this vanishing speed of light of Lorentzian physics. We have also seen that these symmetries are naturally associated with null surfaces like the boundary of asymptotic flat spacetimes. So these CFTs defined on these null surfaces hence will be naturally natural holographic duals of asymptotic flat spacetimes as they inherit the symmetries of the bulk theory. And in the talk in the morning, you saw that there's been quite a lot of, evidence gathered, especially in the duality between the 3D flat space and the 2D, Carroll CFTs. In a 4D case, we saw that the celestial approach has, to my mind, some drawbacks. And what we could do is we could keep track of the null directions to resolve some of these issues, and ended up with naturally three-dimensional, versions of a dual theory. And yeah, so that's the main message. And I will just to take half a minute to actually look at what's up in the immediate future. We want to figure out what an explicit concrete duality pair is. This is, for example, would you be able to take the limit of ADS4 CFT3? Can you do the same thing for ADS4, ADS5 CFT4? So we also want to link up to string theory, and there are indications that the null strings will play an important role. So I refer you to the poster sessions where Sachin is going to speak about some stuff that we are trying to do about null strings, Gross-Mende, and scattering amplitudes, which I hope will be out soon. But also, we want to figure out black holes, and that's something that we will, if you are interested in this, please feel free to ask me later. But I will, in view of the time, stop and thank you for listening.
Thanks a lot. So one very short question.
Very quick question. Thanks a lot, Arjun.
Yeah.
So do I understand that the following is true? Take the S matrix in flat space,
Yes.
send it through your modified Mellon transform, get the relevant object.
Yes.
If the S matrix in flat space is Poincare invariant, then your modified object has your Carolian symmetry.
Yes, because these are the same. These are the same sort of symmetries on both sides. So in a sense, we are not doing much, but it's just realizing it in one dimension.
No,
Yes.
so this is true, right?
Yes.
So then any string compactification, what have you, that has a well-defined S matrix will get this symmetry. The question really is there a microscopic theory that
Yes, this in a sense is just rewriting, if you will. Now, can we get an explicit example of something, which is what we are trying to build up to?
Okay.
Yes.
Okay. Thank you.
Okay, thanks Arjun for your very nice talk. Okay, so we have final year of this session. Abhiram would be talking about some rethinking of complex multiplication. So let's welcome him for his talk. Okay, Abhiram, floor is yours. Thank you.
Hands are tired. Hoping the handovers.
Okay. So no, let's leave it like this. I think this is fine because it's too small to see them back. What's going on? It's fine. Yeah, it's okay. I mean, I don't care about the color too much. No, it's okay. I mean, like the only thing that's on the top are the titles, and I'm happy to read the titles. I can't see anything in the back. It's okay. Okay, so oh, someone took my bottle away. Thank you. Okay, so thank you, everyone. Let me just ask show of hands, how many of you are really, really hungry and want me to end this very quickly? No, I'm going to, oh, there's one, honesty. I like this. So I'm going to talk to you about a title that is kind of a bit bizarre, but actually first, let me thank the organizers for inviting me here, and I'm very happy to be here and talk about something that I've been thinking about for the last few years. And it has to do with this odd set of words, complex multiplication. So complex multiplication is, as the name suggests, nothing to do with multiplication of complex numbers. So if you were to go on Google and ask, well, what is complex multiplication? Most likely with the new AI stuff, you're going to find that you have two complex numbers, you multiply them together. But I already given a key of what actually complex multiplication is, and it has to do something with that figure over there. So before I start, I need to show some legal stuff. Okay, so parts of this talk are works which I did in the past with Taizan Watari and Masaki Okada, who are both in IPMU in Japan, and in sort of two papers. Some parts of the talk are work in progress, and some parts of the talk are computational, which is ongoing, parts of it with the LMFDB, part of it with the Calabi-Yau cluster, and most of the talk is going to be very introductory. So I thought, well, if I'm going to talk about a topic which is very abstract, let me keep it basic. So I'm going to answer 4 questions, mostly 3 questions due to lack of time. What exactly is complex multiplication? How is it relevant in string theory, which we'll come to in the very end? And why we need to revisit complex multiplication a bit carefully. So my motivation to do this is purely mathematical, and this talk is something I usually give to an audience of mathematicians, arithmetic geometers, number theorists over 2-3 hours, because I use a blackboard. So this is a bit of a challenge for me to do this all in half an hour. So I'm going to start very, very simple. So this actually, I'm honestly not joking. This is lifted from a CBSE grade 6 question, which I fact-checked yesterday, which is, if you draw a circle using you draw a circle of any size that you like, and using only a compass and an unmarked ruler, I ask you if you can divide the circle into some number of parts, right? So show of hands, can you, in a finite number of steps, divide a circle into 2 parts, 2 identical parts, using only a compass and a straight edge? Yes, no. How many of you say yes? Okay, some of you say yes, very good. I like the audience interaction here. And what about 4 parts? Show of hands. Yes, I will come to this too. And what about 7 parts? How many of you say yes? No one, okay. And why is the question that we're going to answer here. And the question that I want to ask in general is, for what n can you divide a circle into n identical parts using a ruler and compass alone in a finite number of steps? Or as the gentleman in the front said, and what about using origami methods? Actually, this is a very simple question that you can ask yourselves, but at the heart of it is actually a beautiful mathematical theory which leads you into something called cyclotomic fields, geometric quadratic extensions, Galois theory, and geometry of numbers. So I'm going to define what a constructible number is. A number n, a number x, which is in Rn, is said to be constructible if and only if all xi in R can be marked using a ruler and a compass. And if x is a constructible number, then actually you can convince yourselves that so is the square root of x, okay? So the question that I asked you in the beginning was, if I give you a circle, for what n can you dissect it into n identical parts? That is, when are the dots, the red dots, actually representing constructible numbers, which actually you can formulate as for what values of cosine of q times pi are actually constructible. So dividing a circle into n equal parts is actually asking which regular n-gons actually are constructible. And it actually gives you these constructive numbers, the series which you can actually find on the OAIS. And this actually has to do with the fact that this is a theorem, which actually I think is due to Gauss, that a regular n-gon is constructible if and only if n is basically 2 to some power r, positive power r, non-negative power r, times p1, p2, p3, where p1, p2 are all distinct choices of something called Fermat primes. So Fermat primes are primes to the form 2 to the alpha plus 1. Okay? And interestingly, the field of constructible numbers is the smallest subfield, right? It is an abelian group on the multiplication addition, however you want to define it, of C that is closed under taking square roots. So if you take square root of constructible numbers, you're going to get constructible numbers themselves. And in fact, if you take B and C to be constructible numbers, the roots of the quadratic equation x squared plus bx plus c are also going to be constructible. This means that any finite extension of Q, well, if you don't know what Galois theory is, don't worry about it, means that if you can extend F over Q as a vector space, then this is going to have dimension 2 to some power, right? And this actually leads you to something very, very profound that we're going to start appreciating in just a bit. That is that a number is constructible if and only if Q adjoint A is contained in a field that is in some sense Galois over Q. And the dimension of this Galois group is 2 to the A. I think 2 to some power. Okay? So you can ask, why am I going to all of this? Because then here comes a very important corollary, which tells you that, well, I gave you a representation of dots in a circle, so you want to ask about nth roots of unity now. So if you let zeta n be the nth root of unity, then similarly as before, Q's adjoint zeta n over Q is Galois, and the size of this Galois group actually is a power of 2 if and only if n is the same kind of number that we saw earlier, that is for which n is actually a constructible number. So this was a remarkable result that actually goes back to Euler and Gauss that led to the theory of geometry of numbers. And the theory of geometry of numbers actually is relevant in a lot of physics that people do. In fact, in the study of BPS black hole indices, there are these objects which actually are being used quite interestingly. And there was a question about what happens if you can use origami methods. Well, it's a slightly different n, but in this case, n is 2 to the a times 3 to the b times, again, a certain set of primes called Pierpont primes, which are 2 to the a plus 3 to the b plus 1. So only then can you divide a circle into n identical parts. Right? So this actually is a very interesting question that you can pose to a 6th grader, but behind it lies a very beautiful and deep mathematical structure. So all of this is quite nice. I asked you a question about dissecting a circle. A circle is rather boring. It's a one periodic variety in R2. So what about doubly periodic functions, right? I want to consider doubly periodic variety. So what is a doubly periodic variety in R2, right? There are two of them I can think of. The first one, of course, is the ellipse, which tells you that it's the locus of all points whose sums of distances from two distinct points actually are constant. And the ellipse is kind of nice, but I actually want to go the historical route, so I'm going to talk about the other doubly periodic object. And this is known as the lemniscat, right? So the title of this slide is Doubly Periodic Functions. The lemniscat is the locus of all points whose product of distances from two focal points is a constant, right? So it's not the sum, but rather the product. And it has this very beautiful kind of shape, and you want to ask the question, when can I divide this into equal parts in perimeter? Then same as before, you can actually, the only difference here is that in the previous case, you were trying to look at roots of unity, and this point you have to look at something called the ring of Gaussian integers, which is basically a set of numbers a plus ib, where a and b are both integers. And a very famous theorem of Abel, which was given to him, I think, in a problem by Fagnano, is that a lemniscat is divisible into n equal parts in perimeter using a compass and ruler, if and only if n, again, is of the form as before, 2 to the a times product of distinct Fermat primes. And there is a bit of a subtlety here that you have to think of zi over nzi as a Galois group, and to do this you actually need to motivate the theory of modular forms and modular functions, but we don't want to do it. We just want to understand that there is something beautiful going on here where you just try to divide this figure into n equal parts. Okay? No, these are constant in perimeter, equal parts in perimeter. I'm not talking about area right now.
Equal parts in perimeter?
Equal parts in perimeter.
But is that unique because you have a bifurcation point, so if one can go
I'm
around?
coming to the bifurcation point now.
Okay, thank you.
I think I understand your question. I'm not going to answer your question because in the lieu of time, but there is some subtlety with the bifurcation point, you're correct. So exactly as you try to compute the perimeter of a circle, you can use the circumference law, but there is no such law for ellipses and for lemniscates. You have to actually use the arc length formula. And the lemniscatic integral, which computes the arc length formula, actually has a very interesting thing. It has a branch point, and at this particular value of r tends to IR goes to IR, you actually have a multiplication law. And this multiplication law kind of is very interesting because you start off with something that actually is given by a rational equation, but now you have an endomorphism. S of IR0 goes to I times SR0. It has an endomorphism, but this endomorphism is no longer valued over the field in which it was defined. So you start off with something rational, but it's got something that is not in the rationals anymore. And at the end of it, you might think, okay, it's just got some scaling by R. But no, this actually is very remarkable, because who ordered this is what you should be asking. And this is the earliest observation of something called complex multiplication. So we want to go into something slightly more complicated than this today, not just for ellipses and lemniscates, but something more complicated, like elliptic curves and Calabi-Yau and K3 surfaces. So I should also tell you that the result actually holds analogously for the case of ellipses too. So this is why I'm not talking about ellipses today. So we now have first steps in complex multiplication. So again, we're going to go back to high school mathematics. We're going to start with the work of Gauss and Lagrange on positive definite binary quadratic forms. So this is something that you all studied in school. So I have a quadratic form, which is ax squared plus bxy plus cy squared. And I set a and c to be greater than 0. And if I require that d is the discriminant, which is b squared minus 4ac is less than 0, then what happens is that this quadratic form is used to express, can represent positive integers, right? And I tell you that the discriminant is fundamental if it is either 0 or 1 modulo 4. And you can find the set of all the fundamental discriminants. And what was very interesting back then was that Gauss and Lagrange were playing with what the action of the SL2 group or any GL2 group on binary quadratic forms are. And they actually found that if you send Q goes to, do I have some pointer here? If I have Q goes to Q prime, where Q is ax plus by, comma cx plus dy, as before over here, x goes to ax plus by, y goes to cx plus dy, such that AD minus BC is 1, meaning ABCD form an SL2Z matrix, then they observe, you can actually check this for yourself, that the discriminant actually stays invariant. This means that binary quadratic forms can be composed by actually just acting on it by SL2Z. And this is actually something that was discovered by Gauss. This is something called as Gauss composition of quadratic forms. And interestingly, there is a law for this even for the case of cubic forms. So this was discovered by Manjul Bhargava, something for which he actually won the Fields Medal. So for a fixed discriminant, if I fix D over here, how many orbits actually are there? And this is a question that you can ask. Are there only one orbit? Can all the quadratic forms be generated for a given discriminant just by applying SL2Z on each other? Or do I have inequivalent quadratic forms of the same discriminant? And Gauss suggested and actually proved that the number of inequivalent orbits, which is known as the class number of the discriminant D, actually is finite. And actually this class number has generating function for quadratic forms has deep ties to the theory of mock modular forms, and they appeared in Boris's talk. I don't know if they actually appeared explicitly, but they're kinds of modular forms which also appear in the kind of things that Boris mentioned yesterday. And Gauss conjectured that this number is equals to 1 if and only if D is these finite many values. And this is kind of interesting over here because you only have these particular values, so I want to keep some of these things in mind. In particular, 163 is going to be quite nice because we'll do an example with 163 later on. So more modern formalism of complex multiplication is that this is a bit more technical, so if there are any mathematically oriented people in the audience, this is for you. It's like 1 minute for you guys. So if you consider a ring of integers in an imaginary quadratic field, and if you take the ring of integers to be z plus z squared of d over 2, then the binary quadratic form is basically given by this particular norm, quotient out by this particular quotient. You take an ideal that is non-zero with a particular given basis, and the quadratic form is given by this particular expression here. And the SL2Z orbit of the binary quadratic form depends only on the choice of the ideal class. And the class number is given in terms of this ideal class group, that is the size of this ideal class group. And in particular, if this guy is supposed to be 1, then it means that any ideal that you choose is going to be principal, meaning that every ideal of this particular form here is generated only by one element. And this you can convince yourself this is quite nice because if you consider a ring of integers in any imaginary quadratic field, then if you take, for example, let's say the case where d equals minus 20, you know this is not a universal factorization domain, so it cannot be a principal ideal. Unique factorization, not unique factorization domain, because 6 can be decomposed in 2 different ways. It doesn't have only one decomposition. If you look at the space of integers, all integers can be decomposed into prime decompositions in a very unique way. Whereas here, if you go to a larger field or larger ring of integers, you do not have unique factorization. So this guy cannot be equals to 1. In fact, the homework for you would be to compute what this actually is. Okay? So this is kind of interesting because we want to keep this in mind, that so far we started off with something very simple, which was talking about like how to find, how to divide a circle into equal parts. And now we start off with something which is quadratic, binary quadratic forms. And this has something to do with basically, and the problem here was to find out when, for imaginary quadratic fields, the set of binary quadratic forms actually have size 1 orbit. And these two actually are going to be related to one another. So this section of the talk is slightly more, this is where I think I start off a little bit more into complex multiplication. So this is a program that I've sort of been working on, not for the case of elliptic curves, but more generically to develop methods to study geometry and automorphic properties of something called, and from Galois theory, basically. And this is a tinier part of a very, very large program in modern mathematics. And this program actually goes by the name of something called the Langlands program, which conjectures that every motivic L function actually is automorphic. And the properties of this L function are deeply tied to how complex multiplication can be described. So today I want to describe a subprogram within this, which I think also has very interesting application of string theory, which is how complex multiplication will start to come in. So complex multiplication for me is, personally, it's a very beautiful mathematical phenomenon in which several facets of an algebraic manifold or an algebraic variety actually are delicately linked together. And these facets actually include arithmetic in terms of L functions and zeta functions, geometry, that is Hodge theory, endomorphism algebras, Galois representations, differential equations, and periods. And all these objects come together and they talk to each other very, very beautifully when you have something with complex multiplication. And in fact, this is one of the reasons, not a lot of these relations were not known when Hilbert was around, but several relations were known, and Hilbert actually remarked that the theory of complex multiplication is not only the most beautiful part of mathematics, but the whole of science. And this is something, a sentiment which I actually share quite well. And today the philosophy that I kind of want to share, which I might not even get to because of time constraints, is that it's a mathematical phenomenon in which if you take an algebraic variety, which means just a manifold expressed by a set of polynomial equations of some dimension d, it tries to behave arithmetically. What that means is that I will tell you a bit later, as if it had a smaller dimension than it actually was. So it tries to behave as a d prime dimensional arithmetic object where d prime is between 1 and d. So today the varieties that we're going to be considering are so-called Calabi-Yau manifolds, and there are very different ways to define what a Calabi-Yau manifold actually is. So for me, a Calabi-Yau manifold is simply a smooth variety of complex dimension d over some algebraic field k, and such that it's simply connected and its canonical bundle is trivial. This basically means by Yau's theorem that it is a Ricci flat manifold. So I don't want to go through the list of all Calabi-Yau manifolds, but just to give you some of these things. The simplest case is the one which you're going to omit today. It's just 2 points or a finite set of points over the line P1. We're going to start with elliptic curves, which is the first one-dimensional Calabi-Yau variety. At 2 dimensions, you've got K3 surfaces and T4, which are basically 2-dimensional abelian varieties. In 3 dimensions, you've got K3 surfaces times with a product of an elliptic curve or Calabi-Yau threefolds. There are several kinds of Calabi-Yau threefolds. You can have things like toric Calabi-Yaus, local P2s, many different kinds of things, and 3-dimensional abelian varieties. And I kind of want to point out that for the case of abelian varieties, this theory of complex multiplication actually is well known. It's kind of well understood, and there are several books about this. So the string theory results I will tell you today only have to do with abelian varieties, but it kind of also instigates why I should start thinking about these in terms of a Calabi-Yau point of view as well. So for me, an elliptic curve is a smooth projective cubic over field K, meaning it's given by a cubic polynomial equation. It has genus 1, and it has at least one rational point. So for me today, I'm going to talk about K as either Q or I'm going to be talking about C. And this is something that you've all seen when you do a string theory course, that you have a lattice. You quotient out the complex plane by a particular lattice. And basically, similar to the case of binary quadratic forms, there is an SL2Z action, not in the quadratic form, but now rather on this particular object tau, which is the ratio of the 2 periods of the elliptic curve. And you get basically A tau plus B over C tau plus T. And the question which I want to ask right now is, what function do you need to compute the isomorphism classes of these elliptic curves? And So we already saw that basically earlier, that if I is a non-zero ideal, it defines basically a lattice. Well, it's a non-zero integer ideal, so it is a lattice by definition. These lattices have a lot of symmetry, since you can take one ideal and multiply something from itself and from the ring of integers onto itself, meaning that the Hom space of E onto E is basically the ring of integers. So usually for arbitrary lattices, what this means is that if I had this particular lattice over here, the endomorphisms of this particular lattice is basically just scaling it up and down by multiplying it with another complex, with another number, basically. But occasionally what happens is that when an elliptic curve is defined over an imaginary quadratic field, it is basically defined over an ideal from an imaginary quadratic field, there are many more such maps you can actually consider. What this means is that the lattice no longer just scales, but it can also rotate, basically. And this is what complex multiplication actually does. So such curves in principle where the endomorphism algebra actually again contains an element which is not in the field that is originally defined on, is said to have complex multiplication. And the class number HD are size of isomorphism classes such that you have complex multiplication by the ring of integers given by z plus square root of minus d. And this is kind of fun. So if you knew how to compute the J invariant, which comes from theory of modular forms, this is where I'm coming in right now. So you can also have the following question, which is that given an elliptic curve over Q, which is a smooth projected curve of genus 1, you want to ask, how do I embed this into P2? And the map here is given by something known as the Weierstrass equation, which is this expression over here. This is something standard in the theory of elliptic functions. And I don't know if it's there in string theory textbooks, but it's a very common function that you study when you study elliptic functions, where G2 is a function which is given by this particular lattice sum over here, is weighted by -4, and G3 over here is weighted by -6. And you can construct the so-called discriminant function over here, which is basically G2 cubed minus 27 G3 square. And to the untrained eye, basically you realize that this actually is something that uniformizes the holomorphic Eisenstein series. So G2 is basically something that uniformizes the weight 4 holomorphic Eisenstein series. G3 uniformizes the weight 6 holomorphic Eisenstein series. And delta uniformizes the weight 12 Cutts form, which is the 24th power of the Dedekind eta function, which appeared today in Daniel's talk. So from this, you can actually construct a function, which is 12 G2 cubed over delta, which basically is roughly E4 cubed over delta. And this is something that does not depend on the lattice scaling at all, because this goes as something 6, this goes as something 6. They cancel each other out, and therefore this scaling doesn't depend on the lattice at all. And this guy is going to be an invariant of the isomorphism class of the elliptic curve. So this we call the J invariant. So meaning that if you took your elliptic curve, you computed its periods, and you computed what tau the elliptic curve actually has, and you plug it into the expression for the J function, which is something that I'm pretty sure exists in string theory as the hop module, or something that does the generating function for weight 0 modular functions, then you actually will get the value of this particular object over here. Now for elliptic curves which have complex multiplication, this J guy actually is a number. It's an algebraic integer. And when we take the elliptic curve over Q, this guy actually is going to be an integer. So this is kind of bizarre, because the J function is a modular form. The modular function is a transcendental function. And at values of other algebraic or even transcendental numbers, a transcendental number valued at a transcendental value actually has an algebraic or even integer number as an output. Okay? So this is kind of interesting. So because when you actually go back and look at the same discriminants that you had earlier, and you compute the J function, you actually see that these guys actually are integer. So this kind of is one of the beautiful things about complex multiplication is it's taken an object, an elliptic curve, you've constructed an invariant of this object, which is given by a transcendental function. You value this transcendental function at another transcendental number, or an irrational number, and then what you get out is going to be an integer. Right? So this is really, really remarkable in mathematics. Oops, what happened here? And this fits into a larger part of something known as Hilbert's 12th problem. So the title here is supposed to read Hilbert's 12th problem, which tells, it actually goes by a different name known as the Kroneker's Jugendraum, which asks you to find all abelian extensions of arbitrary number fields by adjoining to it special values of transcendental functions. Right? We had the first case earlier, which is you generate a so-called cyclotomic field, which you adjoin to Q the roots of unity, and you form the very nice abelian extension that is a real quadratic fields. For the case of imaginary quadratic fields, the theory of complex multiplication, it gives you a finite abelian extension where you adjoin to it the algebraic values of the J function, the Weierstrass P function, and other roots of unity. Where the Weierstrass P function, I think, again, is something you might have seen before. It's a solution to this particular equation over here. Okay? And another step to go forward is to actually not look at just these endomorphism algebras, but actually do some actual computation to look at the zeta functions. So the title here is supposed to be zeta functions and complex multiplication. So if I take any smooth projective variety, meaning that no singularity is embeddable into projective space, and over Q, meaning that is expressed by polynomial whose coefficients are all rational, then the number of points over Q is basically what I'm interested in. I'm counting the number of rational solutions of this particular curve over some finite field, where finite field basically means the set of all numbers in Z over PZ, where P is a particular prime. And this is a field of characteristic P. So local zeta function has this very beautiful definition over here. So if you know it, you know it. If you don't know it, it's a beautiful place to go and start learning something about the zeta functions. And a very interesting thing, which was proven by Dwork, which is actually conjectured by André Wey, is that these polynomials, P's, are actually rational polynomials in T. And the degree of the polynomial is given by the ith Betti number. That is the dimension of the ith cohomology of your variety X. So for an elliptic curve, basically, this simplifies quite a lot. And your zeta function looks basically as 1 minus AP times t plus pt squared. The denominator is a bit boring for the case of elliptic curves. For any odd dimensional varieties, the denominators are boring. For even dimensional varieties, the numerators are boring. So you have this guy over here. And these APs are very, very interesting because they actually tell you how to find the number of rational points on an elliptic curve modulo prime. So this is why zeta functions are so important. They actually tell you how to compute the number of solutions to basically equations which you are not sure if they can be solvable completely Diophantine-wise. Okay? And if you were to look at this in terms of, for example, the Riemann zeta function and trying to bridge some analog, these APs would be the analogs of basically how the Riemann zeta function predicts the location of primes on the prime counting function. So these APs are quite interesting. They're computable also from Galois theory of Galois representation attached to elliptic curves. And there's a very profound result in mathematics called the Sato-Tate conjecture, or now it's called the Sato-Tate theorem, which tells you that via the Chebotarev density theorem, the conjugacy classes of these Galois representations usually are equidistributed with respect to the Haar group, or Haar measure of some compact Lie group. That compact Lie group is something known as the Sato-Tate group, and the Galois representations actually map onto the conjugacy classes of these Lie groups. And this is kind of interesting because it tells you something very, very profound. And if you were to sit down and compute the Sato-Tate group for all these elliptic curves, if the curve has complex multiplication, the Sato-Tate group actually is abelian. And this you can see directly because it reflects as a change in the structure of the zeta function itself. So now, for the case of complex multiplication of elliptic curves, you have about 7 different ways in which you can definitively define what it means to be complex multiplication. The first one is something you saw. The endomorphism algebra is larger than the field over which is defined. The J invariant is a rational integer. The Sato-Tate group is abelian. In fact, there are about 4 more definitions which I didn't tell you about. That the Mumford group is abelian. There's a split of the Hall structure, with each Hall structure being complex multiplication itself. The Galois representation actually factorizes, so it's got a 2-dimensional representation. It factorizes into GL1 representations. And so GL1 representations here meaning 1-dimensional modular forms is what I call it. And around 50% of the traces of Frobenius, the APs actually vanish for different primes. So these are all good definitions of complex multiplication for elliptic curves. But how many of these properties actually do generalize? And this is kind of difficult to do because it's not easy to compute the endomorphism algebra straightforward. You don't really know if you have a Kronecker Jugendstrom-like phenomenon. I'll finish, I'm done. The Sato-Tate group actually is abelian. All these guys here are actually computable. Right? So anything between 3 and 8 over here is something which actually can compute and use in some sense to define what complex multiplication is. So in the last, maybe I have 2 more minutes, I want to tell some string theory about this. So I told you all about this theory of complex multiplication and I motivated this, but what does it actually do for this audience? Why does it arise in string theory? Well, very briefly, the title of this slide is called the attractor conjectures. The attractor variety, I'm going to define these, use the notation of something called attractor varieties, which are Calabi-Yau manifolds whose moduli are solutions to the so-called supergravity n equals to attractor equations. And well, Greg Moore in the 90s was studying rational conformal field theories and these attractor points in the modular space of Calabi-Yaus. And motivated by complex multiplication of elliptic curves, he put forward these conjectures. It's a very nutshell, I'm being very loose here, but this is essentially what the conjecture says, that the period vector is valued in a number field. So you compute the Calabi-Yau period, it should be valued in a number field. And we sort of know a counterexample to this one already. And I call it potential because it relies on algebraic independence of L values. So it's only potential so far. The attractor variety is arithmetic over a number field, and this number field is a Galois extension of some other field. And in the case of attractor varieties being elliptic curves, then the elliptic curves have complex multiplication. And if the attractor varieties are K3 times T2, then the K3 is singular, and the elliptic curve has complex multiplication. In fact, singular K3s also have complex multiplication. And the other one where it appears is in this, the study of rational conformal field theories. So if you take X to be an elliptic curve over C, so that's your target space for string theory. So to me, string theory is just a way in which you can attach to some Calabi-Yau variety, some zeta-graded vertex operator algebra. So if you take X to be an elliptic curve over C, and you take X check to be its mirror, then the vertex algebra associated to X, I don't call CFT because for me CFT also means class field theory, so it's in my own internal head. The vertex algebra associated to X is rational if and only if both X and X check are complex multiplication and they have isomorphic CM fields, meaning the the field by which they have complex multiplication actually is their isomorphic. And again, motivated by work that Greg Moore had done, which tells you that if the elliptic curve has complex multiplication, then the CFT should be rational. Buka and Rafa conjecture that for Calabi-Yau variety X, the zeta-graded vertex algebra is rational if and only if X and X check are complex multiplication type, and the endomorphism of these fields, endomorphism algebra for the fields actually are isomorphic. And this is kind of an interesting thing because there are several things to unpack over here. And what we did, or what I did a couple of years ago, was that to study this conjecture and carefully, also for the case of abelian varieties, and we also already found that for the case of abelian varieties, this is not a sufficient statement. In fact, we actually managed to generalize this a bit more. I'm not going to tell you the full formalism of the statement, but the refined version of the rationality conjecture requires some conditions on what it means to be complex multiplication, what exactly it means to be mirror symmetry, and for the case of SYZ formalism, we actually put forward a refined theorem. So the refined theorem here is that it requires further conditions on complex multiplication and basically what it means to be rationality of abelian varieties. We actually computed this for abelian two-folds, and we gave a conjecture with some self-mirror for self-mirror Calabi-Yaus in the paper. As I'm not going to tell you about this, so please feel free to come and talk to me. And recently, reconstructing the vertex algebra data from complex multiplication, Hodge-theoric data, was actually done in a paper by Hans Jokkers, Puru Kusala, and Mike Sarva. So as a very final remark, I want to tell you that there's not much physics in this talk, but some work in progress is to actually study this for K3. K3 is a bit of a boogeyman in the world of in zeta functions. We have some arithmetic constraints on complex multiplications coming from zeta functions. So something which I'm trying to understand is what the interpretation of the Mumford group and Sartre group actually are. So for this, one has to really go into the theory of motives quite extensively. And there's several interesting complex multiplication-like phenomena that have been observed in Calabi-Yau differential equations. So I think that's something that should be looked into and looking into it as well. And as a final remark, that there's great power in trying to play with numbers. And you can ask if whether a number is an integral of an algebraic or rational polynomial, or is the number a root of a rational polynomial, or is the value of a special or transcendental function. And when you ask these questions, you actually find surprisingly more beautiful mathematical structures behind what you're actually trying to do. So with that, I will stop. Thank you very much.
Okay, so thank you, Abhiram. So one very short question, if there is any. Otherwise, we are ready for lunch. Okay, so let us thank all the speakers of this session and also the morning session for these wonderful talks. And we again get back at, say, 2:45. No? 3, okay, so 3:15.
3:15, 1.5 hours of lunch. Yeah, so we get back at 3:15, right? Yes.
ये 200%. ठीक यार वो टेढ़ा हो गया उसको सीधा कर दो. I think it will come because this is not a very high. Yeah. Oh. Yeah, so nothing higher than that. Just a little bit of it and right. तो 10 कर लेता हूँ
जूम आउट कर लो
हाँ तो 10 करते रहो
दिख रहा है ना टाइटल दिख रहा है ना 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 इसे थोड़ा नीचे करो
थोड़ा नीचे
कैसे वो देखो
ये
हाँ टाइटल हर स्लाइड पे दिख रहा है ना ठीक है
it's yeah it's not there yeah it's fine
Okay, good afternoon. Let's get started because we are running late. So first speaker is Shailesh Lal from BIMSA. He will talk about deep learning. Okay. He will start talking as soon as he gets a microphone. Okay.
Okay. Yeah. Okay. So let me begin by thanking the organizers for giving me the chance to talk about this work here. It's a great pleasure to be back in Khurda Road. The last time I was here, I was 6 months old and in my father's arms. So, yeah. Anyway, so I'll be telling you about some work which we've been doing, which is about how to find new integrable models by deep learning. And if you want the short version, it is that neural networks solve the Yang-Baxter equation to get new results, okay? And so before I start the storytelling, let me show you one thing concrete, which we will come back to at the end of this talk. But so Shiraz, you wanted to see something concrete and non-zero. So this is concrete, but it is definitely zero because these are algebraic varieties. So they define the zero locus of some space. Okay, but yeah, so this is concrete, and the reason why I wanted to show you this before I start, like, you know, talking about how we got here, is because I really want you, like, you know, to remember that at the end of all of that is an expression which you can write down on pen and paper. Okay, so it's not deep learning as some abstract thing that exists in a very high dimensional space. Well, this still does exist in a very high dimensional space, but that's not deep learning's fault. So with that in mind, let me begin by kind of motivating this, this idea. And the point is that, well, we know that quantum integrable systems are kind of ubiquitous. They are tractable. They have some very controlled dynamics, but they do have dynamics. They have phase transitions. And they're, in a sense, they're everywhere, from string theory to quantum computation. And of course, some of the definitive experts in these things are in the audience. So to the experts, I'll say that this is a story. So the first rule of good storytelling is that don't let facts get in the way of a good story. So please bear with me. Yeah. But the really interesting question is that could we, I mean, given the fact that there are these infinite dimensional symmetries, could we just say that, can we determine them uniquely, in a sense, just by on count of symmetry alone? And say, for example, say the CFT bootstrap, right? And appealing as this sounds, I'll show you why, at least naively, this problem is extremely difficult. So just to set the stage, let's think of a quantum spin chain in a sense, the simplest quantum system with many body dynamics. And so this has essentially L sites. It's periodically identified, and the spin degrees of freedom at each site are L-dimensional. Sorry, D-dimensional, right? And so when I talk about D-dimensional Yang-Baxter equations, say, for example, I'm talking about the site dimension. So nothing funky like higher dimensional polyhedra, anything like that. Okay, so standard story, we think of nearest neighbor interactions. So the Hamiltonian acts on the vector space, which is composed by taking products of two nearest neighbor objects, right? This is just standard. And quantum integrability, basically, well, in this context, one definition would be that there is a formally infinite tower of conserved charges that commute with the Hamiltonian. Okay, and one way of, say, deriving these conserved charges, or at least one constructive way, is that we postulate the existence of this object, which is called the R matrix. And I'll be looking at the R matrix in this very special limit, which is R matrices of difference form. And the idea, I'll show you the concrete expressions in a moment, but the idea is that this R matrix is going to encode the Hamiltonian and all the higher charges. Right? So for example, say this is the Hamiltonian. There's an additional constraint which is essentially comes from locality, that R of 0 has a very special value. And the third thing, of course, which is what makes the whole thing hard, is that there's this additional Yang-Baxter equation that we have to impose on R, right? And it turns out that this Yang-Baxter equation is non-trivial on a product of 3 sides, okay? And this means that there are d cubed times d cubed cubic equations in d squared times d square functions. So these are cubic functional equations, okay? Not just polynomial systems by themselves, which are hard enough. So, so here's the equation, and as you can see, it gets more and more and more overdetermined as the dimension increases. So in 2 dimensions, it's quite bad. In 3, it's terrible. That's where we are working, and also 4. And the upshot is that we will like to solve this Yang-Baxter equation by deep learning. Okay, and what I mean by that is that I will use Rij, the Yang-Baxter, the R matrix will be modeled as the output of a neural network, and from that we can extract numerical values of the Hamiltonian. Okay, and from there, how did we get to equations like the one that I showed you right at the beginning? That is part of a very, at least what I think is a very interesting story. So I hope you will share that interest. But before that, let me tell you about why deep learning is so powerful. And the idea is that deep learning in this context, it resolves a very typical lacuna that you might encounter when you're doing numerics in general, but in particular when you're doing numerics for the Yang-Baxter equation. And to see the lacuna, all you have to do is ask that if I wanted to solve this Yang-Baxter equation numerically, what would I do? So if I wanted to say solve, say a crossing equation numerically, what would I do? I would pick a basis, expand in that, and try to constrain the coefficients of the basis, right? The question is what basis to choose. So here's one example. This is the famous XYZ model solved by Baxter, where the R matrix is actually composed of elliptic functions, Jacobi elliptic functions. And there's also a function of function structure that I just want to mention this to you right now. Okay. But if you look at another example, which is essentially a very similar looking Hamiltonian, and this comes from this paper by Marius Deleu and collaborators, and you see that the R matrix now, it looks like a very innocuous change, and the R matrix now is simply just some polynomials or rational functions, right? So even innocuous changes in what kind of ansatz you're looking for mean that what kind of Hamiltonian you're looking for means that typically you would imagine that the ansatz function that you're scanning with has to be changed dramatically, yes? Sorry? This is just enough to, I guess it didn't work, so it was supposed to scare you into thinking that this is non-trivial. But basically, the really important thing, so thanks for that question. There's a mistake, not a mistake, but I want to emphasize this thing to you, that the important thing is that you would have had jx plus jy equal to 2, and jx minus jy equal to delta, and this is the condition for integrability. Okay, and these are, this is essentially this eta and m, and I think w, they are parameterizations of this delta, if you wish. Yes? U is a thing called the spectral parameter. The only thing we need to worry about is that R is going to be holomorphic in U. Okay? So if we need a really powerful ansatz, so here's a really powerful ansatz. So, and this is the idea that neural networks will give us this really powerful ansatz. And the toy example for this is univariate functions over some finite interval. this is going to be very sketchy, but it contains all the important ideas that you need to understand what is going on. Okay, and we know from calculus, whenever you studied it, that if you have this univariate function, you can always discretize it over bins. And then the claim is that if I can construct a neural network which learns, can mimic this discretization, then I'm done, right? Because what I'm saying is that up to some arbitrary precision, I can always learn this function. Is that fine? Okay, so here's a broad brush summary of the proof. The idea is that if you have a neuron, well, you know it can turn on at some threshold point. I can take a difference of two neurons to get an object that turns on at some point and turns off at another point. I can multiply it by a number to raise this bin to any height I want. And then I add up all of those things to get this discretization. So, I mean, rather than show you the algebra, I'm just showing you this plausibility argument, which tells us that any function within, so there are different statements of this theorem depending on what exactly you're trying to prove. But the upshot almost always is that any quote unquote any function can be described by such a neural network. Another reason which is actually, if you wish, later I can tell you about why that first answer is actually a non-answer. But the real reason why this is really important is that this neural network that we choose has actually two layers of neurons rather than one, right? This argument tells us that we need one layer. And the reason why we need two is that because if you imagine that one layer is telling you how to learn a function, then essentially two layers are telling you how to learn the function of a function. Okay? There is like a lot more, like you can fill it out with numbers, you can talk about like sawtooth wave functions and all of those things. But at the heart of it is the idea that this is the kind of structure which enables you to learn efficiently functions of functions. Okay? And finally, the thing to do is, and this is where, I mean, you kind of have to trust me that although the argument that I showed you seemed to rely on saying that, well, you need to know the values of the function that you're trying to mimic. That is not strictly the case. You can just specify these constraints. And the idea is that if you define these as the Yang-Baxter equation and associated identities as some kind of targets for the neural network to satisfy, and then you can always tune the neural network to come quite close to this. Okay? And this is essentially, this is proof by assertion. If you have questions, like please ask me later, because if you ask me right now, it will become proof by intimidation. But it looks like we are good to go, right? Because we have this set of equations we want to solve. I said that the most important difficulty is searching for a proper ansatz class. I gave you an argument to tell you that here's an ansatz class you could try. So it looks like everything is kind of good to go. And this is like the basis of a lot of work that I presented last time at the ISM in Mumbai. And so it's also very satisfying to be able to give this follow-up talk here where we are actually giving new results. There's some slightly misleading notation, but these are all continuous functions of the input parameters. The other thing is that the discrete functions thing is really only a plausibility argument. Okay, so that's why I said don't take it too seriously. But I can give you the robust argument. So it looks like we are good to go, but there's a problem here, which is that AI can fake solutions of the Yang-Baxter equation. I had a slide here which was kind of mocking ChatGPT and saying that it looks like you want to solve the Yang-Baxter equation. That can be surprisingly helpful. Would you like me to list out the possible solutions? And then it gives garbage, but I lost courage. So, okay, but the idea is that AI can fake solutions of the Yang-Baxter equation. And at least it's possible to understand where these solutions can plausibly come from. Okay, and the idea is that, like I said, everything is consistent at face value. Right? You're solving some Yang-Baxter equation with some pattern that you've chosen that these particular entries of the R matrix are non-zero. Fine. And then you solve the Yang-Baxter equation, and then you extract H using this kind of differentiation. And like I will claim to you that this can be done. Right? But in practice, it's disturbingly easy to get fake solutions. Okay. And the source of the fake solutions is, remember, we are trying to look for trying to optimize the Yang-Baxter equation, which basically means we are trying to solve the Yang-Baxter equation up to some possible numerical errors, right? And the problem is that this Yang-Baxter equation, it has this trivial solution, which is that R of 0 is just the permutation operator itself, for which this Yang-Baxter loss function or target potential is just 0, right? That is where the Yang-Baxter equation is satisfied. And now, if I consider neural network outputs, which kind of give me this, this projection operator here, just perturbed by small random functions, okay? Then, as long as these perturbations are just tiny functions in some neighborhood of U, then what I will see is that the Yang-Baxter loss is not 0, but it's approximately 0, right? But because these are some some spikes in a small neighborhood in one place, this has nothing to do with actual solutions, right? But on the face of it, when you stare at it, it'll look like a solution. If you stare a little more, you can quite easily tell that it's not. But remember, we are trying to be as axiomatic as possible, so we don't really want to kind of have to rule this out by hand all the time. And this is where we need a new input, which is essentially that the idea that we have to go back to is that integrability implies the existence of this tower of conserved charges, right? And normally, of course, these are encoded in the R matrix, but there's also an algebraic construction, which essentially determines the R matrix, the Q3 charge by starting with a 4-side spin chain. So this condition is degenerate for any, so if you take a 2-side or a 3-side spin chain, this construction actually gives you some triviality, but for 4 sides, it's non-trivial, and you find that this is an extra condition that your Hamiltonian must satisfy. But on the face of it, it is an independent computation, although it's encoded in the R matrix. But so this will help us rule out false positives. And now we are done. Okay, so now we can run that machine. We can get some numerical Hamiltonians up to some precision, right? 10 to the minus 4. But the problem is that integrability is an exact statement, right? And you need to prove it in closed form. The Yang-Baxter equation being approximately 0 outside of very controlled environments is not really something physically meaningful. But this is where that equation comes to help us again. And what we find is that using that Hamiltonian, this is now just a standard root finding problem that you can put into Mathematica, and you can, in the neighborhood of this function, this value that you found, you can construct multiple precise solutions of Hamiltonians that obey this equation to order 10 to the minus 8. And then you can do some machine learning, but really linear algebra to extract polynomial relations, and what you find is that those polynomial relations have almost integer valued coefficients. So by the state-of-the-art inference technique called 0.51 is equal to 1, you can conclude that these must be integers. But now you can kind of check that whether you're right or not, right? Because these are now formulae that you can plug back into this in Mathematica as symbolic calculations. And you see that this is just identically 0. Okay, so although we started with numerics, at the end what we found is actual analytic expressions. And by the Reshetikhin conjecture, this criterion is actually, if you believe the conjecture, it's already sufficient for integrability. So it's clearly necessary, but Reshetikhin conjectured that it's also sufficient. But we don't have to be lazy. We can even solve for the R matrix. So finally, in the last 3 minutes or whatever, let me tell you about this new story. I don't even know if it's a story or not. And the question is that, is there an algebraic geometry of integrability? So the question is that if you start solving that Q2, Q3 commutator equal to 0, then what kind of algebraic varieties do you get? And like I said, initially, at least in the literature, it was believed that these are all standard linear quadratic type of equations, and it's a bit of a triviality. But if you do this in 3 dimensions, then one of the things that we found is a Hamiltonian that looks like this. So, and this is really the last slide, okay? So, and the question is that what are the algebraic geometry properties of these kind of polynomial relations? Sorry? Yes, spin 1 basis. Okay, so the idea is that we are looking for solutions of this particular equation, and we do have some observations, although we don't have a proof. And obviously, I think if you're looking for a proof, I'm possibly the last person who will provide it to you, but I have smart collaborators. Yeah, so we always find polynomial relations with integer coefficients, and it's enough to help us to solve the full charge conservation equation. Okay, that will give us enough to factorize the polynomial equations so that the remaining parts also become solvable. And this somehow always happens. We don't know why. It also turns out that the Hamiltonians are rational varieties. I don't know what that means, but according to algebraic geometers, this is a really big deal. And we don't know if this is always true. And the question would be that, are there other interesting properties that these polynomials have? Do they define a Calabi-Yau space, or is it Fano? Right? And of course, that would be very interesting, because these are, if we could construct Calabi-Yaus, then they would be Calabi-Yaus that are in a sense twice distinguished. Because one, they are Calabi-Yaus, so they're not generic algebraic varieties, but second, they come from solutions of this particular integrability criterion. And here are the conclusions. I want a gold star for finishing on time, but here are the conclusions, which is that if you use deep learning, but not just deep learning, a lot of analytical inputs as well, you get these about 200 new integrable Hamiltonians in analytic form. And this is important. Otherwise, really, there's no result. But now the question is that, okay, we are physicists, so what are the physical properties of these Hamiltonians? And there are 200 of them, so it's not that easy for me to answer. But more interestingly, what about R matrices of non-difference form? What about, say, S matrices, both in the S matrix bootstrap itself and also, say, a Zamolod-Chekhov bootstrap? What about the algebraic geometry? Are there better ways to denoise this variety in the language of computational algebraic geometry? So all of these questions are there, and we don't really know the answers to most of them, but hopefully there are now interesting starting points to ask these questions and even have enough control to say that, can we find integrable Hamiltonians, say, conditioned on other different properties? And so that's all that I have to say. So thank you for your time.
Thanks, Shailesh, for finishing on time. Are there questions? Yes, Rajesh.
Hi, thanks. So I didn't quite get why were you expecting maybe a Calabi-Yau or some special geometry for?
Yeah, so there isn't really a specific reason. It's just something that one can check, I believe, relatively quickly. And in that sense, it's just kind of like appealing to ask that, can this thing happen at all? So there isn't really an underlying connection. But the idea is that, yeah, if there is, then it would be interesting to see exactly how that happens, because there's an independent definition of these varieties coming from integrability itself, which has nothing to do with Calabi-Yaus. So yeah.
And this thing is you use nearest neighbor Hamiltonians,
yes,
but presumably this can be
generalized. Yeah, this can be extended to certainly next to at least finite distance interactions is possible. The kind of spin chains in string theory where you have genuinely non-local interactions is, I think, still a bridge too far, but we have some, at least there are some now techniques by which we can at least hope to address. Yeah. The other constraint of non-difference form, we are certainly trying to.
Shailesh, Shailesh, so are there any at the very end?
Where?
The back.
Oh.
Are there any continuous redundancies that one has to worry about? Meaning, how do you know that the two Hamiltonians that you get
they are not just
equivalent in some way, let's say by
to,
change of basis, local
right,
change
right,
of
right.
basis,
So,
and if there are redundancies, how do you deal with those?
Right. So, of course, since we are trying to do this on an industrial scale, it's kind of hard to answer this question. But typically, like the slightly slippery idea, which is that either you start with ansatses that you already know and you deform it slightly, or you start with such an extreme ansatz that it's very unlikely that there are that this is related by a similarity transformation to some previously known object. But yeah, in general, like we don't know if like all 200 of them are new or not. Yeah.
I mean, it could be that I mean, first of all, why is there a discrete space of solutions? Because you talk about 200 solutions.
No,
as
it's not a
opposed
discrete.
to
No, it's not in that sense. It's like we did this and we got 200 solutions, but at some point we had to stop. That's all. No, so in the two-dimensional context, there is there are discrete families believed to be 14, which were given in that Marius Deleuze paper. But in 3 dimensions and higher, there is absolutely no knowledge. So
what do you mean by 3 dimensions?
3 side dimensions.
Oh, okay.
Yeah.
Thank you.
Yeah, something small, I guess. So you use just Q2 and Q3.
Yes.
I mean, in effect, you're going to have an infinity of them, right?
So
why do you just need up to Q2?
It's really a necessary condition, but at least if you believe Reshetekin's conjecture, it's sufficient. But more than that, it's enough to fix the Hamiltonian, which is purely two-side, right? So now that you have the Hamiltonian and you solve for the R matrix, say using some standard analytics like small u expansions, even if you can't solve in closed form, you can at least show that to every order in U there's a solution.
So higher in dimensions would require
Yeah, so basically,
more stuff.
yeah, that's why I said that, formally this infinite tower exists. So if you have finite dimensional spin chain, then beyond a certain point, the conditions of the conservation conditions kind of trivialize.
Okay.
So say, for example, the Q3 condition, if I had a 3-dimensional or a 2-dimensional spin chain, it would be trivial.
Nice talk, Shailesh. Just a small curiosity. You mentioned that you can create a function by not even looking at its actual values,
yes,
but instead some constraints. So in general, what are the possible constraints or minimum number of constraints that you have to specify in order to write a function?
The functions typically are so over-parameterized that it's very hard to, I won't be able to give you an honest answer to this question. You really have to check and see. In fact, the architecture that I kind of sketched it out for you, but if I were to blow it up as a really machine learning network, it's kind of so complicated that it's very hard to, it's kind of non-trivial that it worked at all. Okay. Yeah, but on a case-by-case one can answer this.
Okay, let's postpone further questions for the tea break, and thanks Shailesh again.
Thanks, sir.
The next speaker is Akash Jain, and he'll talk about string. When the organizers didn't tell me what the title of the talk is.
I mean, that's my fault. I didn't give it to them.
It's about Schwinger-Feldish formalism and some thermodynamics.
That's close enough.
I'll do that. Okay. Hello? Yeah? Yeah, I think this probably work. All right.
Thank you very much. Thanks the organizers for allowing me the opportunity to speak here, for the invitation. I hadn't been to Bhubaneswar, although not that we are in Bhubaneswar technically speaking, but I love the weather, love the food, and not the least the company. So really glad to be here. For my talk today, I decided to speak about some things that I've been starting to think about in the last maybe month or two with Mark Mazzei at Oxford. Full disclosure, I don't really have any concrete results to show you, Shiraz, unfortunately. You'll have to make do with the formalism for now, which also means that my talk will abruptly end at some point, and I'll just leave you with some questions. So on the plus side, maybe you'll get to go home, I'll let you go early. On the plus side for me, maybe some of you who are experts can tell me the answers to those questions straight away, and then I can put this project to rest. All right, so what I'm going to talk about today, by the way, also the funding thing, I'm funded by ERC, but not my funding. It's a Mark Mazzei's consolidator grant, so thank you very much, ERC, for the position. All right, so I'm going to tell you a little bit about quantum fluctuations in Schwinger-Keldysh hydrodynamics. I know for a fact there are many experts who have or are working on Schwinger-Keldysh hydrodynamics in the audience, so you probably know what that is. If not, then I'll probably at least try to give a self-contained statement for that anyway. All right, so the big picture, which I suppose almost none of you will need convincing, is that effective field theories are great. They are great because they allow us to describe complicated systems with simple ingredients if we only want to focus in a particular regime of applicability anyway. Right, now the traditional EFT framework, at least the thing that we study in textbooks or in quantum field theory courses with like a Lagrangian or a path integral and some action sitting in there, is really only working for either zero temperature field theories or zero temperature systems or finite temperature systems in thermal equilibrium, and there it becomes statistical field theory. Now, if you want to go outside equilibrium, there are a lot of tools to do that, but one very important and very nice tool is hydrodynamics. It allows you to start from thermal equilibrium, do small perturbations on top of thermal equilibrium, and describe non-equilibrium phenomena. Now, as it sits, it is almost an effective field theory already, because what we mean by effective field theory, it's an effective description that depends on fields that depend on space and time, and you give me some prescription of telling me how to evolve these fields in time. So in that sense, it is already an effective field theory, but up until like maybe 10 years ago, now it's becoming a bit hard to say recently, but up until 10 years ago, there wasn't really an effective action prescription in the way that we like to think of Wilsonian effective field theories, but there is one now, which has made much of my research possible in the past n number of years. All right, so the problem or the main sort of paradigm here is that hydrodynamics, as we try to think of it as some conservation laws which determine some mode spectrum or some fluctuations of some variable or conserved variables in time, is not really a complete picture. Why? Because hydrodynamics only tells you half the story. It has dissipation, but it doesn't really have fluctuations. And if you are aware of thermal field theory, there's a very important theorem in thermal field theory called fluctuation dissipation theorem, which tells you that whenever you have dissipation in your system, you will also need fluctuations. And this is what we are going to talk about today, is how to incorporate, or what, not really how to incorporate fluctuations, but rather what do these fluctuations tell us if there's something interesting. In particular, there are two kinds of fluctuations that you can consider in these systems. They are statistical or stochastic fluctuations. They appear just because you have finite temperature in your system. So you have some probabilistic nature in your system inherently, even if your system was purely classical. Just like a bunch of billiard balls, but a large number of billiard balls. And because there are a large number of billiard balls, you always have some uncertainty if you're looking at macroscopic observables. But then there are also quantum fluctuations, which I want to talk about a little bit today. And all of this is nicely captured in this Schwinger-Keldysh paradigm of hydrodynamics. A lot of people, including many in the audience, have worked towards it. But yeah, you can look up the references. So the main pair of the game is this equation up there. It's known as the fluctuation dissipation theorem. It's one particular instance of fluctuation dissipation theorem. There's an infinite towers of such theorems which exist for any number of correlation functions, but this is the simplest one. And it has some ingredients. On the right-hand side, there's this thing known as a retarded correlation function or the response function. This is the thing that you typically are talking about in hydrodynamics. it really is the expectation value of the commutator of two operators with some theta function sitting there, which tells you that the response can only happen after you give an initial perturbation. And then you do some operations to it, multiply it with some quantity, and then this object on the right turns out to be the symmetric correlation function. It is the expectation value of the anti-commutator, and it tells you that there is some probabilistic variation. This object, if you can expand it out, it is really just the variance. I mean, if you also subtract the 0-point contribution, it is really the variance of these observables. And it tells you that whenever you have dissipation in your system, this right-hand side in some sense is telling you about dissipation, and then you will always have fluctuations in your system. You cannot deterministically tell me what your observables are. There will always be some variance associated with it. And then the important thing is this factor here. This factor, which is some complicated object, you can expand it out in h bar, if you will, or beta, which is the inverse temperature. So you can expand it out in large temperature expansion, or small frequency expansion, or small h bar expansion, and it takes this particular format here. The leading order part, which is just 2 over beta omega or 2t over omega, is, I think, the most, like, it's perhaps the way it is familiar to most people. So this is the classical fluctuation dissipation theorem. So it tells you that even if you don't have any quantumness in your theory, even if you set h bar to 0, there will still be some fluctuations going around. And then, of course, there are these finite h bar corrections. Right, now the classical formulation of hydrodynamics, which I haven't told you anything about, but I am sure you will probably have some idea, does not actually contain any fluctuations. But then you have stochastic hydrodynamics, which contains the classical part of the fluctuation. So in some sense, the hierarchy you should have in mind is something like that the frequencies that you're interested in are much, much smaller than some inverse time scale that has been induced to you by your microscopic theory. It could be some mean free path time between collisions or any other microscopic time coming from the lattice scale of your theory. And then there's this quantum time scale, which is even much smaller. So stochastic hydrodynamics, I mean, this sort of the left equality is always assumed in hydrodynamics. You always assume that you're looking at small frequency perturbations with respect to some time scale that may be microscopic. And then the second one is required to be able to truncate this expansion to leading order in h bar. But then you can imagine, for instance, in conformal field theories, the middle scale, there isn't really one. So there is no scale in the theory intrinsically other than the temperature. So in which case, omega is only controlled by the thermal scale. So for instance, in conformal field theories, when you're talking about derivative corrections, you should also consistently talk about these corrections that are coming out at leading order in sub-leading orders in h bar. Right? Not if, okay, yeah, sure. Yeah, I mean, basically, if you have any other scale, then that can play the role of the center thing, but otherwise, yeah. All right, good. But then the thing that I got interested in, I mean, why I'm talking about all of these things is these things that there are other kind of correlation functions that you may be interested in. And this is why I got the job, because Mark Mazet has a grant to talk about, to research about not Schwinger-Keldysh, about quantum chaos. So in chaos, you're not really interested in retarded or symmetric correlation functions. These are a totally different exotic kind of correlation functions where you're talking about the commutator of some operators, then the square of it, and then you're looking at the expectation value of this object. And this object, as it turns out, it's called OTOCs, or out of time ordered correlators. Many of you have probably heard of these already in the context of quantum chaos. And what happens is that if your theory has some many-body quantum chaos inherently in it, then at early times, this object, this OTOC, will typically grow, and it will grow with some characteristic coefficient known as the Lyapunov coefficient. And it turns out, by the seminal paper, I think I got the year wrong, 2015, I would imagine, Maldacena, Shankar, and Sanford have this maximal bound on chaos, which also is a Planckian bound, so it's a quantum bound, which means that, again, it is controlled by the same scale that we were looking at the previous slides. So which means that if you are, I mean, there are a lot of interesting models that actually have this. So most popular one is SYK, and then large C or large central charge conformal field theories also have this feature. So if you want to construct effective field theories that you're not really relying on a particular microscopic description, but you want to construct an effective field theory framework where you can see some effects of these chaotic systems or nearly maximally chaotic systems, then you would also need to understand how to construct effective field theories that are consistent at least perturbatively in H bar. Right? Good. So this is my one-slide introduction to what I mean by hydrodynamics. So take it as a generic slide, not in a particular system. So in a generic system, I would imagine that there are some conserved quantities, and hydrodynamics is a theory of conserved quantities. So n is supposed to dictate one such conserved quantity. In this case, it would be something like a scalar variable, some conserved particle number, but it could be energy, it could be momenta, whatever you want. And then it has a conservation equation, and J is the flux associated with this quantity. Right? And to make this equation a complete set, I need to tell you how J depends on n, because once I tell you that, then you could give me an initial condition for n at some initial time t or 0, and then I could use this equation to find you, I mean, at least as long as the equation is well posed and all that, then I could solve for n for any late times, given some background fields E in the system. So as it turns out, J has some set of constitutive relations which are given like this. Sigma here is known as conductivity, mu is the chemical potential, both of these objects depend on n, and this is some data of the theory that you will need to provide me, and E is some applied electric field. And this is some very standard constitutive relations. We can talk about where it comes from, but the only thing that you need to know is that conductivity is non-negative, and this particular combination appears because of the second law of thermodynamics. Again, we are not going to go into all that. But the only thing that is of interest here is that once you give me something like that, then hydrodynamics prescribes for you how to compute retarded correlation functions. It tells you that take this J, put it there, you find n, which is a solution as a functional of the applied electromagnetic fields. You take variations with respect to the associated sources, and this is how your retarded correlation functions are defined. And this is a prescription, not a derivation. So this is how you are prescribed to define retarded correlation functions, but there is no such prescription for fluctuations. So at the heart of it, this theory is incompatible with FDT on its own. Right. Now there are many ways to fix this. I'm going to directly go through, because I don't have a lot of time, I'm going to directly go through the thing that I want to do, which is Schwinger-Keldysh hydrodynamics, which is like an uplift of the theory that we just saw on the previous slide to an effective action. What you do, the ingredients of this theory are that if you're not going to know anything else about Schwinger-Keldysh, the most important thing is everything gets doubled for some reason. And the reason I'm not going to talk about very much, but essentially your dynamical degrees of freedom now are not n, the particle number anymore. It are these phase fields phi1 and phi2. And then also your background fields get doubled. And the prescription now is that these phi1 and phi2, you define some average basis, we label it with R, some difference basis, we label it with A. And it turns out that if you define a particular combination of these phi fields and background fields, then your n gets related to these dynamical fields in some particular way. But then there is, because I started with 2 degrees of freedom, I also have a residual degree of freedom, which is the difference field here. And it tells you about the stochastic noise that you have in your system. So you not just have dynamical field n, you also have some stochastic noise, and then you have an associated stochastic background field as well. And then I define for you, again, I'm not going to tell you where it comes from, but I define for you an action, which is given in terms of these ingredients. And what you can already show, like with this action, is that this, if you vary this action with respect to phi r and phi a, you can convince yourself that you will recover your classical equations of motion. Right. But more importantly, this action, I have written down some term here, and then you can convince yourself that you can also add some arbitrary fluctuation terms that depend only on the noise fields, or at least depend quadratically on noise fields and so on. And these terms have to be engineered to satisfy fluctuation dissipation theorems that classical hydrodynamics does not provide you. And the chair tells me I only have 10 minutes left, which is nice, because I thought I'm not going to go through my talk. But anyway, because of that, I'm going to accelerate a little bit. So essentially, yeah.
let's say, if I want to calculate some, not the complicated OTOC, any outer time order coiter, I still need multiple, like the, how is that related to this doubling of degree of freedom or accelerator? Like there I might get 4 contours, 10 contours, like, depending on what I want to calculate. So how is it related to this doubling and getting dissipation?
Yeah, unfortunately, I'm not going to get there, but yes, you will have to. So this prescription here will only allow you to compute time-ordered correlations, retarded or advanced or symmetric. If you want to compute OTOCs, or even in general, you will have to reconstruct a theory in which you will not just have 2 copies of dynamical fields, you will have as many copies as you need. And you will also get dissipation in this picture, because if you, for instance, have a 4 contour theory, then the 2 contour theory sits as a subset within there anyway.
So in some sense that is known already, right? So I'm just trying to understand what is the
No, sure. I mean, so far, no, nothing is new on this slide at least. So all I'm trying to say is that that you have these actions of this kind which depend on 2 copies of fields. Right now, this does not allow you to compute OTOCs. So this was just for time-ordered correlation functions. And there's a prescription to tell you what this S should look like. And there are these so-called unitarity conditions which tell you that these S has to satisfy certain conditions, but at the end of the day, what that means is that S has to split into this particular format, where the first part is a hydrostatic part. S1 essentially just means that S is functional of only 1 copy of fields. S1 means it's a functional of first copy of fields. S2 means it's the same functional of the second copy of fields. And you can show that this blue thing already satisfies all the 3 conditions that are sitting right there. And this is already the hydrostatic part. In fact, S1 of phi can be understood as the action of just the equilibrium part of your, or it's basically the free energy that doesn't depend on 2 copies of fields. It only depends on the single copy of field. But then you can also add some coupling terms that do not factorize into S1 minus S2. And this is known as an influence functional. And this carries information of dissipation, but all of this is still not OTOCs. But why I wanted to go there is that then there is a prescription to how to actually construct what this object is in addition to these constraints, and then this is known as a KMS symmetry, which is the thing that you need. Yeah. Sorry? What is Sij? Sij is basically my shorthand notation, which I said on the right-hand side, is essentially means that it's a functional of the 2 copies of fields. So
Fij is Sij?
Yeah, I mean, Fij, okay, yeah, I should probably be more careful. This is just a collective notation. So Fij is in general a notation for some functional F of fields Fi and Fj. So then Sij is essentially the action S, which is a functional of 2 copies of fields. Sorry, I was probably being a little too quick there.
Is just phi I.
Yeah, Fi is just a generic term for any field that
like
carries the label I. Right. All right. So I'm not going to walk through this KMS symmetry all that much, but essentially the thing that you need to know is that at the end of the day, it allows you to construct effective actions. So as we said, for S1 minus S2, it is pretty simple. You just give me some form of S1 or the functional S as a single valued field, and I can construct the associated part of the action. So in this case, if I take this particular combination, B is a field that I had defined a couple of slides before, which was some combination of your phi field. You can just take it as a derivative of phi. But like the only thing that is important here is that you can construct these objects. And the important part is that if you construct this systematically, you will find that there is an H bar correction that comes out. So classically speaking, there is some field, some term here, which is essentially looks like a difference field multiplied by 2 copies of your average field. But in general, you will also get some H bar correction in these theories. But you can also do it for dissipation. There are a lot of symbols there, but at the end of the day, the only thing that is important is that if you do this systematically, you will find that at every possible term that you can write down in the action, you will have some quantum correction that will show up. So which will drop out in the leading H bar correction, so which will drop out in stochastic hydrodynamics, but it will show up as some correction in, if you look at the full quantum theory. So really the thing that I want to sort of say is that there are multiple kind of interactions in your theory. There are some classical interactions or stochastic interactions that will the ones that will survive in the limit h bar goes to 0. These are the ones that people typically talk about in stochastic hydrodynamics or fluctuating hydrodynamics if you're familiar with those topics. But otherwise, now there are also purely quantum interactions which only show up because you are taking into account finite h bar corrections. And then these things can back react on your solutions. So for instance, this the tree level correlation function, just looking at the Gaussian part of the theory before, just the top line there, you can find that there's a correlation function here. Here m of omega is some complicated functions of frequency, which is a quantum correction that is needed to satisfy the fluctuation dissipation theorem. In the limit h bar goes to 0, this m of omega becomes 1, so you recover the ordinary diffusive pole that you might be familiar with. But then these solutions get corrected by some one loop corrections, and then as we saw in the previous slide, there is a quantum correction of this kind RRA, which comes from this object here, which is a quantum correction, so which will induce a quantum correction in your calculations. So I'm not going to display the actual calculation here, but then you can also go ahead and look at other vertices. So this triple A vertex on the previous slide, this is a purely quantum vertex. It comes from, again, this term and also this term. So it comes when this guy acts on with this, and similarly this A cube term. So it's a purely quantum interaction that does not show up in ordinary stochastic hydrodynamics, and this will also contribute to your retarded correlation function. So basically the upshot being that you can do this computations and you can find h bar corrections to your retarded correlation functions for whatever need you might have. All right, so I did want to come to OTOX, but I actually am going to run out of time, so I'm just going to take 2 minutes just to sort of fill such in. So if you want to do OTOX, then this commutator, you cannot really represent it on a 2 contour anymore. You have to do it on 4 contours. And in general, you can imagine that maybe not this, you want to compute, I don't know, commutator to the power n, and then you might need as many number of like these contours that go back and forth. So in general, the setup that we discussed so far is not really sufficient. Depending on what observables you're interested in, you might need to compute more, like construct more complicated theories. And in general, if you want to construct only OTOX which require at least, at most 4 contours, or which might at most have things that go back and forth in time twice, then this kind of generalization of Schwinger-Keldysh theory may be sufficient, in which you now have 4 copies of all fields rather than just 2 copies of all fields. And the unitarity conditions also have to be modified. This first set of unitarity conditions essentially tells you that you can collapse any 2 parts of the contour, any 2 simultaneous parts of the contour, and get back to the action that you had previously. If you sort of collapse the first 2 parts of the contour, you don't do any operator insertions there, this part will collapse, and then you will again be left with a 2 contour theory. So which means that after doing those contractions, this effective action should reduce to the 2 contour effective action that we had previously. There's a complex conjugation condition which is also easy to prove. The positivity condition I have just put there, I don't know how to prove that, I'm not even sure if it is correct. Maybe some of you can help me out with that. But anyway, once you do all that hard work, you can show that there is a part of the 4 contour theory that is entirely fixed by the 2 contour theory just because of these conditions. So this will contain all information about hydrostatic and dissipator, basically all the hydrodynamic part that was already contained in the 2 contour theory. But then you have a 4 influence functional that is an additional correction to your action that you did not have in the 2 contour theory, which might have information about chaos. I cannot be very certain. Anyway, so here is a representative example of one such term that you can write down here. You can convince yourself that this satisfies all these 3 conditions there. So basically it drops out whenever you do 2 contractions, 2 simultaneous contraction, it has a correct complex conjugation property, and it has no imaginary part, so it automatically satisfies the final one. Unfortunately, it's not that simple because this simple term is not compatible with KMS. You can convince yourself of this yourself, so I'm not going to bore you with that, but I can only tell you that this has at most 3-point interactions. As it turns out, these actions are always entirely constrained up until 3-point interactions because KMS is very strong. For 2 and 3-point functions, it exactly fixes for you everything. So there is no redundancy that you can possibly add. So we already know that whatever term that we might need to add consistent with KMS will have to be a 4-point interaction at the very least. Now I had some slides on how one might go about constructing that KMS symmetry. So I'll just tell you this in words, that on a 4 contour, the KMS symmetry, rather than becoming a Z2 symmetry that it had on a 2 contour, it will now become a dihedral 2 symmetry, which is essentially a Z2 cross Z2 symmetry that has to be imposed on this 4 contour. I don't want to go there, but this is the point where I'm going to abruptly stop because I wanted to and also because the chair wanted me to. So essentially the last part I wanted to sort of did not have so far, which I would have liked to present here, was that is there an A1234 compatible with the KMS symmetry that you can write down? I know already that it will have to be at least 4-point interaction, but it's a bit hard because it's a non-local symmetry and it's also not just Z2, so it's a Z2 cross Z2, so I'm not exactly sure how to do that. And if we can, then is there such a prescription in general for multiple contours? Are there extra conditions coming from the fact that this is a maximally chaotic theory, perhaps an SL2R symmetry that I need to impose on these? There are some works on that, I can talk about that. There's some other things that are written there that you can read, but thank you very much.
Sorry, 2 or 3 related questions.
Yeah.
In the case of n equals 4 Yang-Mills at large n strong coupling, are the things you call stochastic fluctuations and quantum fluctuations suppressed by the same parameter, namely 1 by n, both of them? Can you distinguish them in any way? And from the bulk, can you say, from the bulk I just see quantum fluctuations. Is it somehow that the stochastic fluctuations are those quantum fluctions nearer the horizon while
basically it's, I think it's this, I mean 1 over n sort of acts as h bar, right? So it suppresses all the quantum effect. Now I am not
as well as the statistical.
Basically it gives you just a classical solution. So I'm not exactly sure how you
cannot separate them in that context.
Yeah, no, not that I know of. This is one of the reasons I wanted to. So basically, also all these Skenderis Vanries or all these constructions where they try to find the corrections. I'm not exactly sure if they are doing specifically classical or stochastic corrections, or they are also accounting for quantum corrections.
One last quick related. This amount of data grows as we go to higher. Amount of new data grows higher and higher.
Higher order in derivatives and higher orders in nonlinearities. So yeah.
Akash?
Yeah.
Hi, I'm here.
Yeah.
So I'm confused about something because this is something I looked up recently in the Crossley, Glorioso, and Liu paper. And there I thought that their statement was that quantum KMS would fix the AA coefficients treated as operators in their differential operators in terms of the AR differential operators.
Yes.
And so at least if I was to take their results at face value, if I'm reading them right, then that would give me quantum fluctuation effects on the symmetric Green's functions, but not on the retarded Green's functions. But you seem to be saying the opposite.
Yeah, but I mean, this is,
So
I
I'm
mean, okay,
confused about that.
I took some creative freedom there, right? So, like, you are right. So I sort of, I mean, because the thing is that I can also take these coefficients that are sitting there and I can make them into operators themselves. So I took some creative liberty, so you can always, so if you wanted to, basically, it's this M coefficient that contains quantum corrections, but you could redefine sigma such that you can absorb this M outside and you can make it into the first part. So then it will show up in the symmetric correlation function rather than the retarded one.
But that seems very ambiguous.
I mean, so it is ambiguous just in the sense.
Whether I have quantum corrections showing up in retarded Green's functions or in symmetric Green's functions.
I mean, okay, I think it is ambiguous only in the sense that fluctuation dissipation theorem only tells you that the two have to be related.
Yes.
It doesn't, so fluctuation dissipation theorem on its own doesn't tell you whether the retarded correlation function effect, like admits quantum corrections or the symmetric one. So by symmetries, either of them could, or both of them could, as long as they satisfy the.
But I care about the retarded Green's function.
Yeah,
So
I
does
mean,
it receive quantum corrections or does it not?
Yeah, I think generically speaking, I would say yes.
But we're saying that we were
yeah,
allowed
but
to
the
choose
only
which
thing
side
that
of
I
the
want to
equality we
sort of
put there.
say is that if I once fix the quantum corrections, or let's say I expect that the sigma appears some sort of quantum corrections which are not fixed by this particular prescription, then the symmetric one will have corresponding quantum corrections, which will then affect in a very particular way through interactions. So I don't want to make a claim that I know how to compute quantum corrections to sigma itself, but they are not, yeah.
Last question from.
If I can just go to your summary slide.
Summary slide, all right.
You had this comment about maximal and near maximal chaos.
Right.
And I was just curious, because a black hole in ADS far from extremality does exhibit maximal chaos, as you know. But as far as I know, there's no SL2R in that geometry. So what did you mean by saying, is there a connection possibly between maximal chaos and SL2R?
Perhaps someone in the audience might be more. So SL2R symmetry, this is, I was presumably primarily thinking about the Schwarzian sector in the SYK.
Right.
So, so the Schwarzian sector has an emergent conformance. Yeah, so I was only talking about.
Okay, but of course, black holes far from extremality, which don't have a Schwarzian anywhere, have maximal chaos. So I was wondering.
So this is why, like, I had the first question first and then SL2R.
Okay.
So because I mean, SL2R is a particular low energy sector where I would have the symmetry, but I mean, far from extremality, I cannot.
Okay. Thank you.
Let's thank Akash again. Next speaker is Bishwajit Sahu from King's College, London, and he'll talk about magnetized bounds in conformal field.
Hello. Hello.
So let me start by thanking the organizers for giving me the opportunity to speak about my research work. And as the title says, I'll speak about magnetized bounds for conformal field theories. And thanks to Shubham and Akash to set up the stage for me about talking about various causality constraint and as well as effective field theory, retarded Green's function, and introducing all of that. So hopefully this will help me to go a bit faster while talking about those things. So this talk will be based on the following paper I wrote with a set of wonderful collaborators. They are the colleagues of mine at King's College, Chris Harjok, William Pannell, and Andy Stargiu. And please don't hesitate to ask any question at any point if you have. Okay, let me first introduce the problem which I'm going to give the answer. So I would like to answer the following questions under some assumptions as I will mention as I go along. How does a conformal field theory respond to a uniform background magnetic field? are the magnetic susceptibility and transport coefficients in a conformal field theory in strong magnetic field background can take any arbitrary values, or are they constrained? And if they are constrained, what are the physical principles are used to derive such kind of constraints, and what are the main results? Because here, when we apply some magnetic field, it breaks the Lorentz symmetry explicitly. So the usual techniques of bootstrap ideas cannot be applied directly, as you have seen already from Suham's talk. Very nice. So first, let me think of a conformal field theory in a strong magnetic field background in the Wilsonian picture as a renormalization group flow. Thinking of, you start with a conformal field theory. Let's assume it's a 2 plus 1 dimensional conformal field theory, which will have a global U1 symmetry. And that has a conserved current, which has scaling dimension 2. So it's a relevant operator. So can we be able to deform this CFT by turning on this relevant operator? We can do that by coupling to the theory some background gauge field, which I denoted by this curly A. And the constant magnetic field is basically choose this curly mu to such value of the background gauge field configuration, which provides a constant magnetic field B. And in 2 plus 1 dimension, the B has a dimension of mass square. Now, what happens under the RG flow if we go to low energy or in large magnetic field? The expectation is that it may go to some gapped phase, or it may not. I will come back to these assumptions of this mass gap in the next slide. Suppose there are some sets of conformal field theories which generates a mass gap, and since there is only one dimensional full parameter, which is the magnetic field, the order of magnitude of this mass gap will be determined by the square root over of magnetic field. And as you can see, I break the Bush symmetry if we turn on this constant magnetic field background on top of the conformal symmetry. So now this is the symmetry breaking pattern. Okay. So let's come back to the mass gap assumption. Is it very generic that any conformal field theory in strong magnetic field have a mass gap? The answer is no, because there are already few counter examples. One of the simplest example is basically you take a free fermion in 2 plus 1 dimension, and if you study its quantum mechanical properties, in constant magnetic field, it has the Landau level structure given here. And the 0th Landau level actually has 0 energy. So if you go to the second quantized picture, the quantum field theory picture, there are some massless particles. There is massless particle. So in general, the free fermion has a massless mode, and it is not a gapped RG flow if we put a constant magnetic field. There are also some examples in holographic CFTs where also this massless, this mass gap assumption is invalid. However, there are a large set of examples or CFTs where this mass gap is generic. The simplest example is a free scalar conformal field theory. And if you take a complex free scalar, its Landau levels energies are given by the square root over 2n plus 1. And as you can see, for n equal to 0, it still has a ground state lowest Landau level energy is non-vanishing. And in the second quantized picture, so basically there is a mass gap because the lowest lying particle has still a mass given by square root over B. There are also interesting examples like which one can study perturbatively or even in large N expansions, like Gross-Neveu model, Wilson-Fisher fixed points, and those kind of theories one can study in strong magnetic field, and they have a mass gap. Also, if you use the S duality and take a pair of theories like the Halperin and Peskin like pairs, the gauged and the ungauged XY model, then you can see the constant magnetic field background to the ungauged field corresponds to basically a superfluid phase, which is basically turning on a chemical potential for the gauge theory. And using S duality, you can see that for such kind of duals, that theory with constant magnetic field generates a gap. Okay, so there are interesting set of CFTs which becomes gap. So all my results what I'm going to speak about are valid only for such kind of CFTs which becomes gapped in strong magnetic field. Very nice. So now let me first now put forward all my assumptions and setup. I will consider parity invariant local unitary conformal field theories in 2 plus 1 dimension, which will have a global U1 symmetry. Then I will place this CFT in a strong magnetic field background. And finally, I will assume the spectrum is gapped, and the gap is proportional to the square root over magnetic field. Those will be my assumptions to proceed. And as I asked the few questions at the beginning, to answer those questions, I'll be giving the following recipe. What I will do, first I will gauge the global U1 symmetry by introducing some background fields, the background gauge field denoted by mu. As well as I will place the conformal field theory in a curved background, and it's a conformally coupled curved background, so that I can restore the wild symmetry. Now, after integrating out these CFT degrees of freedom, I will construct a connected functional using gauge and wild invariance. And finally, I will expand this connected functional in strong magnetic field and derive a local effective action under this gap spectrum assumption. And using this effective field theory, then I can compute few correlators, for example, current, stress tensor current, and stress tensor correlators in a low energy expansion or large magnetic field expansion, which will carry the Wilson coefficients of this effective field theory. And finally, I will develop a dispersive arguments to bound such Wilson coefficients to answer the questions I asked at the first slide. Okay. So now let me provide the EFT construction. I hope it's not working for me. So okay. So as I mentioned, I will place my CFT like in a card background as well as gauge the U1 global symmetry introducing gauge field. So this is kind of a way I can define the connected functional W, which only function of the background gauge field A and G. Okay, and since I am working in 3D, there is no wild anomalies and there is no parity anomaly because I already assumed a parity invariant theory. So this connected functional will be diffeomorphism wild and gauge invariant. So just to spell it out a bit more, so this W will be invariant in the diffeomorphism, and these are the wild transformations of the metric, gauge field, the gauge transformations, and also I want, once I come back to the flat space-time setting the background metric to beta mu nu, I should get a local, I should expect that the connected functional should not diverge. Okay, and also parity invariance basically constrain that the connected functional I construct that only carries even number of derivatives. It turns out that if we use all those things, then the fundamental building blocks to construct the connected functionals are the following. So first one is the field strength, then G hat mu nu is basically wild invariant metric. So it's a combination of the background metric G mu nu and a scalar constructed out of field strength given by F, and the wild transformation property of G mu nu cancels the wild transformation property of F so that it makes the G hat to be a wild invariant metric. And out of this wild invariant metric, I can construct the Ricci tensor, covariant derivatives, and those will be the fundamental building blocks for constructing the connected functional. Okay. It turns out that working with Mathematica, instead of tensor, defining a vector turns out to be useful. So we can define a dual vector of the field strength by contracting with the Levi-Civita and just change the first part of the building block as a dual vector. And all the indices will be raised and lowered by the metric G hat. Okay? But if we use this definition and construct the connected functional, we have to also get rid of terms which vanishes using Bianchi identity, which basically becomes this simple form, as well as there are some constraints on these F hats, which can be implemented, and as well as different terms can be related by integration by parts, so one have to be careful with that as well. It turns out that if I can construct this effective functional up to 4 power in derivative expansion, and in the first part, like in the first 0 derivative order, there is a single term. At 2 derivative order, there are 3 terms, and at 4 derivative orders, there are total 28 terms. One can write up to the integration by parts and the constants I mentioned earlier. Just to give expression how it looks like, for example, that 0 derivative order is the simple like determinant of G hat. At 2 derivative order, those are the 3 terms. At 4 derivative order, I just wrote only 2 out of the 28. Now, once, as I mentioned, once you have the connected functional, now you can expand this connected functional about the constant background magnetic field, like the gauge field configuration which gives the constant magnetic field and the fluctuation which is denoted by this rate mu. And since the gap assumption is there and the connected functional we constructed on the local, so basically it gives a local effective action after this expansion. For example, the scalar we constructed has this following large magnetic field expansion. It starts with a constant magnetic field, then there is a f square over b, and then 1 over b cube. This is kind of the expansion, and the effective field theory will be valid below the energy scale given by the square root over magnetic field. Yes. So it's kind of, we try to write all possible structure in mathematical, like all possible structure by constructions of these objects and at the particular derivative order. Then we implemented these sets of constraint and that total derivative, all these things in Mathematica. There is a better way to construct like the Cirrus used, for example, for graviton scattering amplitude stuff. But this kind of, we use kind of more brute force approach.
I see. So, I mean, is there not any definitive argument which says like you missed one structure, for example?
Yeah, I understand it. Yeah, it could be possible, but like this is what we got, and maybe there could be a more systematic way one can use to settle this issue.
Quick question. You are calling your magnetic field strong because you are choosing a particular derivative counting scheme?
Yeah, it's just that I want to work in an energy scale below the square root of a magnetic field. So in general, I don't have to tell this B to be strong. It's just that my effective field theory will be valid below the energy scale given by this square root of a magnetic field.
Let me ask it another way. Like in constructing those terms, are you counting your f mu nu as order 0 in derivatives or first order in derivatives?
It's a 0th derivative because it starts with the expansion B.
Okay, so it's basically magnetic field is 0th order in derivatives.
Yes. So for the electric field, so since I am choosing, so the electric field part also comes in when we expand, for example, this expression, and those parts breaks, for example, the Bush symmetry because of this like background choice, and they will automatically generate. So, oh, that's also like electric fields always comes with a, I think, first order in derivative, because if it is contracted, say f mu nu, then there is a magnetic field square and there is electric field square, right? And electric field will be part of a, like it's a small parameter compared to the magnetic field as expansion.
Okay.
Sure. Sorry, I cannot hear.
Why are you saying the boosts are broken because of a background magnetic field?
Oh, it's basically since we put the magnetic field in the F12 direction. So basically, now basically the boost in the 1 or 2 directions, right, are basically broken. Because it's the time direction, like if you think of it, say magnetic field in the time.
I would have thought that you're breaking rotations.
No, the SO2 rotation is still there because it's a uniform magnetic field in the 1-2 plane. So the SO2 rotation is still there. Only the boost part of the Lorentz group is broken.
So boost will involve 1T and 1 spatial.
Exactly.
So your 1, 2.
So F12 is like in the vector, like if you dual it in the dual vector, it's the F0 or the F time component, right? Dual vector.
Okay.
Just one question here, this right side here. So I was just wondering why we made the assumption that the action is local. Wouldn't all the current correlators and the stress tensor correlators be contact terms? Like,
so yeah, those are really contact terms if I assume the like mass gap and the effective field theory is local. And that's the point. Like, so in the IR, that's why it's a empty CFT. There is no massless degrees of freedom left. So the effective field theory only involves the background fields and the effective action is local. So those are only really contact terms.
Okay, I see.
Yeah. Okay, maybe I should proceed. Okay, now once we have this effective field theory, we can compute some observables. And one of the interesting observable is that if we Euclideanize the theory and put on a Euclidean 3-dimensional manifold, like on a plane, and then basically we do a conformal compactification to go to a cylinder, then basically what happens is that we can now consider a field background fields configuration which corresponds to a magnetic monopole background with the corresponding kind of field strength components. and this Q denotes the magnetic charge, B is the magnetic field, and L is basically the radius of the sphere, S2. And if we do that, and now let's compute the free energy on the cylinder after like some doing Euclidean compactification of the time, it turns out that the free energy can be just determined from this connected functional evaluated on the background I choose, and the metric is basically the metric on the cylinder. And this we can compute using our connected functional, and it turns out takes this following form: the total energy times this length scale L has a large Q expansion, which is a large magnetic charge expansion, starting with Q to the power 3/2 and Q to the power half, Q to the power minus half, like this. And as you can see, there are only few EFT coefficients are appearing here. Now, once we have this free energy, we can compute the magnetization and also the susceptibility, magnetic susceptibility. And the magnetic susceptibility at leading order turns out to be constant, given by the value of the C0, which is the leading Wilson coefficients, then corrections given by the other Wilson coefficients suppressed by the 1/Q. So from this expression, as you can see, if I go to strong magnetic field, thank you, then the C0 value and its signs determines whether the magnetic field goes to a diamagnetic, paramagnetic, or ferromagnetic phase. One can use this effective field theory also to compute the correlation function, and as one of the audience mentioned, is that since the effective action is really local, so it will be given by some contact terms, basically which are the derivative of delta functions, or in momentum space, those are basically polynomial in momenta. And also, since we used all the symmetries corresponds to like gauge, diffeomorphism, while, so basically one can study various word identities follows from them, and they are automatically satisfied by the results we can compute from the effective field theory for these correlators. For example, just to show one example, so for example, the current correlator will have the following form. The first term, as you know, it's very standard. The tensor structure, it follows just from the Lorentz invariance and conservation of the currents, but since the Bush symmetry is broken, it has another term which has this following behavior. Only the spatial part of momentum are there involved, these k vectors. And the spectral densities, there are now two spectral densities which are function of both, like the 3k vectors, the 3k square and the spatial k vector square. And this spectral density has the following expansion in 1/B in terms of the Wilson coefficients. Okay. So we can compute such kind of observables. Now let's see whether we can derive some bounds on Wilson coefficients. And this we do using generalized Kramers-Koenig dispersion relation. Sorry. So as you heard from Shubham's talk, that still causalities hold in our theory, and causality implied some analyticity of retarded Green's function. So here I defined the retarded Green's function, which is support only in the forward light cone. And if you do a Fourier transform and define a momentum space retarded Green's function, it has this, like this is the definition. And now to work with a single complex variable, let's choose the following momentum configuration, that the k is given by omega times 1 and the xi vector, and omega is complex, and this xi vector is a real 2 vector, and its modulus between 0 and 1. And if you restrict to this condition, then it turns out that the forward light cone support basically translates to the fact that the retarded Green's function has only support, or it is analytic in the upper half complex plane in omega variable. Okay. Now this is only the causality. Now we also want to implement the unitarity. For that, we need to have a dispersion relation. And as I mentioned, we have to start with the retarded Green's function, which is support on the upper half plane in the complex omega. It could have branch cuts because due to the mass gap to one single particle, there could be poles, and also branch cuts due to multi-particle exchange. And let's start with this following contour. Since the GR of omega is analytic inside, so basically evaluate the contour integration of this object for any value of positive value of L is basically vanishes. This is what analyticity provide us. But now we know how the UV behavior of this retarded Green's function is, because we know that it is determined by the UV, it is determined by the CFT. So suppose this retarded Green's function in the UV in omega going to infinity limit has a omega to the power L UV. Then if we choose the values of L here, which is greater than this L UV, it turns out that if we deform the contour, like for this whole contour, the contribution from arc at infinity basically vanishes. On top of it, if we restrict to the values of L, which are even, then it turns out that this cuts in the negative omega axis and the cut, like the contribution from the C1 and contribution from C2 combines in such a way that it becomes a White-Band correlator, and you can insert complete set of bases and use unitarity to show that these contributions become positive or semi-positive. So once you use all these things, what you will get is the following thing. So the evaluation on this C0 half contour in omega going to 0 limit will be given by this object. And if you do now, since you have this retarded correlator at omega going to 0 is given by the effective field theory, you can use effective field theory, which is a contribution to it, which is a small omega expansion, and then basically its various derivative order of it will be given by this thing, which is a semi-positive definite from unitarity. And finally, this is a retarded correlator. However, the effective field theory provides you a time order correlator. You have to relate this condition to a time order correlator, and using this relation, what you will find actually I times the time order correlator's L derivative is positive definite with the momentum configuration given here, and as well as for the values of L greater than LUV, and it's even. So now let's choose such an operator for which I want to use the retarded, I want to define the retarded correlator, which is a combination of some derivative of current and a stress tensor, and this is dimension 3 operator in the CFT. And so LUV is given by the value 3. So basically now if you use this constant I mentioned, I derived earlier from the dispersion relation, that basically translates to the following thing, is that this matrix have to be positive semi-definite. And this matrix, as you can see, involves some combination of current and stress tensor correlators, and this has to be true for each order in small omega expansion for the values of L, 4, 6, 8. Those are the terms which we derived from the effective action. So now it is a positive semi-definite matrix, so it's just become like a SDPB program, but fortunately this is for independent components of the stress tensor and currents. We have only, this is 8 cross 8 matrix, so we can solve it analytically. And if we do that, we get some set of non-linear, some set of constraints, semi-positivity constraints involving the EFT coefficients. If you identify the chi squared to be the x in the region x from 0 to 1, they basically become some linear, like constant, linear, quadratic, and cubic, some non-linear identity, some inequalities. And from, for example, just to show some examples, the C0 turns out has to be negative, like negative semi-definite. C23 is also same, and for the combination of the second derivative, the Wilson coefficient at 2 derivative orders has this kind of following inequalities. And for example, this C0 is less than or equal to 0, basically tells that the magnetic susceptibility is negative, which in turn tells that any 2 plus 1 dimensional CFT under the assumptions will behave diamagnetically in strong magnetic field expansion. So microscopically you can think of, in response to the strong magnetic field, the orbital angular momentum contribution to the magnetic flux always wins over the spin contributions. Similarly, one can also find some bounds on some ratios of Wilson coefficients. There is some allowed region and disallowed region, for example, at 2 derivative order Wilson coefficients, and there is also a kink which we don't understand yet, like whether which theory lives there, and it would be interesting to explore. We also went on to like 4 derivative order EFT coefficients, and there also we found some 3-dimensional plot, but it is not very illuminating, but there is also a presence, so there is a kink as well there. Nice. So how much time do I have? 1 minute, okay. Thanks. So now obviously we have to test such results, that whether we can compute such EFT coefficients and where in the allowed theory, or where the values of these C's lies in the allowed region or not. For that, we can compute, for example, the pre-complex boson theory, in a strong magnetic field, which is the complex scalar theory. And fortunately, Swinger already derived the propagator, like which you can see sum over all the Landau levels, because the poles are given by the Landau level energy levels. And you can use this propagator to compute the 2-point function. For example, this involves some computation of these Feynman diagrams, and one can compute these Wilson coefficients, which we did only up to 2 derivative orders. Similarly, for free fermions, obviously for the free fermions, as I mentioned, the ground state, the lowest Landau level, it is basically has 0 energy. So this, the quantum field theory has a massless particle. So to do that, we have to, like if we want to compute these results and want to integrate out this massless degrees of freedom, it generates some non-local effective field theory. what we did here, we just by hand removed the lowest Landau level and then computed these values, and those values takes the following form. But keep in mind that we removed one of the state. So basically, complete set, like when we insert resolution of identity in terms of complete set of bases, we are removing a state, so the unitarity will be violated. And this is what we see in the bounds. For example, the free scalar lives inside the allowed region. On the other hand, the free fermion actually little off from the allowed region, because we removed the massless state for the free fermion, and if we include, then it will violate one of our assumptions. So that leaves a question that how we can generalize our effective field theory construction in presence of some massless degrees of freedom. So let me just end by future direction. This will be my last slide. So obviously we only computed some free examples. It will be interesting to compute the CFT coefficients for some interesting interacting CFTs. For example, some of my junior collaborators are computing for Wilson-Fisher and Gross-Neveu model at large n. And also one can compute from some holographic CFTs where this assumption is valid and try to see how the values of the Wilson coefficients fits inside, like whether in the allowed region or disallowed region, and if so, what kind of assumptions, like the assumptions we made, like we assume at the beginning, which kind of assumptions or what assumptions are they breaking if they are not in the allowed region. Also, as I mentioned, if there are some massless state in the, if there are some massless states remain, then obviously we have to incorporate those massless state in the effective field theory construction. How to do it properly, it's still unclear. This is one of the open directions which I would like to explore. Another thing is that on top of this magnetic field, one can turn on, for example, finite temperature or chemical potential, and can try to study whether there is some interesting phase diagram if we tune between them. For example, as you know, if we turn on chemical potential, then basically in a CFT, like it usually goes to a superfluid phase, and also there could be also Fermi liquid as we heard. But if it goes to the superfluid phase, then also there is effective field theory construction there. So one can ask, can we use the S duality? This is this Peskin-Halperin S duality pair if we take, and suppose now we have effective field theory in the strong magnetic field, there is a construction for the chemical in presence of chemical potential or finite charge density, whether one can relate using S duality between them, whether those bounds derived here can also be applicable there using some S dualities. So all those kind of questions could be interesting to explore. And with this, let me thank you.
Let us thank Vishwajit. Questions? Everybody's in need of coffee.
Really very nice talk. In a situation where you have, when you have bands, like one fill Landau level, then another fill Landau level, if you take your chemical potential and put it in between two bands,
yes,
then it sounds to me like you still have effectively a gapped system there.
Exactly.
And you could replay this whole thing.
Exactly.
So you could get a whole series of such constructions, one for each gap between bands.
Exactly.
I was even wondering whether in the case of a quantum Hall effect, fractional quantum Hall effect, once again the system's supposed to be gapped, let's say with 1/3 filling.
Mm-hmm.
So you could put the chemical potential at 1/3 filling and once again play this game.
Exactly.
And it sounds like that might be very rich physics.
Yeah, this is interesting. Even this is like, for example, the free fermion case, as I was telling, I just removed the lowest Landau level by hand, but I could have given a chemical potential between the lowest Landau level and first Landau level. This is a natural thing what I am doing, but instead of putting this thing. But it is interesting to see whether basically then when we are computing, for example, these loops, right? So basically now this n runs from 1 to infinity. So obviously the numbers which I get won't be in terms of zeta functions because those really sums over all the Landau levels. So one can numerically actually compute those things and see what happens. This is one of the interesting thing. But the thing is that if the chemical potential is order of square root over a magnetic field, then what happens is that there could be a competition between them, because as you know, turning on a chemical potential effectively generates a negative mass square value. And there could be a competition between the magnetic field and the negative mass square, and one have to be a bit careful, like with this mass gap assumptions and all other things. So,
but we expect in between bands that it's gapped, right?
Yes, yes.
So physically we expect that. But also I was thinking most interestingly in like a fractional quantum Hall effect. Let's say 1/3 filling, yeah, there are these very interesting states which are supposed to be gapped. And if you could characterize them in this interesting way, it might...
Okay, yeah, maybe this is interesting. I need to discuss more with you.
So if you have to convert your bounds into islands to isolate specific theories, would you add more correlators or what correlators?
I feel that it's just at the 2-point function level what I did. One is to improve it like maybe 3-point function using like say some integrated stress tensor like people do in NAC, and maybe at the 4-point function maybe like commutation of the two operator but inserted not in the vacuum but another operator operating on the like vacuum, and this is like effectively a 4-point correlator, but two of the operators in commutation relation, and they still those are outside. If they are in the space-like region, still vanishes. So generalizing this kind of ideas like to higher point functions will be useful, and then maybe you will be able to shrink this region. There is a possibility. So only at 2-point function level, this is what we can do at most.
And the points that saturate the bound, are they special? Are they free theories?
So there is, we did not find, for example, the kings here, what I was mentioning here, there is a king and here also there is one. So we did not find any example yet whether some theory saturates those bounds. So it will be interesting to explore those as well.
Okay,
Any further question?
Let us thank Bishwajit again. So we take a short break and be back here at 5 o'clock. Announcement from the organizer, just hold on a second.
Those of you who are interested, please sign up for the excursion. The sheet kept at the registration desk. And also please look at the posters. They are being changed every day, so it's new poster each day. Tomorrow in IIT there will be another set of posters. Going to, oh, it's a Konark. Okay, that information given somewhere. Depending on the number of people, I mean. You haven't decided where it's going? No, it's decided for the Konark. That's what I'm saying. That fact was my figure.
the sorting schedule?
Stop it. It's Vinata Panda, Suprano and Chakraborty. Siddhartha Prabhu is gone, right? Who is the
Siddhartha Prabhu is gone? Oh, okay.
this guy? I think he gave. Nico, yeah, he
Nico,
gave.
yeah. Rozali Vasu.
He didn't give, right? Yeah, he is. So it's Vinata Panda, Supranin, and Rudnani. Vinata is here.
Not up to first, right?
Yeah.
And what was? What was the name?
Supranin.
Chakravarti.
Let me check if Nishan said something else specific. Maybe he's going to give them.
Rudal was not there. Schedule is correct, right?
Yeah. Call, right?
What happened to this? Why did this stop?
Pointer.
Pointer.
Check. He said it stopped working in between. No, it's not.
It
Okay, it's fine. It's working now, right? Then leave. You say we should leave it south. Yeah, it's good. In fact, it's slower. So, okay, maybe 510.
Okay, please settle down. We are going to start the last session today. The first speaker is Binata Panda from IIT ISM Dhanbad. And she'll talk about logarithmic corrections in black hole entropy. And the next talk will be online talk by Rudra.
Okay, thank you, Devasista, and thank you the organizers for the invitation, and it's always a pleasure to be a part of ISM. So this ISM is Indian School of Mines, so where I work. So today I'll be talking on our recent work about logarithmic corrections to the near extremal Korn-Neumann black holes. And this talk will be based on our recent work that I did with my student, PhD student Assis, and a postdoctoral fellow Aditya Singh. Both Assis and Aditya are there, and they will be ready to answer your questions after the talk for any discussions. Okay, so let me start with a very small recap of what we have understood on black hole thermodynamics. So black hole, as we all know, behaves as a genuine thermodynamic object where every familiar thermodynamic quantity like temperature, energy, entropy, it admits a precise geometric interpretation. And among all these quantities, entropy plays a central role because it captures both the macroscopic, the geometric description, and the underlying microscopic degrees of freedom. So greatly helps us to understand the constants, the features of a full quantum theory of gravity. And this entropy is encoded in the leading order contribution to this entropy is encoded in Bekenstein-Hawking formula, and that is further validated through microscopic state counting in string theory. So this entropy, this leading order Bekenstein-Hawking formula, that is basically a semi-classical result, and in a full quantum theory of gravity, it expects corrections, expects to receive corrections on both sides. Like there can be classical corrections from the higher derivative terms in the action, or it can be also the quantum corrections. And we will be focusing on the quantum corrections. So the quantum gravity predicts the corrections of where the leading order is logarithmic in the form. It's logarithmic in the area of the, so if the Bekenstein-Hawking formula, it's the area, and the leading order is the logarithmic of the area. And these log corrections, they are the leading quantum corrections, and they originate from the one loop fluctuations in the gravitational path integral. So these logarithmic corrections, they depend, they are kind of semi-universal, like they appear in any generic theory of gravity, but then they depends on the spectrum of the massless fields of the theory. So for any, it can be computed for any theory, but the contribution, this coefficient is different for different kind of theory. That depends on what theory you are considering. And we have a systematic way of computing this logarithmic correction, well established, the quantum entropy function formalism. So with that, one can compute these corrections, and for the extremal black holes, we have a method that is called the heat kernel of one loop action of a gravity theory. Considering the one loop action of a gravity theory and the heat kernel, one can systematically extract these logarithmic corrections to the entropy of extremal black holes. For non-extremal black holes, you can still use the heat kernel method, although the treatment is a bit different than the extremal ones. And this technique basically use the near horizon ADS2 factor that appears in the extremal black holes and its symmetries. And string theory has provided a microscopic interpretation of these corrections to black hole entropy. So for various cases, the matching of the logarithmic corrections from gravitational and the microscopic perspectives has already been achieved. And for obvious reason, the extremal cases are the most studied ones. It has more symmetries and it is easily computable. So these are the most studied ones. And okay, so before going to my actual talk on near extremals, so for another example of this extremal case, we are working on computing the logarithmic correction for these hyperbolic black holes in n equal to 2 gauge supergravity with Imtazian, Alok Nanda, my student, and Anwar, currently a postdoctoral fellow at IIT Mumbai. We are looking for computing these logarithmic corrections, focusing on the Bojanic real scalar truncation, and where a non-trivial scalar potential is considered instead of a cosmological constant. And we follow the Seeley-DeWitt coefficient method to compute this hit kernel evaluation. This coefficient A4x is the Seeley-DeWitt coefficient in this truncated Bojanic sector for this non-minimally coupled Lagrangian for this theory. So Anwar will present a poster on this work. So for details, please see Anwar's poster. Okay, coming back. So there are nearly the non-extremal cases. Of course, the microscopic understanding is not yet understood. So the next thing that one can look for is to study the near extremal ones. So the near extremal black holes are the black holes with small temperature. So they serve as good candidates to generalize the results that we obtain from the extremal black hole in the presence of small but non-zero temperature. In some recent works by Trivedi and authors and Turiashi, the low temperature dynamics of this, it is found that the low temperature dynamics of such black holes is governed by one loop corrections, which is proportional to logarithmic of t. So, and in a followed of work by Nabomita and all and Turiashi, they have shown that these correction terms can also be computed from the one loop quantization of the near horizon near extremal background, like we follow the method that we follow to compute the logarithmic of area corrections. So the procedure basically depends on the computation of eigenvalues of the kinetic operator of small fluctuations around the classical background, and I'll show how the hit kernel is modified. Okay, so this by saying the motivation of doing this work, this is my outline of today's talk, that I will briefly explain the hit kernel approach for the extremal case, because we are just considering the near extremal as a small perturbation to the extremal black holes, and the modified approach, how the approach will be modified for near extremal black holes. And then I'll summarize, I'll show the theory that we exactly computed. It's near extremal Neumann in n equal to 2 supergravity theory, and I'll conclude with the results that we have received. Okay. So in the hit kernel approach, we basically start with the 4-dimensional Euclidean path integral, where you can write the partition function as the integration of all the fields in the black hole background, including the metric, and S is the Euclidean action. And we consider small fluctuations around the classical background as G tilde and X lum tilde, and then if you expand the action for these fluctuations and write down the quadratic fluctuated action. So that can be schematically written as in this form, that these are the field fluctuations and delta is the differential operator that controls the quadratic fluctuation. So delta is called the kinetic operator of the theory, and the one loop effective action can be defined as or finally can be written as a determinant of this kinetic operator. For bosons it goes as -1/2, and for fermions it goes as 1/2. So you can write down, we can in turn write down this expression or extract W as in terms of the eigenvalues, discrete eigenvalues of this kinetic operator. And for any theory it is difficult to compute W directly by computing these individual eigenvalues. The way out is one follows the hit kernel of the corresponding kinetic operator, and one calculates the hit trace and extract W, the one loop effective action or the log correction systematically from it. Okay, so the hit trace is, I wanted to show this expression because lastly in the latter part I will use this expression. So this is called the hit trace of the corresponding kinetic operator, and the eigenvalues appear here. The next thing to be noted that this determinant, so this is one thing that we cannot compute it, and we use the hit trace or the hit kernel method to extract the result. The other thing is that there can be modes with zero eigenvalues, which we call are the zero modes. So the determinant itself may be ill-defined due to the presence of the zero modes. So the contributions from zero modes and the non-zero modes, the modes having non-zero eigenvalues, should be computed separately. So the treatment is a bit different for both of them. And also the bosonic fluctuations, the kinetic operator is a second order differential equation, and for fermion it is linear in the derivatives. So so they should be treated differently. So in my results mostly it is divided into sector wise. Okay, so next come what happens for the near extremal. So the analysis that we follow is the approach that is established or carried out by Nobomita et al. In their recent paper, that we treat the near extremal solution as a small deviation of the extremal black hole. So what happens in the extremal black hole, the temperature is 0 and we take a small temperature deviation above the extremality. So the near horizon geometry, which is a ADS2 cross S2 for Rhizon nostrum or for Korn-Neumann, it is some manifold K, that gets modified. The geometry is slightly modified from ADS2. It's a deformed ADS2. And then there are some zero modes which are originally zero modes in the extremal background. Now they, because of the small temperature, they get lifted and become non-zero modes. So those modes we call as slightly non-zero modes. So they have small non-zero eigenvalue, and the quantum quantum fluctuations, they become important. So earlier we have the contribution from two modes, the zero modes and the non-zero modes. In the near extremal case, we have to consider the three different kind of modes and their contributions has to be computed. That are the non-zero modes, the zero modes and the slightly non-zero modes. And what we observe that this logarithmic of temperature or the log T corrections, they generate from these slightly non-zero modes. The zero modes and non-zero modes, the proper zero and non-zero modes, their contributions are still logarithmic in the area. So the methodology that we follow is the Euclidean path integral, and with the heat kernel regularization, and we use a first order perturbation in the temperature parameter. So near the extremality, so we fluctuate all the fields in the linear order of the temperature, and then extract the quadratic order fluctuations. So these quadratic order fluctuations then takes this form, where these are the field fluctuations, and all these temperature dependent corrections goes to the kinetic operator. So and the job is to find out the heat kernel for this perturbed or the modified operator, which we call as the delta bar. Delta bar is linear in temperature. So if we have the eigenvalues, as earlier we will need the eigenvalues of the kinetic operator. Then this eigenvalues of the kinetic operator again are first order, get a first order correction in the temperature and also the eigenfunctions. And using the first order perturbation theory, we can actually compute these shifts in the eigenvalues and the eigenfunctions. Of course, so in this method we will not be using these shifts. We don't want to compute. And the aim is to extract the logarithmic corrections in lambda and t. So lambda is okay. So lambda is the scale parameter. Since I have in one of the slides I'll show you how lambda scale. So my charges of the black hole will go as lambda, the angular momentum goes as lambda, and the area goes as lambda square. And we evaluate the quantum corrections by considering the three different sectors separately, the non-zero, the zero modes, and the slightly non-zero modes. So we call those non-zero modes are proper, those were non-zeros on the extremal background. Fine. We call them proper zero modes. They are exactly treated in the same way what we do in the extremal case, and we found that they give rise to the log lambda terms. Those zero modes which still remain as zero modes in the near extremal background don't get lifted in this by the temperature. So these are called as the proper zero modes. Again, we treat the proper zero modes exactly same way in the way that we treat in the extremal case, and that gives rise to log lambda corrections only. However, the slightly non-zero modes, they should be treated separately, because they are zero on the extremal, they are zero modes in the extremal background, and then they are shifted to be non-zero, and they are found to generate both the log lambda and the log t corrections. Okay. So we consider, I'll show you how this log lambda and log t comes, but in our case directly, because I don't have the time to discuss the methodology in detail. So we start with considering the near horizon geometry of the extremal core black hole, and it is already in the Euclidean continuation, and we consider the write down the determinant of the near horizon metric, because that plays a central role in evaluating the heat kernel coefficient. And this is how my charge and angular momentum and the area of the horizon, they scale with lambda. Okay. So from the bogenic sector, if I am considering the non-zero modes or the zero modes, for the non-zero modes, if you write down the logarithmic of the partition function, so we have to evaluate the heat trace of the heat kernel, and then if you integrate and expand this heat kernel in the smallest region, and the coefficient of the S independent term basically gives you the log lambda terms. And we do the integration for small s region, and this is the result for the non-zero modes for the extremal case. The zero modes has to be has to be calculated separately, and there is a systematic method how to take care of that. So if you count the number of zero modes in that background, and beta is the weight factor, it's specific to the type of zero modes that you are considering, and we can write down the contribution of the zero modes, and we write the total logarithmic correction for the bosonic sector in the following equation, coming from both the zero modes and the non-zero modes. For the fermionic sector, for the non-zero and the zero modes, we follow the usual hit kernel method, where we start with taking the square of the derivative operator and account for the square root in while calculating the contribution, and we compute the total, the non-zero mode contribution and the zero mode contribution, and this is the result in terms of the charge, the angular momentum, and the number of zero modes in that black hole background. So for the slightly non-zero modes, as I said, these are zero modes in the extremal background. So if you go back to the eigenvalue equation, you can see that the eigenvalues of these modes are already order t. There is no order 1 piece, because they are zero modes. The eigenvalues are zero in the extremal background. So the relevant contribution in the partition function, their eigenvalues will have a t part. So we are summing over such kind of non-zero modes, which are called slightly non-zero modes, and then okay, so defining the dimensionless objects and doing the integration, you will get a contribution which have both log t and log lambda coming from these bosonic contributions, the bosonic slightly non-zero modes, and we can calculate the number of such modes, and this is the final bosonic contribution. However, for the fermionic kinetic operator, the kinetic operator is linear in the derivatives. So here we work differently. We work with the eigenvalues of the fermionic kinetic operator, not its square, not in the as in the usual method. And then if you follow the regular formalism, you can extract the contribution from the logarithm of the partition function, considering such kind of slightly non-zero modes, and there will be no log lambda contribution from there. And this is the final logarithmic correction that we got from the slightly non-zero modes in the fermionic sector. There are no log lambda term from this sector, and we write down our final result by considering the zero modes, the non-zero modes, and then the slightly non-zero modes from both from the bosonic sector and fermionic sector for the theory. And okay, so these are basically the coefficients that are calculated in the extremal black hole case. And then we calculate these quantities, so the final result will depend on which theory you are considering. So the number of zero modes or the slightly non-zero modes, they will depend on what kind of theory you are exactly considering. So we have computed that for a Korn-Neumann black hole in n equal to supergravity theory, and this is the final result that we obtained from the computation. So this extremal Korn-Neumann, it's already known. It's known in the literature, so you can substitute the value. So in addition to the log lambda terms, there are also the log in temperature terms in the correction. Okay. So this is what we have calculated. So we computed the precise logarithmic correction to the entropy of near extremal Korn-Neumann black holes, and we hope that our result is will give some constant for the microscopic theory which wants to calculate these corrections from a microscopic computing. And of course, we have our analysis complements the quantum entropy function framework, extending its applicability to the near extremal rotating black holes. Yeah, so I'll stop.
Thank you, Vinata. Questions, comments?
Thank you for this nice talk, ma'am. So this near extremal geometry, this is smoothly connected to the extremal geometry, right? Like d going to zero limit.
Okay, what do you mean by smoothly connected?
Like, are you?
Okay, in the extremal, the near horizon is ADS2 cross. Let's say for horizon nostrum, it's S2.
S2.
And this ADS2 has a infinite throat in the extremal limit, and so for these near extremal ones, this throat is large, but it is finite.
It's finite, yes.
Yeah.
So, but in the entropy, you have a log t term. So there you cannot take, after getting the entropy, you cannot take t going to zero limit, right?
Yeah, we cannot take the t going to zero limit, because while evaluating, we have made these scalings, so where in the answer you cannot take the t going to zero limit and see that it will going back to the extremal. Yeah, you cannot do that.
Okay, so so the geometry ADS2, because it's2 has a it's a finite throat in near extremal, so that becomes infinite throat by a smooth transition from t to zero, right? Am I?
Okay.
Geometry is
the geometry transforms, but while computing these log corrections, when you do this integration, we do smallest integrations. Okay, I'll just show one calculation. Maybe that. Yeah. Here we change the. So this is small s integration. Fine. And if you change the t going to 0, you are going to basically s going to 0. So we don't do the s going to 0.
Okay, so somehow you cannot take the t going to 0 to entropy.
Okay, so in the answer, if you go take t going to 0 limit, it will not give you the extremal answer.
Okay, okay.
Nice talk, Vinata. But maybe, did you mention, is there a sense in which this log t term is universal, meaning it's higher derivative corrections and so on would not change it?
Okay, so this will be, the first thing, it will not be universal, because again it depends on the theory that which modes will be uplifted. Fine. Universal in the sense you see the appearance of the term or the coefficient of the term.
No, the log t term, just like the log a term, came only from the
one loop correction.
From the one loop correction.
Okay, so this is again from the one
loop, and but there you can argue you won't get any other correction. So, any other contributions to the log term?
Okay, so the log t will not come from the non-zero mode or the zero mode. It is
slightly non-zero modes.
So
it's essentially just determined by the kinetic term, right?
Yeah, it is determined by the kinetic term, but then it depends on largely on the, like I said, the kf0 or the kr0, the ones which got uplifted. Fine. So it's a theory. You have to see which modes are uplifted in this. So yeah, so there are some computations, okay, not from this method, but treating near extremal black holes in some other way, but they said it's 3/2 log t, like will be coming, but then they only consider the metric modes to be, the tensor modes to be uplifted.
Yeah, you would have to consider all the fields, but the kinetic terms, I thought, I can't quite see whether there would have been any other log t terms. It seems difficult to get other log t terms, but again, we can discuss.
Just a side comment on Rajesh's question. So suppose you do not care about the coefficient and just the log t behavior,
and also not about the theory, but just what kind of spectrum might give rise to log t. Then a very toy system, if you take exponentially many low-lying states with some fixed spacing like a harmonic oscillator, and then suppose there is a, if you do stat make of this very simple system and take a certain low but not too low temperature limit, you actually get log t term quite universally. We can talk later.
Let us thank Vinata again. In the interest of time, we have to postpone that.
Sandeep has a question. He asked from the beginning.
Okay, let us thank Vinata again. Next speaker is Rudranil Basu from BITS Pilani Goa campus, and he will be joining online thanks to Indigo. Well, I don't think he is there yet. Don't look at the screen. You have to approve it on your phone.
नेट फोन चेक करो तुम्हारा नेट ठीक है, इसका नेट खराब हो जाएगा। देखिए अकाउंट क्या करे, ठीक है मेरा पासवर्ड रुको खुलने से पहले मेरे को पासवर्ड निकालने दो। मेरा पास की है क्योंकि मैं पासवर्ड नहीं यूज करता। यार पास लोड करके देखता हूँ। Huh? Okay. Wait. What is this email? I don't know what is this email. Okay. What is it? Okay. Send it to ISM 2025. 2025. .iitbs@gmail.com. Control. Reload करो. Yeah. Code one second. Open Zoom meetings. There is no speaker on the mic. No video का audio का देखो. Host कौन है? जो No, the host hasn't started the meeting. The host hasn't started the meeting. क्या अकाउंट से भेजा है, किसी ने भेजा है? Yeah, we are. I can do. Should I create a new main? Yeah. Yeah, I guess, sir, sir, it's done. Is it? So it's audible? Color mark is here, but
Yeah, we'll take it down. Rudunil, you are muted. Is this on? No. It is also not on.
it's on. It's not on.
Rudunil, can you hear us? You are muted. We can't hear you.
He's the.
Oh. Can you increase your volume or the local volume here? I don't know which one is the.
There's an audio issue. Well,
So what is the problem in the audio? Why is it not coming?
really low, sir. Really low.
No, but
Hello, sir. Hello. Can you hear me, sir?
see, table that table will go.
Hello.
Say something. I can see you want me to say something to you. You didn't say.
Yeah, okay, sir. Give us 5 minutes, sir. Right.
how many string theories does it take 5 years after Zoom became common to fix an online talk?
Hello, sir. Yeah. Have I tried it? It doesn't work. Huh. Where's the column? नहीं सर के पास है the chair hello sir. Yeah. Say something, sir. That one. Near. Can you hear us, sir?
Yes, yes, I can hear you.
Okay, start. This is fine, right?
This can
Keep it here, right?
see moving or not, we will see.
I think
Let's start and see if we can get some.
battery charge
Yes. Should we try and move this there? I mean, just keep it. Okay.
there's a slope light difficult.
Rudra, just try and speak a little bit and see if we can hear you.
Am I audible now?
Yes, you are. Yes, you are.
Okay.
Somehow
Great.
this has worked.
Wow.
Sorry, Rudra, sorry for the delay. I'll give
It's
you a
fine.
warning 10 minutes before. You have 25 minutes. So I'll tell you
Okay,
10
sure.
minutes before, that's after 15 minutes and then after 20 minutes. Please start and try to finish on time.
Sure, sure. I thank the organizers for inviting me to speak here, but due to unfortunate flight disruptions, I could not make it to Bhubaneswar this time. Anyway, let's start. It's already quite a bit late in the day and people must be tired. I'll try to wrap it up with only the interesting features that I wanted to talk about. Mrityunjay's talk yesterday and today Daniel's talk and Arjun's talk has summarized quite a lot about the basics of Carolean symmetries and weird features that we see quantum field theories having Carolean symmetries. My talk will be especially for a bit of condensed matter applications and focusing on the electric aspect of Carolean symmetries where we see localization and ultra-localization to be more precise. Now, to start off with, I will pose an undergrad physics question. What happens if I create a small fluctuation localized in space and let it evolve quantum mechanically with respect to a local Hamiltonian? To answer this, the answer is very well understood. If you create a small fluctuation, very localized in space and let it evolve, what you would expect from non-relativistic theory, the local Hamiltonian is a non-relativistic theory, you will see it will spread out the fluctuation and the same will happen for a relativistic field theory as well. Standard wisdom tells that the fluctuation will disperse. And this is why we are more, when we are talking about free field theories, we are more concerned about dispersion relations. Now, what if I don't want it to disperse and want something like this? I again create a small fluctuation localized in space and let it evolve. And depending upon curious engineering of my Hamiltonian, I don't see a spread of it. And I see it's, there are some fluctuations spread. It's caged, just like a lion, it's moving around there, maybe a little bit here and there, but it's not spreading, just like this. That's why sometimes people call it that the fluctuation is caged. Now, the point is that there are questions that would arise, of course, why in my sane mind would I want that? And of course, how can I achieve, for example, how will I tailor a Hamiltonian which will give me such an evolution? Thirdly, what are the aftermaths of this? Let's say by hook or crook, I can get such a situation. What are their implications? Of course, if you have a very boring theory, you have no dispersion, this will definitely happen, but we want something more interesting than the most boring. Now, to answer that, why would I want that? As you have heard from Mrityunjay, Daniel, and Arjun, also in flat holography, we are dealing with Carolean symmetric field theories where correlations are very ultra local, in particular in a certain branch, the electric branch. The second interest comes from flat bands in real materials. In condensed matter physics, people really worried are concerned about materials having flat dispersions. And of course, there are other experimental setups where you can engineer such a dispersion in an array of cold atoms. Now, the point is that how can I achieve, as a theorist, how can I achieve such a Hamiltonian? I will be appealing to Carolean and BMS symmetry and go beyond a little bit. While I'm talking, I'm not just talking about universal features, but model-dependent questions. So I am more interested about designing such models. And aftermaths are very fun. So there we can see quantum phases of matter, like higher order topological insulators. There are fun quantum group structures emerging, and very ease of access that gives rise to possibly anionic excitations. We are yet to work around in this, but there is some interesting stuff coming. Lightning fast Carol algebra recap. We already have seen this quite a few times today itself. The crux is that, unlike Poincare, you have the Carroll boost, which has this xi delta form, and you can easily extend this to an infinite number of other generators, b suffix x, if where f is any function of spatial coordinates del t. Now these bfs for any arbitrary f and g any function, they form an abelian ideal of this larger Lie algebra. And the algebra closes. That's the main important part while trying to construct theories or models which will respect this. Okay, so that's it. And then possibly I'm repeating this from Daniel. That so this is the quote from Schwinger back in 1963 that any local relativistic quantum field theory will have this property that the Hamiltonian densities at 2 points won't commute. But if you have Carroll boosts in particular super translations, the Hamiltonian densities at any point will commute. This is what ultralocality is, can be thought of this the way we understand causality in quantum field theories. This breaks down because of the collapse of the line points. The most boring theory that you can come up with that has this is like this, that you can write an action with no gradient term, no spatial gradient term, and the consequences are funny. You can directly work out the consequences. The correlations are, of course, ultra-local. You have Dirac delta functions, spatial dependence, and of course the gap comes and tells you the temporal dependence. You can add any interactions there. We worked out with various interactions, and in the presence of these interactions, we calculated one loop beyond one loop, and these super translations are anomaly free. What happens is that the mass term gets renormalized. That's it. Nothing more happens here. There are, of course, non-trivial RG fixed points, but that won't be focus of my discussions today. Their other thing is that, of course, since there is no gradient and correlations are very, very localized, there is no entanglement that you can see in these theories. Other curious feature that would be interesting or important in condensed matter applications, that you cannot couple any magnetic field. At least minimal coupling doesn't work here because you do not have a grad term, so you cannot replace grad with a covariant term. Okay, with that said, so these are our 2 plus 1 cents. The third one is, the plus one is coming up sometime soon. Arjun, Aritro, and some of students, Shoikok, my students, and we are growing up in collaboration sizes. People in condensed matter community are getting interested in this stuff. So I think that this is just beyond curiosity in localization of physics, but maybe real condensed matter applications would be useful using the methods that we are working on here. Okay, to start off with, we will be working on a lattice. And since we don't want a very boring theory, we will expect their fermions on the lattice, the fermions to hop from one lattice point to the other lattice point. My Hamiltonian is given by this, where Hj connects to nearest neighbor lattice points. You have creating a fermion in J plus 1 its side, and at the cost of fermion at J's side. Where Q, we will have to determine what the object Q might be by imposing the conditions of ultralocality. This is the basic premise. What we will do is that we will, if you have just a Hamiltonian like this, where Q is a real number or a general matrix, what will happen is that you will get dispersion. The kind of dispersion that we discussed earlier, it may be a Schrodinger-like parabolic dispersion, or it will be a dispersion like a relativistic Dirac-like dispersion as well. I don't want that. What I want is that very ultra localization, time evolution, first derivative, of course, will show you some dispersion, but that has to be there since this has non-trivial hopping. What I want is that second derivative or any higher derivatives will keep you localized very much there at the same lattice point, that is psi j double dot should go as psi j. This condition is very severe, and a little bit of algebra gives you that this takes your q square equals to 0, where and q and q dagger anti-commutator should be proportional to identity. Only then this alpha localization happens. Now, basically, this is a harmonic algebra of q matrices denses, or you can call them Grassmann objects. If you can choose representations of q's, and standard you can do the diagonalization of the Hamiltonian, and you'll see that there will be two distinct dispersion bands. Means no dispersion will be there. They will be perfectly flat bands. So here is the connection between imposition of strict ultra. How it appears in the discrete lattice models is that you impose ultra locality, and as a byproduct, you get flatness of bands. This is one of the first non-trivial representation of such Q matrices that we construct this way. This is a two-dimension, so your fermions will be two-component fermions. You can, of course, construct higher dimensional representations of these nilpotent Q matrices. This is one of the pictures of a condensed matter realization. You can construct this in lab using ultra-cold atoms. This lattice model has been known for quite a long time by Kreisler. I'm not going into the details of this hopping network, but so this gives us one of the ways to construct this model of ultra-localization. This is a mnemonic where we can see how it works is that normally at the top picture you will have two dispersion bands. In continuum field theory, what we do is that we do the Dirac part, we do the creation and annihilation interchange, and we do not want the Dirac there. But in condensed matter, you can well do that because of finite number of particles. The standard one is the dispersive case. Now, for a particular choice of parameters, the parameters that I showed for the Kreisler, you get flat dispersion, where the vacuum sectors circled in reds and the half-filled ground state, where you fix your chemical potential in a certain way, both of them become flat, and the whole band becomes flat in this way. The characteristic velocity, the Fermi velocity, goes to 0. The other way to see this is that the effective mass that the electron feels while traveling in the lattice, that goes to infinity. So there are two ways. One is that you, if you are looking at it from a relativistic perspective, you call that the speed of propagation, characteristic velocity, or speed of light, if you want to say, goes to 0. The other way, this is not the way how condensed matter physicists discuss this phenomena. They call it heavy fermions, very heavy fermions. So because mostly in condensed matter setup, people do care of p squared by 2m like dispersions, where now if mass goes to infinity, that gives you a flat band in that sense. So there are actually two ways to look at them. Now, how to manifest chiral symmetry here is a little bit of trick here and there. We do combine my site local fermions. In this way, we call those compact localized states. This is a very common nomenclature in condensed matter literature. And we construct the Hamiltonian. The interesting feature is that if you write the Hamiltonian in these variables, which are also basically site local, these are not plane waves. These are basically localized, and these sites are again states of the Hamiltonian. How the super translations act on these compact localized states is given like this. That I showed you that EF here, F won't be a continuous function. Of course, we are working on a lattice. This is any arbitrary lattice function. What is that now, since f is any arbitrary, we can construct all the infinite number of possible Noether charges, which all come. Now this spells us integrability. Of course, there is no surprise because this is a free theory and any quadratic theory is integrable. What is interesting and important as far as I am concerned is that the integrability here comes from local space-time symmetries. In most, in all free theories, the integrability comes from symmetries which act non-locally. But here, there's this difference. We understand the symmetry principle behind very easily from a local space-time perspective. Ultra locality is that 10 more minutes. So I'll just rush a little bit. We can calculate the correlation functions in a fixed chemical potential where the ground state is half filled, and of course they show localization. Basically, this delta is when you take to continuum limit, this gives rise to Dirac deltas and derivatives thereof. We added interactions here. An addition of interactions give you exotic quantum phases, which are observed by change in the ground state structures. I won't go into the detail of it. What I'll briefly tell is the fragility of the Carroll symmetry. What we did here is that we had the interacting Carroll theory, which is of course Carroll symmetry. We did add a little bit of perturbation. In our CFD language, most of these perturbations that we can add are relevant perturbations near the transition points, near the critical points in the quantum phase diagram that I showed. What happens is that little bit of perturbations near the critical points. So if you are near the critical line separating two phases, little bit of perturbation makes the correlations spread out very large, and you get practically infinite correlation length. So the Carroll symmetry is very, very fragile if approaching from one side of the critical line. What happens is that it's robust if you approach from the other side, but that's another long story. I won't go into this because I want to tell you a little bit about what happens in 2+1 dimensions. Basically, we repeated this same structure, same analysis in two-dimensional lattices as well. Here, the algebra becomes a little more interesting. Since you are in 2 dimensions, let's say you are on a square lattice, you will have to have now not a single Q matrix, but a couple of them. And they have to follow the demand of ultra locality enforces that the Q matrices they have to satisfy a fermionic algebra themselves. Now this algebra has the first non-trivial representation in, okay, there's a 2-dimensional representation where you have to choose one of the Q's to be 0, the other one can be non-trivial, but both the Q's being non-zero has a 4-dimensional representation. Now, while doing so, I was thinking that the strategy is similar to what Dirac did more than a century ago. We are designing a matrix algebra to produce a particular dispersion for fermions. So this seems eerily similar to Dirac's approach for fermions, relativistic fermions. This is one of the examples for those Q matrices, and of course, any of their unitary equivalents to suffice. This system, for example, in the 2-dimensional system gives me 4 dispersion bands, and each of them are twice degenerate. Again, to see explicit Carroll, you need to do a little bit of jugglery with the matrices, just like we do a lot of jugglery with the Grassmann algebra for relativistic fermions. Analogously, you do a little bit of them, construct bilinears, and using them, you can construct compact localized states. And you can construct Hamiltonians, which are, the interesting point is that, look, if you write the Hamiltonian in terms of this, these guys are site local. So you have Xi-r dagger and Xi-r. It's not that Xi-r plus X dagger and Xi-r. So it's strictly local in this way. And obviously, at any 2 points, the Hamiltonians do commute. That strings of Carroll feature here. These are also known as frustration-free systems, where Hamiltonians in 2 different points. Actually, this is a very strong feature of frustration-free. The other way would be that Hamiltonian density themselves are conserved. That's already there. But Hamiltonian densities commuting with each other, it's even a stronger condition. Now the thing is that I told you earlier that since the continuum theory does not have any derivative, explicit derivative, you cannot couple a magnetic field with the model. Non-minimal coupling is not there. But while doing the same thing for a lattice, what you'll have to do is that you'll have to carefully do the Wilson lines, put them. That's called the Peel substitution, and a bit of longish calculation gives you something like this.
5 more minutes.
Yes, I'm about to finish. Now the Hamiltonian gets modified. Here you see what's in the summand. There is alpha. Alpha is the magnetic flux per placket, per square placket. And of course, there is a new element comes into the picture. There's the magnetic quantum group, magnetic translation group, where unit translations in 2 orthogonal directions don't commute. You'll have to do a little bit of modifications with that. Translation symmetry, of course, breaks down. That is something you can see from the structure, that this N1 index appears in the Hamiltonian density. For that, you have to choose rational values of the magnetic flux. All that being taken care of, one can do a little bit of trick here as well, and so one can gauge away this translation non-invariance inside Qy. Only one thing you'll have to keep in mind, that you'll have to satisfy the fermionic algebras of Qx and Qys. You can anyway do that by gauging away the magnetic term, but the effect of magnetic field remains in these newly defined brackets that I'm defining at Qx dagger, anticommutator suffix alpha. These are a Q-deformed version of the anticommutators, and they typically arise while talking about anions. We do not have a very good understanding why this structure appears here, and it requires a little bit of more discussion than feasible here. Of course, if you have these magnetic Hamiltonians, this is weird that magnetic field is entering the picture, but I'll tell a bit briefly that the Hamiltonian densities, even in the presence of magnetic field, they commute. So Carroll is still there. Carroll is not spoiled, even if you can see at first that the translation symmetries are spoiled. What happens for a lattice of fermions, if you turn on a magnetic field which pierces the lattice, the spectrum becomes like a fractal structure, which is known as Hofstadter butterfly. I should have put it here. That's a beautiful structure, and the distinct bands that you see is no more there. It's a completely fractal structure. What happens here? Carroll symmetry is still very much constraining that, and we do not get Hofstadter butterfly, but we get still 4 bands. There's a little bit of misnomer while calling it 4 bands, because translation symmetry is gone, again restored back by Gibbs transformation, so it has to be taken with a grain of salt. Those bands now do have energies which are which depend on the magnetic flux or placket. This is how the energies flow. In the x-axis in this diagram, that the flux quantized, I'm varying them. I do not need to give them rational numbers. I can give them any real numbers, because I can gauge away the issue of translation invariance. And you see, for alpha equals to 0, we had 2 degenerate flat bands. Each of these points that you see are flat bands. I'm just plotting their energies. Right. So this is a bit weird that I said clear Carroll symmetry prevents coupling with magnetic field, but there is still a bit of coupling, not as much coupling that you can expect from a dispersive system. still a coupling there, but we really don't understand because we are not being able to directly map it to a continuum theory as of now. A probable explanation is that even with zero magnetic field, each planet carries a non-zero current, which is interesting. That is generally seen in condensed matter systems with non-trivial topological order. And talking about that, what we did a little bit of, if you have heard about topological insulators, generally in these systems, what happens is that there are localized wave functions get localized at the edges, and that is responsible for this robust current in quantum Hall systems. But here, this is called a higher order topological insulator. What happens is that the localizations are local, the wave functions are, or the probability distributions are localized at the corners, and that's called a higher order one. People have, and this is topologically protected because if you perturb this, these corner localizations are robust under any kind of perturbation, means sane perturbation, local perturbations, any still local perturbations. This is a flat limit of, then we realized, went back to the condensed literature, and people have found it experimentally in 2017. This now is very famous as the BBH model. I'm not going to that. One last part. So the couple of systems that I showed had only flat bands, but real materials and people working with them, quantum matter, have flat as well as dispersive bands. We have, so inspired from our construction in Carroll, what we have done is that we really have the scope for designing such systems here as well. The only construction that we need here, which we already have, is a canonical transformation from the site local fermions to the things that are called, we are calling compact localized states. And this is the key equation which helps us construct any model which has a flat band and a dispersive band. I'll not go into the detail of the construction. If you're interested, we can talk about that. So you add dispersive fermions as well as flat fermions and revert back to real space fermions from the size, and you can have models like this where you have a flat band, you have a dispersive band. There's the crux that this work, this mix and match of flat as well as dispersive band works quote unquote when the band touchings are non-singular. I am not going to define band touching being singular here because that requires a bit of more discussion. So yes, I gave this talk to a condensed matter, proper condensed matter conference last week, and I saw people getting really interested. So this is interesting from the Carroll community, or rather asymptotic flat space-time community. Of course, I'm not saying that these should be very good dual candidates for flat holography, but we are, at least flat holography got us interested in BMS physics and Carroll physics, and we are getting some interesting stuff which is of use in condensed matter. So that's why I'm a bit happy about the progress. And thank you for your patience. It's almost more than 6:30.
Okay, thank you, Rudra.
Thank you.
There is some technical issues here. I don't know how the question answer session can. Okay, so let us see if there are any questions. So there is one, Rajesh. Take a microphone.
Not the micro.
First check if you can hear.
Hello. Hi. No, nice talk. I was just wondering whether in this two-dimensional case that you mentioned, if you were to go slightly away from this Carroll limit, I guess the analog of your T1 and T2 being not exactly the same, do you recover this fractal structure for the bands, or is it, do you really have to break it very
No.
strongly?
So the fragility is still there. We have checked that. Thanks for asking this question. Yes. So if you break it, you do a little bit of perturbation, Carroll breaking perturbation, and you turn on magnetic field, the whole fractal structure re-emerges. Yes.
Thank you. Next, there is a question from Shiraz.
Hi, I had a question about very early in your talk where you were talking about this scalar theory with time derivatives and potentials. If you could go back.
Yes. Yes, I can hear you.
Yeah, it would be great if the slide could come up.
Okay, yes.
You had one or two later where you had a V of pi as well. This is 5 to 6, exactly. So first question, in this theory, if we were to compute correlation function of phi square, a composite operator, that looks like it would be delta function square, which looks somehow singular. Is that okay? And sorry, second, let me just ask the second question as well, and then, I was wondering how the perturbation theory here works. Because say I take down 2 vertices of phi to the 6. Now I do a contraction, I get delta function to the 6th. So it seems to me like this lambda will have to be like 1 over delta 0 to the 5 in order for this to make sense. And I was wondering if that is correct and if it's okay. And last question about this is, if you put this theory at finite temperature, it seems to me that the free energy will just always diverge because it's just a bunch of quantum mechanics with an uncountably number of quantum mechanical systems. So just are all these things okay?
Again, Shiraz, most of your question has been answered by Jordan Kotler and French Christian Jensen in their paper related to us. So they worried too much about composite operators, and they did vector fields as well. And what one needs to do is they basically do a little bit of good regularization in order to make sense of this. I exactly do not recall the exact result, but products of Dirac delta functions would be there if you have composite operators, and probably not derivative, sorry, just products of Dirac deltas. If you do the regularization or ordering of the operators nicely, then you can get probably not the largest Dirac delta function that you expect, but something lesser than that. And about the thermal field theory, there was a little bit of consensus among Jan de Boer and their friends, keeping it at a finite temperature. What they initially thought that the partition function blows away. For example, if you wrap around the scalar around the compact manifold, the things blow away. But again, that's a very regularization dependent question. One can get rid of that. But of course, it's again a very quantum mechanical question. You really don't get out of, so the questions are decoupled quantum mechanical oscillators. You just need to do regularization properly. For magnetic, there is something called magnetic branch, which I have not covered. You get something more interesting than that. So your voice was breaking. I could not completely get
No, the answers have been perfect exactly about my question. Just one last question about the thermal physics. Normally we put counter terms that can, renormalize vacuum energy and so on. But once we've done that, the temperature dependence of a partition function is physical. It's not, counter terms don't affect. Here it seems to me that even the temperature dependent parts will have a high degree of divergence. Just because you
right. Yes, that's true. The temperature dependent part has a high degree of divergence, yes. True. Because you can map it to a problem just like this is basically when we study statistical mechanics, this is just the Einstein model of solid specific heat. Whatever answer you get there, you'll get here as well. So unless you go to something doing like coupled oscillators, like as in Debye model, you won't get. But the statistical mechanics would be as exactly similar to what you get in an Einstein model of specific heat of solids.
There's a comment from
Well,
this is actually related to this. So Kotler and I think they are saying that, I mean, there is some UVR mixing. I mean, if you do it, so before you compute these things, if you put it on a lattice and do all the things, so it is not necessary that, I mean, there is a good continuum limit of that, and even if you do that, you may find UVR mixing. I mean, that's the area.
Do you have any comment?
I could not get the points that probably Shomik was saying something. Anyway, so we already can talk about it later.
Yeah, sure. Okay, thank you, Rudranil. We wrap up here this session, and thank you, Rudranil, and thanks to all the other speakers of this afternoon session.
Thank you.
Okay, so this session is over, and now we have a meeting of all the people who are working in Indian institutes in exactly 5 minutes time. So just take your 5 minutes break for whatever reasons. The others, unfortunately, will also have to leave this room. Those who are only people who are working in Indian institutes, faculty members, please stay and come back after 5 minutes. And dinner is, as usual, third floor here. Time, I mean, it's a fluid concept here.
Well, you like Carolian visits.
लॉग आउट करना है ना नहीं 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 मैनेज नहीं नहीं यहाँ से
नहीं करना चाहिए मेरे को
ठीक है एक काम करो इन लोगों को बाहर जाना
5 मिनट की मीटिंग है ना
ओ हाँ
प्रॉब्लम
अच्छा इसमें
नहीं इसका खुल जा
रहा है इस नहीं
मैं अपने फ़ोन से कर लूँगा तो मैं सोच रहा हूँ
फ़ोन से कर लो
So,